is the Industrial Controls Panel course. The audio and presentation / recording of this course is copyrighted by myself, Vincent Wedelich. The material to prepare this course was taken from the internet. I don't think that there's one original slide that I created here. All the material was taken from either standards or from other manufacturers. The purpose of this course is purely for educational purposes only. Industrial control panels, all material again was taken from the following: the internet, Wikipedia, Eaton, Square D, Cutler Hammer, Siemens, ABB, Allen Bradley, all other manufacturers, UL, IEC, EN, British Standards, API, PIP Standards. This material is being presented by myself, Vincent Wedelich, for educational purposes only. Consult the manufacturer before utilizing their equipment. So what we're going to do first is we're going to go over definitions. The definitions were taken from a Siemens manual. It's a good manual. Later on I'll continue utilizing that manual to step through some of the UL 508A practices. I think it's like probably 20 slides of definitions. First, you have 3-wire control. In a motor starter, you have a start and stop switch or a button at the motor, so that's considered a 3-wire control. 1 wire connects to the start button or the stop button, and then it connects to the start button, and then from there it connects to the motor starter. So you have a 3-wire. The motor starter's command device arrangement and latching contact control circuit. ANSI is the American National Standard Institute. ANSI is the most senior authority for regulation in the USA. Most regulations feature the ANSI standard, such as NEC 2008. The NEC is now in 2011, and then also UL 508A. AWG is the American Standard Wire Gauge, or American Wire Gauge. There is a British standard, which is called the SWG, Standard Wire Gauge. This is an international label for wire cross-sectional area. American wire gauge, let's say a 16-gauge wire is equivalent to a 1.3 millimeter squared. In the in the UL standards, in the NEC standards, and similar American standards, we always reference American wire gauge sizing. Branch circuit. The term branch electric circuit is a term that they use in the NEC, and it's the starting point from the load, all products up to the first overcurrent branch circuit protective device. So everything below the branch circuit protective device is called the branch circuit. So the branch circuit protective device, the BCPD, is a device for protecting the branch circuit. Listed fuses, circuit breakers, or miniature circuit breakers, which are built in accordance to UL 489, can be branch circuit protective devices. Some of these smaller little miniature breakers, if they're not per UL 489, they're called supplementary protective devices, and you cannot use them on the main. CANEA is a NAFTA standard. Didn't really take off as much as they thought it was. It's really for harmonization between North America and Mexico, but the NAFTA standards really didn't take off. I don't know whatever happened to them. Circuit breaker, molded case. A circuit breaker generally UL approved for UL 489. A Class 2 circuit, you have a Class 1 circuit or a Class 2 circuit. A Class 2 electric circuit in devices are devices tested and approved by UL for limited energy circuits. So when you see a Class 2 circuit, it is a limited energy circuit. Clearances need to be maintained so that you don't have something jumping over and faulting out to ground or something like that. So you want to make sure the distances through air and over surfaces are per UL. If you're using insulators or those small little red apple insulators, you want to make sure that they are designed for that voltage, and that the panel doesn't have a lot of dust buildup, because dust buildup or moisture in the panel can reduce that creepage distance or clearance distance, and you can have a flashover, and you certainly don't want that. Combination motor controllers. don't remember when they started making these or really started using these, probably in the early 80s, maybe even the 90s, where they had these IEC style motor starters where they had the circuit breaker and the contactor all built into one. So it had a starter with a disconnect switch, a circuit breaker, or a disconnect switch, or a combination of both. And this has the motor controller, including the disconnect switching and overload functions for the motor circuit, branch circuit. So it's one device that can snap right onto a DIN rail. It's pretty nice. And they made UL508A. Something I should mention here is this course primarily is UL508A because we are, I'm American, so I usually deal with UL or NEC or NFPA, but we will talk about CE and IEC standards. If you look at all the Siemens, Square D, ABB devices, AB devices, they all have dual ratings. They are all UL and IEC rated. Rarely do you ever see them not rated dual anymore. The term common control is a control circuit without a control transformer. So you have rated voltage at load and on command devices. So if you have a 120 volt source and that 120 volt source comes from a remote circuit breaker panel, then that is considered a common control. It doesn't require, in this case, a control power transformer. Conduit is the means or the wire way, typically in pipes where we lay the electrical cables. You want to make sure that when you put wires in conduit that you don't overfill them more than 40%. There is a case where if you have one multi-conductor cable, I think it's 52% you can fill it up. Typically what I do is I try to keep everything below 40% because it's just easier to pull it through. You can also have a liquid type connector for connecting to a motor, so it's a flexible connection. You want to make sure you utilize the proper type of fittings and connections, and make sure that you don't make that too long, because there are certain standards or certain length requirements when you're installing liquid tight conduit. Control circuit, class 1 direct. You have your common control circuit, means that a control transformer is not used. The voltage corresponds to that of the motor and or load. Control transformer is a transformer as referred to as a control transformer if it only has control circuits connected on its secondary. So if it has control circuits, then it's a control transformer. If it has power circuits, then it's a power transformer. So CSA is the Canadian Standards Association. The CSA publishes standards and approves products in accordance with its own and other standards, such as IEC, EN, UL. I don't know who wrote the CEC first. Was it NEC or the CEC was written first? But the CEC is a well-written document. It follows along with the NEC real closely, but the way they wrote it, it's easier to understand. It's not as subjective to misinterpretation because they write it out so clearly, in my opinion. I think that they should elaborate a little bit more on that on the NEC because it seems to be a little easier to read. Daisy chaining, this is a term used when you're running one wire. Let's say you run it to terminal 1, and then you jump her from terminal 1 to terminal 2, then from terminal 2 to terminal 3, and terminal 3 to terminal 4. If the connection from 2 to 3 is disconnected, then all the power on 3 to 4 is dead. That's considered a daisy chaining, the layering of wires in series from one terminal of a device to another. A disconnect switch is a switch for disconnecting, and it needs to be UL listed. EEMAC is the Electrical and Electronic Manufacturing Association of Canada. It's equivalent to the American NEMA standards. ETL is the Electrical Testing Laboratory, and ETL is a test body that approves devices in accordance with other regulations such as UL, IEC, CSA, etc. You have external wiring. This is field wiring laid by the electrician. It is not internal, it's external, and there's certain rules that apply with external wiring when you're building a control panel versus internal wiring. Factory wiring is wiring that is only laid and connected in the manufacture of industrial control panels, i.e. under supervision. So factory wiring is compared to internal wiring in the control panel. Factory wiring terminals. The actual terminal blocks are used to connect up in the manufacturer industrial control panels. So you'll have a field terminal block, and you'll have internal factory wiring terminal blocks or terminals. FCPD, it's a feeder circuit protected device, a device for protecting the feeder circuit. Listed fuses, circuit breakers, or miniature circuit breakers can be used. They do need to be listed per UL 489, not just 1077. Feeder circuit starting from the load. This refers to all products upstream of the first overcurrent branch circuit protected device. And you can reference NEC and Article 242, 215, or 220. If I haven't mentioned, we are in NEC 2011 already. The NEC comes out every 3 years. Field wiring. Wiring is connected in the field by an electrician. So that field wiring, if it connects to the terminal, the field wiring terminal, you need to specify the torque value in your markings of that control panel. Field wiring terminals are terminals that are connected in the field by the electrician. So, and you can reference UL 508A, Article 28.3 and 37. FLA is your full load amps. This is the rated motor current according to the nameplate of the motor used. FLC is the full load current. This is the rated motor current according to the tables of UL 508A and the NEC. You know, why do they even differentiate this? Because when you buy a motor, it's tested, and they'll give you the actual full load amps that motor runs under a full load condition. You might not ever see that motor. If you're building a UL 508A panel, you might never see that motor, so you can only use the full load current. And the full load current values are used, these are tables that UL 508A and or NEC uses that are typically a little higher than the actual full load amps. So you want to make sure that when you've got overloads for these motors that you use one of those combination starters that gives you an adjustment range. If you have an adjustment range, you can usually get within close to that value so that if they need to, they can adjust it in the field just a little bit. You don't want to go too high on your adjustment range because you don't want somebody to burn up a motor. Factory Mutual Research, FM. This is the work of FM mainly involves testing components for non-electrical systems such as boilers, water heaters, or oil stoves. GFCI is a ground fault circuit interrupter. A ground fault circuit interrupter usually trips at about 7 milliamps or so, 5 to 7 milliamps. As long as it's below that value, you typically won't electrocute somebody, cause death, right? They'll feel a tingling, but they won't die. There is a EFCI, an equipment fault circuit interrupter, and the equipment fault circuit interrupter is usually for the heat wire, the heater wire that they put out there. What is that called? Thermocouple? No, it's not a thermocouple wire. It's the heat trace wire. And the heat trace wire for freeze protection and stuff like that would use an EFCI, and it's set at about 30 milliamps. 30 milliamps can cause death, so you don't want to make sure that you don't get confused with a GFCI and an EFCI. A GTCP is a ground tap circuit protector. It's part of your motor branch circuit protection. Horsepower is what we measure loads, motor loads in. 1 horsepower is equal to roughly 0.746 kilowatts, or 1 kilowatt equals 1.34 horsepower. IEEE is the Institute of Electrical and Electronic Engineers. This body publishes electrical and electronic regulations as well as papers and things of this nature. Instantaneous trip circuit breaker, a circuit breaker with just one magnetic trip unit, may only be used to protect the motor and only if overload protection is present. So you got to watch out. Some breakers are actually they're magnetic only. They don't have a long time or a thermal overload in them, and so they'll only detect, or they'll only trip if something is greater than, the inrush current on a motor, let's say, is 6 times the full load amps. So it has to be something significantly higher than that, right? So you want to make sure that you understand what kind of breaker you're using, and if you are using an instantaneous trip circuit breaker only, that means you have to install overload protection on that motor as well for thermal or long time detection. Internal wiring is the wiring for the power circuits laid by an industrial control panel builder. It's also compared to factory wiring. The inverse time circuit breaker is a circuit breaker with a thermal or magnetic instantaneous trip unit. So you have it has with thermal or magnetic. So it's got both the thermal or magnetic, if you will. So you want to make sure that if you're installing a breaker and you have a thermal and magnetic trip unit, that you set them properly to protect these the loads. JIC, we don't really see this anymore. It's a Joint Industrial Council. Industrial control equipment for an automotive industry used to be standardized for this body. This body no longer is active, but is often specified in NFPA 79. KC mill, when I was younger, we always used MCM, right? MCM is actually 1,000 circular mills. The thousands is M, but they switched it over to KC mill, which is a little easier to see. I still get stumbled up and I call it 500 MCM when it really is 500 KC mill. So what we're talking about is 1,000 or kilo circular mills. Wire size is the cross-sectional area specification. 1 mil is 1/1000th of an inch. A wire of 1 circular mil is a round wire with cross-sectional area of 5.063 times 10 to the negative 4 millimeters squared. So it's the physical size. So a 500 MCM cable is a fairly large cable. Probably carry about 380 amps on a 75-degree C terminal chart. Knockouts. Knockouts are the openings where you would connect your fitting or cable conduit connection at the bottom of the panel. A KO is also a knockout. A label service is a UL program for certain products which are provided with a special label. Listed or listing is nothing more than a list. That's what this really is. A list is like UL or ETL or a company like this has a list of all the authorized manufacturers or equipment that can bear their name. So listed or listed. Listing or listed, a device that is tested by UL or another approved body and managed in a list. So that's what they're telling you is if it's UL listed, it should be somewhere on a list within one of these companies. Your locked rotor current, or LRC or LAR, LRA is a locked rotor amps, or MLRA, motor locked rotor amps, is your motor starting current. Typically your motor starting current is about 6 times the full load amps. You can go to the NEC article 430.251B and you can look up typical values for these different motors, but really if you really want to know, you have to go directly to the motor manufacturer and get data from them. Main disconnecting means a supply circuit disconnecting device either in the form of a circuit breaker or a disconnect switch. So you want to make sure you know where your main disconnecting means is, right? This is where you can isolate the power to that control panel. Your MCP is your motor circuit protector. You can compare this to instantaneous strip circuit breaker that we just previously read. Your miniature circuit breaker, MCB. It used to be that these miniature circuit breakers were only supplementary protectors, right? They can only be used for small loads such as solenoids, things like that. They couldn't be used as the main branch protector. If there are already small miniature breakers now that have that UL 489 label or listing, and they can be used as branch protectors. So you want to make sure that when you're using a miniature breaker, if you're going to make it your main breaker of your panel, then it needs to be UL 489 labeled. If it is 1077, then it needs to be then it can't be your main disconnect. Let's say if you have a PLC or something and you're running it to a solenoid, you can put a supplementary protector on there. And then you've got motor branch circuit, and you can look that in NEC article 430.1. A motor control circuit is a circuit which produces electrical signals for controlling machines or systems. Control circuits are normally limited to 15 amps. Control circuits can be set up in a variety of ways. Directly connected upstream of the branch circuit protective device. Appropriate protective devices for feeder circuits should be used here, such as circuit breakers or according to UL 489. Directly connected downstream to the branch circuit protective device. Devices known as supplementary protectors can also be used here, such as miniature circuit breakers according to UL 1077 or via transformers or power transformers, and you can reference NEC Article 430. Your motor feeder is your motor supply cable. So this is the cable that connects to the terminal side of the starter, your motor starter, and goes all the way to the pecker head or the connection box of your motor, your actual motor. Your MSP is your motor starter protector, an American name for a circuit breaker in accordance with IEC EN 6947-2, which shall not be used in the USA as a circuit breaker. So some of these motor starter protectors have overload capability. They can be like a disconnect switch, but you want to make sure that you don't use them as your main circuit breaker because it's not built per UL 489. NEC is the National Electrical Code. It is written by the National Fire Protection Association, which is Article 70 of the NFPA is the NEC. The NEC is the installation regulation for the USA. So when we're installing a control panel, we use the NEC to install it. If we want to run cables from a motor to the control panel, we would use the NEC. The NEC is generally used by local inspectors, authority having jurisdiction, AHJ. In many cases, local authorities have added extra conditions to it. The NEC is revised every 3 years. The current version is 2011. This list of definitions is a little old, but certainly a good list of definitions. So NEMA is your National Electrical Manufacturers Association. We have NEMA for enclosures. We have NEMA for magnetic controllers and overload relays. We have NEMA for general regulations. We also have NEMA for motor sizes. So there's different type of NEMA standards. Your NFPA, we already talked about, your National Fire Protection Association. The NFPA publishes numerous regulations and guidelines such as the National Electrical Code or the NFPA 79 Electrical Standards for Industrial Machinery. So we will talk, they talk about NFPA 79 for industrial machinery. So NFPA 79 is the electrical standard for industrial machinery. It is mainly used in the automotive industry and is specified for manufacturers of machine tools. NRTL is a national recognized testing laboratory. You might hear somebody say it's a NERTL. Kind of a funny way of saying it, but an NRTL is a company that is approved by OSHA to oversee and authorize somebody to build UL control panels. So what you want to do is, a lot of times they think, oh, well, it's UL 508A panel, I have to use UL. That's not always the case. You can use UL, you can use ETL, you can use CSA, you can use TUV, you can use MET, Met Laboratories. These are all viable OSHA-approved U.S. state bodies. They all happen to use the UL 508A procedure. UL was the original one that wrote the procedures, and so but any of these authorized state bodies can administer this program for you. I'll be honest with you, I've dealt with UL and I've dealt with Met Laboratories, and Met Laboratories is a little bit more flexible. It's not that they're not as safe, that's not true at all, they're just not as rigid. And so they interpret things a little bit, it seems like they help the manufacturer more than try to hurt them. Not that UL does try to hurt anybody, it's just sometimes they get so rigid you can't work around something, whereas Met Laboratories would say, no, that makes perfectly good sense. And I found it to be a little easier to work with them. But teach your own. ETL, TUV, UL, whatever you want to use, it doesn't really matter as long as they're a nationally recognized testing laboratory. OSHA is the Occupational Safety and Health Administration. The OSHA publishes guidelines for safety in plants and workplaces. If you know of something that's not safe, then OSHA would be the organization that would come out there and maybe issue a fine. It's designed to help you work in a safe place. Overload relays is a device for motor overload protection. We'll talk more about those. So, pilot duty rating. So this is the rated values for contacts which switch solenoids specified in A600 or P600 for Siemens panels. One of the things you want to be aware of is a switch or a push button, or the contacts on the push button or the contacts on the switch need to be rated for the load. And so IEC came up with this nice little rating system where they use the AC15 or DC15 or different values, and we'll talk about them later. But you want to make sure that you use the right switch for the right load, otherwise you could burn the switch up and it wouldn't last very long. A power circuit, the power circuit can be connected directly to or via transformers. Electric motors are generally connected to a power circuit. Devices for a power circuit should be used here, such as circuit breakers according to UL 489. If it's a power circuit and it's your main breaker, you want to make sure it's UL 489 rated. Something that some people might not be aware of is circuit breakers that are UL 489 listed are usually listed at a certain temperature. So if you look on the side of the breaker, you'll see it says listed for 75 degrees C terminal temperature. That means that you should use the 75 degrees C terminal column when you're sizing the wires for that breaker. Some people think that they can just use a 90 degrees C rated cable, and really that's not true. They need to use a 75 degrees C rated terminal. Otherwise, the conductor temperature will get above 75 degrees C and could trip the thermal rating of that breaker, so you want to be aware of that. Power transformers. A transformer is referred to as a power transformer if the loads connected to its secondary side are motors, or almost always loads, solenoid valves, etc. are seldom to be considered as loads. So you got power loads, so it's a power transformer. Recognized. When they use the term recognized, this is components and devices which are not in general use, but only when certain conditions are met. So they're not a UL listed device, it's a UL recognized component, and they're usually in that yellow book, so a recognized component index. Re-examination services is your factory inspection or UL inspectors for UL listed products. RMS is a root mean square, which is the effective value, if you will. We're looking at a sine wave. If we have a sine wave, we look at the peak top of the value of it. We take the RMS times the square root of 2 would be the peak value of that. So if we had a 120 volt AC RMS signal and we wanted to know the peak value of that, we would multiply 120 times 1.414, which is the square root of 2, which would be roughly 169 volts AC. Self-protected combination starter is a device or group of devices which are approved in accordance with UL 508, Type E for controlling and protecting motors. You have Type E, Type F, things of that nature. Series ratings. The UL listed combination of 2 or more circuit breakers for the purpose of increasing the short circuit rating. You can't, as an individual, create a series rating. This has to come from the manufacturer. The manufacturer submit the different combinations that they want series ratings on, and then UL tests them to prove that they can withstand that current. It was probably in the year 2002 or 2001 where we started being required to put short circuit ratings, the SCCR ratings, on control panels. And they, obviously if you put 2 breakers in series, you can actually increase the short circuit rating or current rating of that device. But again, you can't make the call. The manufacturer has to list it, and UL has to approve the series rating. Service entrance is the termination point of the utility or after the main transformer of the building. So if you have a power pole and you've got 3 transformers on that power pole, the secondary side, the first place it connects to, is your service entrance. And you can look up in the NEC Article 220 defines what the service entrance requirements are. Short circuit interrupt rating. This is the short circuit breaking capacity of the circuit breakers and fuses. Years ago, I guess people they weren't as concerned with this, or didn't think about it as much. Certainly when we were designing MCC, motor control centers, or switchgear, we were always cognizant of it, but when they were building control panels, maybe they weren't. Let's say if you have a 1000 kVA transformer at 480 volt AC 3-phase, then you'd have full load amps of 1202 amps. If the impedance of that transformer was, let's say, 5.75%, you take the full load amps divided by that 5.75%, that gives you about 20,000 amps or so. That 20,000 amps, if there's a short circuit on the secondary side of your breaker in that control panel, and that circuit breaker is only 10 kA rated, then the breaker itself will be destroyed, right? It cannot interrupt that much current, and shrapnel and what have you will come off that breaker and fly into the face of the technician. So you want to make sure that you understand what the short circuit breaker capacity is, and what size the transformer and the impedance of that transformer is feeding you, so that you can install all the stuff inside that panel rated for that short circuit rating. So what we're required to do now is put the SCCR rating on the control panel, so that an electrician who's installing that control panel knows, hey, this panel SCCR is only rated 10 kA, and I know for a fact I've got a 65 kA rated system here. This is a mismatch, so they need to fix that mismatch, and you need to make sure that you understand what the issues are concerned with that particular installation. So then you have a starter, which is a magnetic controller or overload relay. Supplementary protector, again, a good example of a supplementary protector would be a glass fuse. Some certain little miniature circuit breakers are also supplementary protections. They're per UL 1077. You don't want to use a supplementary protective device on the main controller or the main breaker. Terminal blocks. All the terminal blocks in your panel need to be UL listed, and you need to make sure that they have the proper voltage and the proper current. And you also need to make sure that the wire size, if you've got a large field wire, let's say that motor is installed 1,000 feet away, which is very far, they'll have to oversize the wire to deal with the voltage drop. So you want to make sure that you understand how far that motor is from your panel, so that you can install the proper terminal block size for the oversized wire. We'll talk a little bit about voltage drop on a later slide. Thermomagnetic breakers, we covered that in the inverse time circuit breaker. Again, they have to be UL 489. They can be either thermal, or they can be magnetic, or they can be a combination thermal and magnetic. A type E is a self-protected combination starter. A type F is a starter combination magnetic combination starter / controller. UL is Underwriter Laboratories. UL publishes standards and approves products in accordance with their own and other standards, including IEC, EN, and CSA. UL standards are obviously 508A or UL 489, etc. So there's quite a few standards that you'll have to comply with. Here we have a control panel. This looks like a pretty well built control panel. Looks like a NEMA 4X. That means it can be sprayed from all different sides with a high jet spray, and the components will not get wet inside that control panel. It's a stainless steel, so that's the X. That's corrosion resistant, so it's not going to rust or fall apart because of salt-laden hair and things of that nature. You can see it's got gaskets. It's got that 3-point latching system where that handle turns and it latches in 3 places: the top, the middle, and the bottom. The components appear to be laid out properly. They have that gray Panduit wireway. It looks to me like there's a good spacing in there, so you can get in there and wire it up. The things you want to make sure you do is, when you do design a panel like this, obviously UL 508A doesn't care if it runs. All they care about is spacing and hazards and safety, right? So they don't care about the, if it actually functions or not. But something you want to do is you want to make sure you add up all your loads and you're not overloading your CPT, your control power transformer. You want to look at the heat dissipation in each one of those components, because each one is going to have heat coming off of it, and you want to make sure that that panel is designed to withstand that heat. UL control panels only go up to 40 degrees C ambient, which is 104 degrees F. Typically, you could have it anywhere from a 10-degree delta there. So that means if you're in a 40-degree ambient, the inside of that panel shouldn't exceed 50 degrees C. You want to make sure all the components are rated at least 60 degrees C. So these are the things you have to consider when you're building control panels, and a lot more. We'll get into them. This next photo on the far left here has no pan to it. It looks like it has the old NEMA starters. They're not the combination starters. And you know, there's nothing wrong with this panel. You can certainly put a lot more components on the back pan. A little harder to work on. If you have to pull a wire or add a wire, you have to follow these little looms, wire looms, but it is a viable option. The one on the right looks like a Siemens panel. It's got Siemens components. The one on the left looks like it has a PowerFlex, which is an Allen Bradley component. You've got your fuses on the top on the one on the right, and then you've got that combination motor starter on the bottom. So you've got, what, 1, 2, 3, 4, 5, 6, 7 starters in a row right there, which is a significant amount of starters in a small little compact control panel, which is the beautiful thing about these combination starters. Here's another control panel. It's got some, I've never seen that wireway before. It looks maybe European or something. I'm not sure who manufactures. Maybe Panda manufactures it. Might be the manufacturer. The company actually puts their logos on it. You never know. Again, you've got your, on the far top left, you've got all those breakers, those miniature circuit breakers. On the far right, you have a disconnect fused switch. And then you've got a power supply to the left of that, and there's a ground bar as well. Again, that looks like a well laid out panel. You've got a PLC in there. It certainly looks like it's easy to work on, and they've thought about it. They've got nice little connections to the bottom for the terminations as well. Here's another control panel. This looks like a pretty nice panel. One thing you want to notice on this one is they've got a ventilation device at the top. You see that? It's like a fan or something. So they're blowing air in or pulling air out and trying. You got a bottom filter at the bottom too. You see that at the bottom right? So probably the top left is a fan, so they're pulling air through this panel. So they obviously have a heat problem associated with this panel, or it's going into a real hot area. UL 508A has, I don't know if they deal with that too much, the ventilation, but you certainly want to make sure that you don't drag any dust or dirt or any oily substances into this control panel. Certainly consider the heat. This is another nice big control panel. You can see you got 480 volt AC, pretty large. Looks like a contactor or a circuit breaker type contactor device at the top. It's connected to a power distribution block. Those power distribution blocks used to be only rated 10 kA. I think that has changed since then. The circuit breakers, there's what, 4 of them right there. They look like a square D circuit breaker. UL 489 certainly rated, probably an FAL style. You got a little GFCI circuit breaker, a little receptacle there to the left. You got a surge arrestor on the top right. Nice little panel. Again, the things you want to watch for are the heat that builds up in this panel. That CPT at the top left looks like it could put off a lot of heat, so you want to make sure you're not overheating one of these panels. Authorized NRTLs. It is imperative that you utilize authorized nationally recognized testing laboratories. This course will not make you an NRTL. It is not written by an NRTL. It's just presented for educational purposes only. I'm not affiliated with UL, MET, IEC, NETL, OSHA, IEEE, doesn't matter. I'm not affiliated with them. This is strictly for educational purposes only, and we're just going to discuss some of the standards and try to help you understand some of the standards and the terminology used in these standards. Designing industrial control panels, we're going to look at safety, understanding the components, understanding the process. We're going to look at UL508A, some IEC, we'll do some calculations. Safety, concern for your safety as well as the safety of others should always be on your mind. Most safety procedures are common sense, but because some hazards are not obvious, there are regulations born out of experience which are designed to make the workplace safer. There are two aspects of safety which concern us in the assembly of electrical equipment and control panels. The first concerns your own safety, in other words, the health and safety regulations. The need to use safe working practices and safety equipment to avoid the risk of injury to yourself and to others in the course of your work. While it is beyond the scope of this course to cover the details of all the safety precautions and safe working practices which should be adopted, there are some general points which can be noted. Safety equipment such as goggles, gloves, PPE should be provided and must be used where they are appropriate. The onus is on you to use the safety equipment provided by your company. Any damage to safety gear should be reported. Safe working practices are part of any job, and you should always learn and adopt them as a natural way of working. Don't take shortcuts which compromise your safety or that of anybody else. You should make yourself aware of the procedures used at your workplace to prevent accidents and to deal with common incidents. You should know how to isolate electrical supplies and how to work safely on electrical circuits. Accidents, know how to contact the correct person, the designated first aider for help. Find out the location of the nearest first aid box. Know how to isolate electrical supplies and how to release a person safely from contact with electricity. Fire, before commencing work on an electric plant, you should know where is the nearest fire alarm activator, fire exit, and fire extinguisher. Are the fire exits clear of equipment or rubbish? Extinguishers for electric fires. Be aware that special extinguishers are needed for fires which occur in electrical equipment. Do not use water-based extinguishers. In America, we have A, B, C, D, and K. A is for wood, paper, and clothing. B is for gasoline, propane, and solvents. C is for computers, fax machines, electrical UL508 control panels. D is for metals, magnesium, lithium, titanium, and K is for oils and fats. There are a lot of fire extinguishers that have dual purposes, like an A, B, C. So you want to make sure you've got the right fire extinguishers for these uses. Here you could have a type Class A or B, Class B, C, and then the preferred is Class A, B, C. So you can see if you have an A, B, C, that's the proper. You can use it for your wood, you can use it for gasolines, oils. You can also use it for your electrical fires. So you want to make sure you've got the right fire extinguisher for the right application. British standards, in Britain they have red extinguishers, which are water-based for your wood, paper, cloth, or plastic fires. They have green, which are halon or BCF based for general fires, not gases, including electrical fires. And then black are extinguishers for CO2 based for flammable liquids and electrical fires. So if you're in a British standard rig or whatever, and you're out there, you don't want to grab a red one, you want to grab a green one or a black one here for an electrical fire. Safety, electrical shock. Learn the basic first aid and action drill. Do not touch the victim with your bare hands until the power is off or they have been pulled away from contact. Otherwise, you will get a shock as well. And you'll both go down for count. Switch off the power and drag the victim off the live conductor. Alternatively, you cannot switch off use something non-conductive to move the victim away from contact, such as dry wood, PVC, or even dry piece of cloth, or folding several times will do. Make sure that you understand these rules and make sure you conduct drills to make sure that you are prepared in case of an emergency. Working with electrical equipment, many of the tools we use are electrically powered, some by the mains, some by batteries. Mains-driven portable equipment should be connected to supply through an isolation transformer. And also, you want to make sure that it's double insulated. These are usually 110 volt AC systems, which reduce the effect of electrical shock. However, 110 volt AC is not enough. You need to also add a GFCI, ground fault circuit interrupter. to make sure that you reduce the available fault current or the current to ground to 7 milliamps or less, and that will prevent an electrical fatality. Heavier fixed machines, such as large lathes, are wired directly to the three-phase factory supply. This is 415 to 480 volt AC, and there are stringent safety regulations governing its installation and use. Something you need to be aware of is these 480 volt three-phase systems can have high fault currents, arc flash values, and so you need to make sure that you understand the arc flash values and the short circuit current available from these devices, and make sure your panels and equipment are designed for that short circuit current. If you're going to open a breaker or close a breaker, you need to make sure that you're wearing the proper PPE to deal with that. Do not take liberties or chances with electricity. Don't interfere with electrical apparatus. Use it as intended, and don't remove any covers or panels. Don't tamper or use electrical machinery with tools that do not concern you. Leave switches and buttons alone. If you want to know how something works, and ask someone who is authorized to show you. Take care when using portable equipment, electrical equipment, power tools, since they cause the highest number of accidents in workplaces. That can be either a drill getting coiled up in your clothing, or some electrical faults. There's just so many things. You could trip over a cord, or you could get something in your eye, or a wide variety of things could happen. Safety standards that we're going to talk about in this course are UL 508A, the NEC, British Standards, IEC. All of these standards are designed to help you make a safe control panel. Safety, there's USA ANSI approvals are made by the Underwriters Laboratory and marked UL. You have CSA for Canada, DMKO for Denmark, CEI for Italy, NEMKO for Norway. Germany has DEN and VDE, France has NF and UTE, and Europe has CENELEC, CE. For the British standards, you have the EN 60204, covers the way in which the electrical equipment should be constructed. It includes everything from the selection of components through the sizes, types, and color of wiring to the electrical test that should be done on the finished equipment. Within BSEN 602204, there are references to other standards, including EN 60947, that will give more detail on individual parts or components. Remember, do not take liberties or chances with electricity. Don't interfere with electrical apparatuses such as use as intended, and don't remove any covers or panels. Don't use it or tamper with electrical machinery or tools that do not concern you. Leave switches and buttons alone. If you want to know how something works, then ask someone who is authorized to show you. Take care when using portable electric power tools, since they cause the highest number of accidents in the workplace. Accident possibilities range from tripping over carelessly laid power cords to getting swarf in your eyes or debris in your eyes because you don't wear eye protection. Next, we'll go over components. We'll go into some detail on the terminology and basic things you need to understand to be able to build a control panel. When building a control panel, you want to understand there's different types of drawings. We use drawings to convey the information about a piece of equipment in a form which all those involved in its production, installation, and service will understand. To make this possible, standard drawing conventions have been adopted by most companies. So you want to make sure that you design these control panels with standard drawing symbols. Circuit diagrams, you can have 1 lines, 3 lines, or schematics. You can have wiring diagrams, wiring schedules, block diagrams, and parts lists. The most commonly used electrical diagrams are schedules, and drawings are 1-line diagrams, elementary 3-line diagrams, schematic wiring diagrams, circuit breaker schedules, motor control center schedules, and lighting panel board schedules. You have out of the electrical diagrams and schedules, you have loading schedules, conduit schedules, wiring schedules, switchgear layout drawings, motor control MCC layout drawings, riser conduit stub-up drawings, and circuit wiring layout drawings or diagrams. The top left, we'll start at the top left. You have a low voltage circuit breaker. This is a typical 1-line. If you have a medium voltage circuit breaker, they use a square with a 52 in it. If you have a low voltage power circuit breaker draw out type, you can see the little arrows that indicates that it's a draw out type. So here you have a 600 amp low voltage draw out type. You can have those little draw out symbols on that 52 or even that low voltage breaker at the top. You have a disconnecting fuse, it's shown like a fuse lifted up. A thermal overload device, you can see the little symbol there that shows you that it's a thermal overload device. So it could be bimetallic or it could be electronic. And whenever it hits a certain value for a specified amount of time, then it opens and the motor trips. A PT, a potential transformer, or a CPT, looks like that. Here we have 4160 to 120 volts, so that's 4160 volts AC line to line, and then on the secondary side is 120 volts. A vacuum circuit breaker symbol looks like that. You've got a ground. You see the line with the 3 little dashes there at the end of it, that's your ground symbol. A lightning arrestor. A lightning arrestor is a device that whenever your circuit is hit by lightning, it'll arc over that open area there and it goes strictly to ground. A capacitor bank, if you have a capacitor bank connected to ground, that's the symbol that it would look like. A disconnect switch, this is the disconnect switch without a fuse. You could have, this we're talking showing here 1 lines, but you could obviously have 3 lines. Just stack 3 of these on top of each other and you'd have a 3 line. A current transformer is a CT or a toroid. Basically you have 100 amps flows through the main wire and it gives you a 5 amp secondary, so it flows out of that little dot. So you have looks like a donut with a wire running through the center of it. So you have a 5 amp secondary side and a 100 amp primary side. Could be 1,000 to 5, could be 3,000 to 5. 5 amp secondaries is a American ANSI standard. In Europe they use 1 amp secondaries. So here you have the next one, you have a current transformer with an amp meter. So you have the letter indicates the transformer type and the number indicates the ratio. So here we have a 600/5, so it's 600 amp primary. Current flows through. If 600 amps is flowing through, you'll see 5 amps on the secondary side. You have an amp switch, and that amp switch is a 3-phase circuit. So you can look at phase, let's say A to B, or B to C, or C to A, or A to ground, B to ground, C to ground. Depends on what your actual circuit is. And then it's connected to an amp meter. Next, you have these letter or numbers like 49, 51, 50, 27. We use those in protective relaying. So here again we have a 1200 to 5 CT. Goes to a 49. A 49 is a overcurrent, like an overload on a thermal overload for a motor. A 5051 is a type of relay that gives you an instantaneous and long time setting, current setting. So 5051 is related to the current. 49 is a thermal overload for the motor. Then you've got a PT connected to the bottom of it, which is connected to a 27. A 27 is an undervoltage relay or a voltage relay. So an undervoltage relay setting. So let's say that if your motor's starting, it'll cause the voltage to dip, the main voltage to dip, and you want to make sure that if the motor dips too far, then you detect it, and you can detect it with a 27 relay. On the top right hand side you have a battery or multi-cell. You've got a reactor as your next one, which is like a choke. You have MVA or KVA on a large power transformer. So here we have a 3-phase power transformer connected delta to Y. So you can see the little triangle symbol is on the primary side, that's your delta side. You have a Y symbol and it's connected to ground in the center of that Y, and that's the Y secondary side. An induction motor, and then they've got 100 in it. That indicates it's a 100 horsepower motor. If you have a synchronous motor, you have an excitation circuit, so they draw that little excitation inductor on the bottom of it, and you can increase and decrease the excitation circuit. So it's a 500 horsepower synchronous motor. So these are symbols that you'll need to use or understand when you're designing control panels. Next we have a transformer with a 13.2 kV line-to-line voltage. So you can see A, B, C is 13.2 kV, A to B. B to C is 13.2, and A to C is 13.2. If you look at that particular primary, that's like 3 pole transformers, individual single-phase transformers connected in a delta primary. You can see how it's connected in a delta. I don't know if you see that, but H1 of the first transformer goes to phase C. H2 and H1 are connected together, so B or A and C transformers are connected together, and you're connected to A phase, and then B phase is connected to H2 and H1 of the next two. So you have created a delta primary. The secondary side is connected in a Y, so you can see X1 is connected to phase A, X1 of the next one is connected to phase C, and then the next one is phase B. It's a natural thing that when you connect a delta Y transformer, you have a 30-degree displacement phase angle. So that means that if you looked at the A on the primary side of that transformer, you looked A to ground, and then you compared it on an oscilloscope to the secondary side, A to ground, the secondary side would be shifted 30 degrees with respect to phase A. So you need to understand that when you're doing protective relaying. On the secondary side, we have line to line is 480 volts. The square root of 3 divided by line, or 480 line to line voltage divided by square root of 3 is 277. So A to neutral is 277, B to neutral is 277, C to neutral is 277. If this was a European system, let's say 380 volt system divided by 1.732 is 220, right? So it's 219.8. So if this was a 380 volt secondary, line to line would be 380, and line to neutral, A to neutral would be 220. Actually, in European systems, we'd call that UVW, right? UVW and not ABC, but you get the idea. Next, here we have on the top, we have a single line diagram, right? We have a delta to Y transformer, and we have these CTs, right? These 200 to 5 CTs connected to a 50-51 and a 51/50 neutral. So we have the N is a residual ground relay, and it looks at the neutral connection. What we're showing you is a single line at the top, and then a 3-line diagram at the bottom. So you can see that you have, in this case, a phase A, B, and C, right? And then that A, B, and C is connected together, so each one goes to a 50-51 relay, phase relays, and looks at the phase current. That would be instantaneous and a long time current. And then the neutral wraps around and is connected to that 51/50 neutral, the residual current. It's optional that you would actually have a CT on the neutral line. Usually you would never see that. Here we're going to look at a single line at the very top. We have 208 volts AC, 3-phase, 60 hertz. We have a fused a disconnect switch connected to a contactor. Then you've got your overload relay connected to a 5 horsepower motor. There's a start-stop circuit. There's a red start stop, green green stop, and emergency stop push button. So that little one line shows a lot, and so you can see the power circuit. You've got your 208 60 hertz, 3-phase, goes to 3 disconnect switches, 3 fuses, then it goes to a control transformer. The M is your main contactor. Your overloads are the overload heaters. They call them heaters because they're bimetallic. Some are thermal compensated, some are not. It's a 5 horsepower, 3-phase motor. The only thing that they left off of this one is the grounds, and I encourage you to always show how the ground starts on the power circuit and how it connects on the 5 horsepower motor. So you don't want to leave out your ground. On the control circuit, we have the secondary side of that transformer, that control power transformer. They show the primary side up there, but then they show the secondary side here. Usually I connect those together. I would never separate those, but line and neutral here is 120 volts AC. They have a ground on that at the very bottom of it. You see that? That's actually required by UL 5088 to ground that control transformer secondary. And usually you ground it with a minimum 10 AWG wire size, which is really large, but that's the requirement. So here we have a control circuit. We have a normally closed stop, emergency stop button. We have the stop button. We have the start button. We have a latching in M contact off that main contactor. We have our M coil that pulls in the main contactor M, and then we have 3 phases of overloads. So the way it works is if you push the start button, assuming you've got power, and your stop and your emergency stop are not engaged, then the M will energize, and as long as there's no overloads, it'll energize. It closes and the motor starts. When the motor starts, the M auxiliary contact energizes, which latches across that start button, and you can release the start button and the motor will continue to run. The M will be closed and the red light will be lit. That means it's actually running, it started, and the 52B, if you will, if you call that a 52A on the normally open M contact and the normally closed is a 52B, it would be open because the motor started. If you hit the stop button, then it would release that latch and the motor would stop, and then that M contact would open and the normally closed M contact would close and the green light would light. So that is a complete motor control circuit right there. Shows you a 1 line and a 3 line. Not a bad little design right there, not a bad circuit. Here we have a schedule, a typical breaker schedule. So we have the circuit breaker identification, we have a main breaker, we have the breaker type, we have the breaker frame size, so we say that's AF, amp frame, 1600 amp frame. It is a 3-wire, it's got 1600 amp trip. So just because the breaker is 1600 amp frame, it could have a smaller amp trip. You can see that in the next breaker, the feeder number 1 breaker has got a 1200 amp trip. It's let's see, then you've got your long delay pickup time is 0.5 to 1.25 times. You've got your long delay time is 4 to 36 seconds. It gives you your instantaneous is none. It gives you your ground is 330 to 970 amps. Your ground T is 0.22 to 0.5 seconds. It says the conductor size is 500 kc mil, and it is 4 per phase, copper. So that's a typical breaker schedule. A lot of good information on there, and you should be able to set your, you could actually create, if you had all that information, you could do an ETAP study or an SKM study. So again, the LDPU is a long delay pickup. The LDT is a long delay time. The SDPU is a short delay pickup. The SDT is a short delay time, and the instantaneous is or INST is the instantaneous setting. And then you have your ground fault pickup or ground fault time. So from there you can create these I²T charts and curves, and you can perform coordination to make sure that if you had a fault on that feeder breaker, that it doesn't trip the main breaker, and that's what you'd be looking for there. Here we have an MCC schedule, Motor Control Center schedule, and it says in 1B, which is in section 1B, we have main lug only, main lugs, and they're suitable for 1 4-aught cable. It's a screw type phase lugs with phase cable entry. We have on the next one, section 1D is a feeder breaker, and we have an this particular breaker is 3-phase 20 amps. It's a HFD, so it's not a it's a breaker that is got the instantaneous and overload thermal setting. It's not just a magnetic circuit breaker protection or motor circuit protection. You can see down you got a return fan, so it has an HMCP, 3-phase 50 horsepower. So you want to watch out for that and make sure that everything is set. You've got your NEMA size here. You've got your CPT. So here you have a NEMA size starter of 2. You have a motor horsepower is 27 there. And I'm looking at return fan number 1. You got your breaker switch is HFD or HMCP. You've got poles is 3-pole breaker. You have your TM or trip clip is 50, and you got your MG range fuse size is 150 to 500. Going back to the other one there, you've got the NEMA size is 220, your 20 horsepower full load amps is 27. You've got your your heater is an FH51. Your CPT for that particular motor is a 100 VA CPT. A lot of good information right there, and that is a MCC schedule. This is a lighting panel board schedule, and here we have a 3-phase 208Y 120 volt system, 3-phase 4-wire lighting panel, 20 amp. So here we got your description of what it's feeding. You have on load A is 16 amps, load B is 16 amps, and load. So you can see the way this thing works out. If you have a line to neutral, it's circuit 1, and you can have dual breakers too. You can have 2 breakers or 3 breakers, so it depends on how you connect it. So you got, let's see if there's any of those that show all 3 phases. The load should be the same. Like that 6 duplex receptacles, rooms 1 and 2, you got 12 amps. Yeah, they just seem like they balanced them all and they put them all at 12 amps. Anyway, you sum up all the amps and then it gives you your total load phase. And the idea is that you would take the average value of these and you calculate your 208 times the square root of 3 times the amps, and then you'll get your 31.8 kVA. So that tells you the load on that panel, and you want to make sure it's balanced as well as you can anyway. So let's see if we take, it says here 89.8, 86.8, or 86.6 and 88.8. We'll take 88, we'll just take the highest one, 89.8 times 208 times the square root of 3 is 1.732 equals 32,350 divided by 1,000 is 32.35 kVA. So if we were to take that 89.8 plus 86.6 plus 88.8 equals divided by 3, we'd have an average of 88.4 times 208 times 1.732 equals, let me try it again, 89.8 plus 86.6 plus 88.8 equals 265.2 divided by 3 is 88.4 times 208 times 1.732 equals 31.84. So they have 31.8 kVA. So that's how they calculate that out. But they give you a nice little schedule. So if you're dealing with a lighting panel, that's what you need to do. Here you have a equipment at the terminal run. So you got, this is like a wiring, a typical conduit and wiring schedule. So you got from plant 454 to plant 82 sub 1. It's underground direct burial. It's got a type of wire which is 90 degrees C shielded. The operating voltage is 15 kV. Its circuit length is 3200. Its conductor size is 4 aught. It is number of conductors and cable, 3 conductor. It is copper as opposed to aluminum. It has parallel conductors per phase, 1. So they're not like 2 per phase or anything like that. And you got conduit type. So that is a conduit and wiring schedule. This is a switchgear. So this, you have a main tie main. So here we have an electrically operated main DS632. We've got a voltmeter, ammeter, and a selector switches at the top. We got that transition side where we have 2 loads and from source. EO is electrically operated, MO is manually operated. So we have 2 mains, and we've got some manually operated breakers, and then we have another electrically operated breaker. You can't really tell that it's a main tie main, but that's just a front elevation view of a switchgear. So this is what the 3-phase, this is what that switchgear would actually look like in a 1 line. So you have 40 volt Y to 77 volt transformer, source 1, and source 2 is also 480 volt Y to 77 volts. And you've got your 2 sources, your voltmeter sources. You've got an automatic throwover, so it's got the ability to switch from source 1 to source 2, and you've got your tie is normally open. It's 3200 amps, electrically operated. So here you can see that you could actually control this. You could keep both mains closed and your tie open, and depending on the types of loads there, if you had one of those sources go out and you had a fast transfer scheme like the SEL 421, you could actually quickly close the tie and open the other main and keep that system up and running, assuming that you had some motor loads and some of them were fairly large and they could withstand, keep that voltage up to a certain value. This is a motor control center. You can see that it's 90 inches tall. It's pretty typical. It's 20 inches wide. I think they come in 20 or 18 inches wide, about 20 or 18 inches in depth. You've got your vertical wireways and your horizontal wireways. Section 1B is a main lug only, so it takes up A and B. So at 1 meaning it's section 1, 2B is section 2. So you can see how they break those up. I believe those are each 6-inch sections. If you took the size and broke them all up, I believe they're each 6-inch sections. So that's what a US version of a motor control center looks like. Here we have a conduit risers. So let's say that we have a control panel. We'll call it P, and that P feeds is connected to MDP. So you have 4 500 kc mil and a 3.5 inch conduit. You want to make sure that the conductor sizes are figured out, the circular mills, the actual size, the area inside that conduit doesn't exceed 40% fill. You can see you go underground in the basement. This is just a typical conduit routing diagram. Here's a lighting or just a room. You've got different rooms here, and you've got lights, and it shows some switches and different diagrams here. This is a circuit wiring layout diagram. Some of this you don't really need to know if you're building a control panel, but it's always nice to know if you're reading somebody's control panel, diagrams, and they're trying to figure out how it interconnects to your control panel. Okay, so we have a common control circuit wiring. Here in the top left, you have a start-stop push button, and here you have a 2-position selector switch. And so this diagram right here gives you a nice little breakdown, shows you the actual wiring diagram, shows you the schematic, shows you the component layout. It's a fairly decent diagram. If you're building just motor control centers, this is really all you need to know. Everything is there. What I've done is I've included this PowerPoint in PDF format so that you can follow along. If you're watching this and you don't have that other PowerPoint or the PDF version of this, it might be a little hard to read. So make sure that you go on eBay and purchase the actual full copy of this, and so that you can follow along. When you get to a schematic that looks a little hard like this one to read, you can follow along with me and be able to zoom in on your computer. But that pretty much covers everything you would need to see in a motor control center, and including your remote control and your power and everything. But I think we've covered just about all of it. If we haven't, we're going to keep going. So when we talk about a conductor, we're talking about a wire. So the general symbol is just a straight line. If it's a temporary conductor, we do dashes. If you have 2 conductors, like in that lighting deal, you actually have 2 dashes. If it's 3 conductors, you can put 3. You might even put 2 lines in parallel. See how you have 2 conductors can be shown in a single line representation or a multi-line representation. Could be shown in a single representation if you had, let's say, N conductors, 15 conductors, or 8 conductors, you could show it that way. If you have twisted conductors or twisted pairs, then you can show it where they the signal like that, or you can actually show it where they twist. They actually jump from one side to the other side. When we have a cable, we generally denote that with a circle, this oblong-looking circle here. So if we have 8 conductors or 4 pair cables, we show these and we circle them all together, and we know that that's one multi-conductor cable. When you're connecting all your different schematics, if it just crosses with no connection, it just crosses the conductor, it doesn't actually have a dot, then you know it's not connected. Some people that's not enough for them, so they want you to jump over it. Just have a little jump over. If it is actually a junction and you'll see a dot, you might see a double junction or conductor. You might also see a little angle where it's alternative to use double junction. But the last three are all connected where the top one is not connected. A general symbol, terminal, or tag. So if it's a terminal, they might use a circle or a dark line. These symbols are used for contacts with removable links. The open circle is used to represent easily separable contacts, and a solid circle is used for those that are bolted. So here you have 13 is the top one, 14 is the next one, linked with two easily separated contacts. Here you have a link where you are actually bolted down, and here you have one that's easily separated and it's bolted on one side, so it's a hinged link, normally open. These are not the only way to show these. This is just one way to show them. These are different types of connectors. So you have a plug or male contact. You have a socket for a female contact. A coax plug would be the circle with a little tangent line coming off of it. Coax socket. So you can see the plug symbols on the coax plug, and the socket female connection is on the coax socket. For a general symbol, coil or winding, here you have a coil, which could be like an inductor. If it has a magnetic or a iron core, then it has that line over those little circles there, or the little arcs. If you're coiled with a ferromagnetic core, you have a CPT or a PT, potential transformer. You can see that they draw the multi-line ferromagnetic core, or one line through it. For a resistor, there's different ways of showing resistors. You can have just a square, rectangular box. The old symbol sometimes used, which I prefer. If you have a fixed resistor with a fixed tapping, you can have a little tap line coming off of it. If it's a variable resistor, like a potentiometer, you can adjust the resistivity. You can see they've got a little arrow on it. And the old alternative way is an arrow that's kind of at an angle. Variable resistor with a preset option is a line with a little line at the bottom. Sometimes you don't see these, too often, maybe in schematics or something like that, or PCBs, printed circuit boards. Two-terminal variable resistor rheostat. You have a resistor with a positive temperature coefficient, a PTC thermistor. Sometimes you see thermistors or PTC thermistors in motors that can be used to disconnect the motor if its internal winding its internal temperature of the stator gets too hot. You might want to disconnect that, especially in a hazardous area, because you don't want to get that motor too hot and cause the atmosphere in that area. If it's got an auto ignition temperature, some explosive gas out there, you don't want to get near that auto ignition temperature. You have a resistor with a negative temperature coefficient, NTC thermistor. Here we have capacitors, a general symbol for a capacitor. If you have a electrolytic capacitor or a polarized capacitor, you have a positive symbol on it. If you connect it backwards, it could blow up. So you want to make sure you're aware of that. Variable capacitor or preset capacitor. General symbols for fuses. Supply side may be indicated by a thick line. Observe orientation. That's an alternative symbol. It's the older symbol. I prefer a rectangle with lines at the end of it, similar to the supply side, but I don't actually, make it solid. Again, it's just all how you want to show it and all how your particular company shows it. Here we have different types of contacts. Remember when we talked about pilot switch or contacts? These could be like a relay or something like that. You have a brake contact or an alternative brake contact version. And there's version 1 and version 2. I think in IEC standards they use the top one, that brake contact, which is a normally closed contact. They say in IEC or British standards brake, we call it normally closed in America. A make contact would be a normally open for us, so you need to make sure you're aware of that. So here's a make contact. It's normally open, and probably the top one would be your IEC version. Your two middle ones, version 1 and version 2, would be, maybe an American or ANSI. You got changeover contacts. So certainly this would be like a relay. So you've got a Form C contact is what they would call that. You've got one normally closed, and when it energizes, it switches over to the other one. It switches over to the normally open contact. So that's how you would show that. Push buttons, you got break and make. A break would be like a normally close for like a stop push button, and make would be like a normally open or for like a start push button. You've got push buttons, a push on off latching. You also have lever switch, 2-position on off. Key operated switches, a limit switch for like a valve. You could have a limit switch so when you knew the valve was in the fully open position or in the fully closed position. So you got make and break limit switches, normally open and normally closed. You've got single diodes. A diode obviously is if you have a sine wave and you run it through that diode, you will get a positive portion of that sine wave out. So these are ways of rectifying AC signals so that you can get a DC signal out. A single phase bridge rectifier is on the bottom there. So there's different ways to show it. You can show it as one block where you have the AC coming in the two tops of it, and you've got your DC coming out. The positive is on the far left, the negative is on the far left. The positives on the far right, the negatives on the far left. And then you've got the 4-diode full bridge rectifier shown there as well. If you've got 3 phases, you can have a 3-phase Gantz bridge. Here you've got phase A, B, and C, L1, L2, L3, and you've got your secondary side of this would be DC, positive to negative. You got thyristors, SCRs. So a thyristor is like a diode. I really go into this a lot of detail in my variable frequency class. You can either watch that or you can go on eBay and buy it with the PowerPoint and all the supplementary information with it. So we go over thyristors and diodes and go over them in detail. But basically a SCR is it's a device where if there is no gate signal, then it's off or it's open. When the gate signal is energized with respect to the cathode, then it turns on. If it's a DC current flowing through there, even if the gate is removed, it stays on. And you have to either cause the potential between the anode and the cathode to be the same or reverse bias them. So in the bottom one you have a triac, a 2-way thyristor. And we use a triac when we have, it's just basically 2 SCRs back to back is what it is. You can be used for an induction lamp of like a dimmer switch. You see that a lot. Could also be used as a static switch. If you're showing DC current, you show one line. If you're showing alternating AC current, you show the sine wave. If you're rectifying but it's not a smooth signal, it's got a ripple on it, then you would show a line with a sine wave on that. Earth ground connection, chassis or frame ground connection. These are the way you would show this. Here's different types of cells, right? You've got a primary or secondary cell. You've got a battery of several cells, and you've got alternative symbol for battery is 2 with a dashed line between them. When we talk about different conductors or wires, we have a single strand conductor. It's solid. And you've got multi-stranded conductor. The PVC or different types of rubber or insulation values is called the insulation. It can be a single solid wire or made up of a number of thin wires. You've got a spool of wire, so there are several ways to describe the wire type. The most used method is to specify the number of strands in the conductor, the diameter of the strands, and the cross-sectional area of the conductor, then the insulation type. So example here we have 1 means it's a single conductor wire, It is 0.06 millimeter in diameter, and its insulation is PVC. So the conductor has a cross-sectional area nominally of 0.68 millimeters squared. That would be more of a British standard version of describing that cable. One of the things you want to be aware of is if you're building, I don't care if it's an IEC panel or if it's a UL508A panel, you make sure that you keep the documentation on all wiring that was used in that panel. Because if they challenge you, or if you have to prove your technical construction file, you need to have proof of how that wire and where it came from so that they can track it. Here we have a different version. We have 35 strands, so we have 0.25 millimeter is insulated with PVC. The conductor has a total cross-sectional area nominal of 1.5 millimeters squared. So see, you got standard wire gauge, which is SWG. So there's also American wire gauge, which we use. So 14 SWG is 2 millimeter. 30 SWG is 0.025 millimeter. 30 SWG is very, very small. Usually we don't use anything less than about 20, 22. Coax cable, so an insulated central conductor surrounded by an outer tubular conductor. An outer conductor which is usually braided, woven, and given cable flexibility, insulation between the two conductors. So these are different types of cables that you can use. A coax cable is primarily used for cable television or high frequencies signal currents. A screened wire, in IEC terminology or in British standards, they call it screened. In America, we call it braided or shielded, right? So if you have a screened wire for a 4 to 20 milliamp signal, you want to shield or take this screen and you want to shield it only on one side. Take the other side, the other screen side, and tape it off and insulate it so that it doesn't touch anything. If you don't do that, you can have circulating grounds and cause all kinds of interrupting problems. You'll use screen conductors or shielded conductors in instrumentation, especially when you're dealing with PLCs. So you're trying to mitigate any low level signals. Could be could have interference generated by current carrying cables that have high power flowing through them. So if you've got a 480 volt phase A and B and C current coming down one conductor, it has a large magnetic field built around phase A. Well, you don't want that large magnetic field to be coupled onto this instrumentation wire because it only has 4 to 20 milliamps, maybe 24 volt DC. And that magnetic field, if it crosses or is in parallel with this conductor, will induce a voltage into this instrumentation signal. So when you take and ground one end of that screen or that shield and you insulate the other end, it takes that interference, that magnetic field, to ground, and it doesn't cause a problem with your instrumentation, so you don't have error. So you could have a multi-way or multi-conductor cable. So here you have a conductor, an outer sheath with individual insulated wires. You could have multi-conductors with shields or sheaths or a braided screen. Just treat it like it's a individual conductor or two pair, and ground one side of the screen or the shield and leave the other side ungrounded. Make sure you understand how to remove the insulation from these conductors. You don't want to nick the insulation where it shouldn't be nicked, and you don't want to remove some of the copper because you can accidentally cut into that and remove some of those strands and decrease the cable's ability to carry the full conductor current. This is a wire remover, right? And you have different methods. Here you can have a terminal block that if you slide it into it, it actually clamps down on it. Where you would see these primarily are on areas with high vibration like gensets or motor gensets, and you want to make sure that these terminals don't come loose. If you have bolted down connections, the bolted terminal blocks can come loose, where if it's a spring connection, it'll always keep pressure on that wire, and that's the only time I really like to use them. A lot of people like to use them because they can build them real fast, but I'm not a real big fan of it. If you have a joint where you want to solder to it, I believe UL 508A says you have to have a minimum of 180 degrees around that point, and then you can solder it. Certainly you could go 350 degrees, that's even a better connection, but a minimum of 180. You've got different types of lugs, an eyelet, a fork or spade, a receptacle, or a slide-on, and then the blade. If you've got a current signal, that eyelet, we call them ring lugs in America. So if you have a current, on that CTs we were looking at earlier, 100 to 5, on the secondary side, make sure you use ring lugs, right? Because if that CT circuit becomes an open circuit, it could cause that CT to blow up, right? It could actually explode. So you want to be real careful about that. I didn't actually personally see it. I just happened to be in the same switchgear room when it happened. Somebody actually cut a conductor that had a live CT circuit on it, and what it did was it acted like a taser gun, right? And it actually shocked him and knocked him into another guy. So you want to be real careful about that. You have different ferrules. These are actual shrouded ferrules. You have insulated ferrules and non-insulated ferrules. These are kind of nice because you can have a multi-stranded wire, slide it over there and pinch it, and it becomes like a solid wire, and it slides in real easily, and it's easy to crimp down. So ferrules are kind of nice. A general rule is to not put more than 2 or more conductors in one terminal. So don't put 3 or 4 type terminals in one terminal block. Just put 2 or 1. And you definitely don't want to force them. So make sure you understand the UL rules for that terminal block, and make sure you understand what size conductors they can handle, and never put more than 2 in there. So here you can add an additional terminal block if you need to add that additional wire. So in that previous example, we had 3 on terminal block 1 at the top of it. So what they've done is added another terminal block, still called it number 1, connected a little jumper on the bottom side of it, and then put that 1 wire on the top of the added terminal block. Some of these terminal blocks you can actually link them together with a bus bar from the manufacturer, which is really nice, and you can link 5, 6 of them together, and so that whole string of terminal blocks could be all terminal block 1. That's kind of a nice deal. So again, they've complied with the rule that it not be more than 2 wires connected to 1 terminal block. If it's a field terminal on the bottom, you don't want to put that little jumper like that. You want to put the little jumper across underneath the ones. You can actually put a block in there, and then you can still put the 1 designator on there. You definitely don't want to crisscross like this, right? So you don't want to jump out of number 4 and jump to the top of number 6. Although it's the easiest way to do it, you don't want to do it because it just looks ugly and it hides numbers, and it's just not professional. What you want to do is jump back into that wireway, run all the way back around, and then stick connected to 6. That's the proper way to do it, not to jump across a terminal block like that. Flexible conduits or cables shall be installed in such a way that liquids can drain from the fitting and termination. So here you have you always want to connect to the bottom side of the control panel, never connect to the top, because water will invariably run down the conduit and into the control panel. When you do come out the bottom, you want to put a low point drain. So a lot of people don't do that, but you should put a low point drain. So whenever you're at the lowest point, put a little drain, and if you do get water in there from condensation, then it'll drip out there. If you have that flexible conduit, you want to make sure that you go into the bottom of that motor there. Electromagnetic field. We talked about this, where here we have a main contactor. They happen to have two phases, if you will. Could be a 220 volt AC motor. Let's say they got 15 amps. There's a large amount of current flowing through there. Maybe 20 amps, doesn't matter. It has a large magnetic field. If that large magnetic field is in parallel, if those wires, those low sensors power wires, are in parallel with that large power wire at the top, the main contactor of AC motors, that AC magnetic field will be induced into that low power sensor cable and will mess up your signal and cause erroneous errors and maybe trips or something like that. It's real hard to troubleshoot things like that. So you want to avoid that. The way you want to avoid it is to run it in different conduits, and you also want to maybe put a shield on all PLC signals that are critical like that. You know, according to UL 508A, as long as the installation is all rated for 600 volt AC, you can put it all together. Well, again, UL 508A doesn't care if it functions properly. So just because it's okay to put it in there per UL 508A doesn't mean it's the proper thing to do. So here we have another example. We have electromagnetic field trapped in the conduit. So we have this rigid metal conduit, and it is grounded, and so it traps it. That's one way to do it. Put it into separate conduits and then ground the conduit. You could also put it in separate conduits, and you could take it a step further and put the low power sensors in shielded cables or screen cables, and then you can guarantee you're not going to get any noise or issues like that. DIN rail, we haven't really talked about DIN rail, but those components that were mounted in those pictures, those control panel pictures, are usually mounted on DIN rail. You want to make sure that your components, and you understand that all the components are designed for certain DIN rail. So make sure when you're specifying a relay, like in this example, that it can connect to that DIN rail, that particular type of like TS35 DIN rail. So you can see there's numerous different types of DIN rail, and they don't all work together. So you want to make sure that you always specify the right one. We talked about this panduit or wire duct. Again, what you want to do is you want to maintain about 2 inches between your component and the wire duct so that you can have clear ways. I know some of these women that wire a lot of these panels have small hands and small fingers, and they can really get in there and wire some small stuff, but a big guy, you know, electrician or an operator out there in the field might not be able to work with that. So you want to make sure you give them ample room. Nothing in the UL 508A code says they have to do it that way. It's just good practice when you're building it. Here you have the fill, right? So you have your lid and the panduit, and pretty much what you want to do is maintain about 50% fill, no more than about 50% fill in that panduit. And the top, so you can see how they're wired. If the device comes out and it's significantly taller than that panduit, then you can get a little closer. But if it's not, you want to make sure you have about 2 inches in between the side of that panduit and the side of that component. Sometimes panduit looks a little too full. Put your thumb on it and press down. If you press down on that wire and you see 50% fill, that's about right. That's a good rule of thumb. You can also just calculate what your percent fill is, just like you would do on a conduit fill calculation. Here's a terminal block. So you've got an individual terminal block, and you need to make sure that you specify each terminal block and the end caps, right? The actual caps that fit on the end of it. You need to make sure that you specify it for the right DIN rail. You want to make sure that you specify the right voltage. You want to make sure it's UL listed. You want to make sure that if you have to interconnect some of these, that you have the right bus bars. Here's a relay, like an ice cube relay. So you have the coil where you would energize it. On the coil, if you energized it, you build up a magnetic field, and it would cause that iron core to become like a magnet, and that armature at the top would pull in and it'd connect. When it pulled in, it would cause those contacts to change from the common to the normally open. If you release the voltage, it would change it from the contact would release and the spring would pull it back, and you would have contact between your common and your normally closed. So that's exactly how a relay works, a electromagnetic relay, not a solid state relay, electromagnetic. And so if you had like one of those ice cube relays, that's what it would do. That's how it would actually function. You can actually look inside that ice cube relay and see it function like this. Here's a larger relay, like a motor starter or something. So you have your fixed contacts, you've got your moving contacts. Your fixed contacts is where your wire, your line and load side or terminal side would connect to. Whenever the coil is energized, that's the part of the moving armature would slam close to the fixed armature, and it would pull the top contacts, the moving contacts, in contact with the fixed contacts, and you would start your motor. So this is a large NEMA starter. Even an IEC starter would work like this. But that gives you an idea of how it works. So you can see things that could cause trouble here is low coil voltage, right? If your CPT voltage is too low, it might not have enough force to pull it in, and you could have chattering, or you could have things dropping out at the inappropriate times. The contacts could have arcing, and they could fail after some given amount of time. So that's kind of a nice little picture of how something like that works. You want to make sure that whenever you're specifying a relay or a pilot device switch or anything like that, that you understand the AC loads. If it's a purely resistive load, this is the least severe condition, like a space heater, like a little motor space heater, would be an AC1 load. If it's a slip ring motor control switching, you would want to use AC2. If it's a squirrel cage motor, like an induction motor, and you're starting and braking during normal running current, then it's an AC3 load. AC4 as for AC3, but with higher operating frequency. If you're starting and stopping that motor all the time, you want to use an AC4. This is the most severe condition. Certainly you could just use AC4 for everything, and you'd probably be in good shape. You might be wasting a lot of money, but you would probably improve the quality of your control panels. For the DC loads, you have DC1, DC2, DC3, and DC4, and DC5. DC1, again, is resistive loads. DC2 is starting and stopping shunt motors. DC3 is the same as the DC2, but allowing inching and plug-in control. So if you've got a starting and stopping shunt motor, but you kind of jog it, you start, stop it, you're moving the motor slowly, and like a jog, or you allow it to kind of increase by slow intervals. DC4 is starting and stopping series motors, and the DC5 is the same as the DC4, but again it allows that inching or plugging control function for more severe conditions. So again, if you have a DC5 everything and an AC4, you're pretty much covered, but you might be oversized and everything. General symbol for a relay. It's really an IEC symbol. If you have a slow to release relay, it's got the solid end on it. If you have a slow to operate relay, it's got the little square on the end, or rectangle on the end of it with a X through it. A polarized relay, a mechanically latched relay. And then you've got different symbols here. So you've got your make contact, or normally open, break contact, or normally closed, and then you got your changeover, make before break, or form C contacts. Changeover, make before break, make after delay, and a break after delay. We've kind of talked about these already. Here's a ice cube type relay. It's in a socket. You can see it's a round socket. It's 1, 2, 3, 4, 5, 6, 7, 8. An 8-pin socket. You've got the little key where you slide it in the right direction. You've got your bottom two, which is A1, A2, is your coil. That's where you'd apply your voltage. Your K1, K2, K3, and K4 contacts. So you can see how that actually works, and you want to make sure you specify the right socket for the right relay. There's an example of that ice cube relay and a socket, pin type socket. You can also have a blade type socket, right? So here's a relay sockets and the panel wiring connection for that terminal block. Make sure again that the DIN rail is specified properly, and the voltage is the right one, and you've got the right type of load, relay for the load. So if it's a heavy duty AC motor, you're starting and stopping it all the time, You want to make sure it's AC4 related. Here's a heavier duty motor starter, and you can assemble these, right? You can add on different modules and you get different signals on the top of it, and you can change it so you got your main contacts at the bottom for your main power in and out, and then you can add some smaller ones on the top of it, and some auxiliary contacts as well. So the dotted line shows that contacts are mechanically linked. So here you have 2 normally open and 2 normally closed. So 13 to 14 is normally open, 23 to 24 is normally open, 31 to 32 is normally closed, and so is 41 to 42. Here you have a panduit on the top, the wireway. The contactor is actually bolted to the chassis, could be connected on a DIN rail, and you've got 2 side by side. Here you've got a pin connector to the contactor. You've got your overload adjustments for your motor. So, and then the contactor is the line side connects to 1, 3, and 5, and the terminal side would connect to your overload unit, which would connect to the motor 2, 4, and 6. The pins would slide up into the contactor 2, 4, and 6, and you tighten those up. The 13 to 14 to 97 is your overload settings, right? So you would actually see that, and you'd go 13 to 97 or 13 to 14, and whenever you had an overload, you could trip and you could say, hey, I have an overload. So here's a main connection, 1 to 2, 3 to 4, 5 to 6, and the thermal overload is 97, 98. So the normally open is 97, 98, the normally closed is 95 to 96. So whenever you would wire this into a circuit, you would put that 95, 96 in series, right? So that whenever you had a overload condition, it would open up your control circuit. So it would open up your main contactor coil. Here you have a solid core, right? Usually metallic, usually thin metal plates laminated together, and you've got some windings on the primary side, you've got windings on the secondary side, you've created a CPT, a control power transformer. Usually you don't see them as a straight bar, you see them in more of like an E, right? And they sandwich together and you've got a complete magnetic field, but this gives you the basic idea. So you get 415 volt AC on the input, you will see 24 volt AC on the secondary side. Here's your general coil symbols, and your symbols are, if you have the line through it, you've got a magnetic coil. Here's your transformer. Again, your primary is your input, your secondary is your output. You could reverse this. Transformers are kind of dumb as long as you don't exceed their amp rating and their voltage rating. You can also have circles. If you have 2 circles, that's an alternative way of looking at it. It's for a block diagram and an IC diagram. You can have multiple primaries and multiple secondaries. Here we have a single primary with 2 secondaries. You can have 2 primaries with 1 secondary. You can have taps. You can change the taps so that if you know your incoming voltage is always low, then you can adjust your taps so that the secondary voltage is higher. There's different types of CPTs or control power transformers. You've got one that is a shielded or encased type on the right hand side. And here you would actually bolt it to your back pan or your chassis, right? Here's a toroid. It's a transformer, so you would run your primary conductor through the donut, and you would get some secondary current on the secondary side of this. So let's say if this was 100 to 5, you would have 100 amps flowing through that wire, the main wire that's running through the donut, and then you could measure on the secondary side 5 amps. That would be a CT, control or current transformer. Here you have fuses. So here you have a fuse that is a nice cutaway version of it. It's filled with like a sand. And basically what happens is if you have too much current through there, it actually burns it, right? So it burns it open. And again, these are your general symbols for fuses on the left. And here we have a glass type fuse, a removable fuse cartridge on the right. If you have a glass fuse, remember that's a supplementary protection. That's UL 1077, not used for branch circuit protection. And here's another type of fuse, right, with your fuse holder. This would be a larger fuse, cartridge and holder, so this could be one of those heavier duty fuses that could be suitable for branch circuit protection. Here's some different type fuses. You got an A4, A3, A2, and A1 size. Here's a resistor, or a large wire wound resistor. And you've got your little symbols, your old-fashioned symbol, and you've got three resistors on a terminal board. Here we have a heavier duty, this is a metal case on a resistor. You have some compound so that you can transfer the heat to the back pan. This is more of a heavier duty power resistor. This back pan can act as a heat sink, or you can actually mount it to a heat sink where it allows the heat to be dissipated off the resistor into the metal. Here you have a variac, if you will. Not a variac, but a variable resistor. So you have a wiper. The part you spin around here, it moves back and forth on this removable wiper, and you can vary the resistance. Here you have your different panel controls and preset type of resistors. We already talked about those. Here's another panel mounted control potentiometer. Could be mounted on the door, a small printed circuit board pot or a trim pot, which is a potentiometer. You could have a linear wound high wattage preset resistor with a wiper clamp. So here you could adjust it and then you could change the resistance. Here's a link with a wiper connected to one end, so you can actually have it as connected as a pot, as a 2-wire variable resistor. You could sit there and change it. Fixed resistors, there's a 4-band color code. So if you're looking at the color, the first digit, let's just say it equals brown. So you'd have a 1. The second digit is let's say it's red, so a brown red, so we could have a 12. And the multiplier, let's just say that it's a orange, it's times 1,000. So that would be a 12K resistor, 12,000 ohms. The last value is your tolerance, right? So you got your, if it's a gold, then it's plus or minus 5% tolerance. So that means it's 12,000 times 0.95 for your low value, or 12,000 times 0.105 for the high value. So that would give you how you would read a resistor. Here's another example. I just let it sit here for a second and you can take a look at it. You got your A is your first digit. Here it's red, so it's a 2. Second digit is violet, so it's 7. Third digit C is brown, so it's times 10. So we would have a 270 ohm resistor. It's got a red tolerance, so it's plus or minus 10%. So it's a 270 ohm plus or minus 10%. And that's how you would read that. Certainly there's other versions of this. You can get a 270 R5% WW wire wound. So sometimes they're actually written on there. So the 270 means it's 270 ohms. It has a tolerance of 5%. And it's WW wire wound. There's also a 5-band code where you have your first digit, second digit, third digit multiplier plus your tolerance. The 6th digit can be 200 parts per million in degrees C. So you can play with that all you want. You can take a look at that and you'll run into all kinds of different resistors. Usually on a control panel you don't see a lot of these unless you're putting in PC boards, printed circuit boards. One of the courses that I've thought about putting together is how to design printed circuit boards for different applications and go over some analog as well as digital circuits. I haven't totally thought about that one yet. I might do it, or maybe not. Capacitors, you have your symbols, your schematic symbols off to the left, and on the right hand side you have what it physically looks like, right? So the top one is a big large electrolytic capacitor. It's polarized for DC applications. And then you have some other smaller capacitors there. You can see the little can type electrolytic caps, and then PC board type caps. Here we have a switch, a toggle switch, and also a panel-mounted push-button switch. Usually in modern control panels, UL508 control panels, you could use a small little switch like this, but I usually like to use those 22mm or 30mm larger Allen Bradley or Siemens type or Square D type switches, Schneider. Here you have a key type actuated switch or a lever switch or a push button switch. You want to make sure that you buy all the components, right? You've got the actual switch, the actuator part of it. Is it a push button or a lever or a key operated actuator? Then you got your adapter, and then you got your contact element. So you can snap the contacts together, and you can assemble these switches, or you can order them all together. You can add contacts as well. Just make sure that you order the right contact element for the load. Here you have a test off-on, a 3-position switch. Doesn't have to be labeled test. It could be anything you wanted it to, but again, you have the 3-position switch. You've got your different components that you'll need to order. Here you have a contact element. So you have 3, like a form C, or normally open, normally closed. You could have, remember we looked at those amp meter switch or voltmeter switches? So here would be an example of one of those switches where you would go off phase 1, phase 2, phase 3 if you wanted. So that would be an example of a selector switch. Here's different types of lamps. I like the LED push-to-test lamp myself, 22mm or 30mm. You could also have a neon lamp or an incandescent lamp. You've got your lens, you've got your panel, you've got the thickness of the panel, you've got the transformer module, or you've got the low voltage lamp holders, and then you've got the different types of lamps. Again, I like the LED where they go from 20, or I think it's like 20 to 130 volt AC or DC, and I like the push to test because it's easier for the operator to work with. Here we have a transformer with proper grounding to the neutral. So here you have your primary side, delta. You've got your secondary side as a Y. It's solidly grounded to earth. The neutral is earth, and you have L1, L2, and L3. Here we have a 415 volt AC European system, probably 50 hertz. Line to neutral is 240 volt AC, and it's solidly grounded. When we have an earth symbol or a terminal block, you can have a green-yellow one that is actually marked PE, so it's actually connected to the DIN rail and provides a source for earth. So here you have your L1, L2, L3 neutral and your earth, PE. You can also have a bus bar, right, an earth bus bar, and connect it that way as well. Want to make sure that you use the proper bolts when you're connecting to a bus bar, or to, if you want to ground your door, right? If you have a welded stud on that door, which you should, you want to ground around the welded stud the hinges to the back panel. That way you're not relying on the back panel hinges or the door hinges to transmit a fault if there's a 120 volt AC on that door. Just as a general rule, when you're building control panels, you never want to put anything higher than 120 volt AC to ground on your door. Don't put 480 or 415 or anything like that. That's just an accident waiting to happen because that door swings open and closed. Make sure it's no higher than 120 volt AC. So this is different examples. So here they have a scrape, they have a bolt, stud welded to the inside of that panel. You can see the hinge, and then you'd have the same thing on your door as well, and you'd want to connect these together to make sure that you're not carrying the current through your hinge. Here's an example of either you can connect individual conductors to ground, or you can connect them through a bus bar to ground. Here's that example where you take the inside of the control panel and you connect it to the door, right? So you're not relying on that ground to go through the door. You actually connect them. A lot of times I'll go out to switchgear and MCCs and different things like that, and they're missing this ground. And I know that it used to not be the requirement, but it's really the right thing to do. It doesn't have to be a little hinge. It could be a wire running through one of those a wire loom or something as part of the overall wiring circuits. Just make sure you have a ground connected there. Here you have a PLC, programmable logic controller, a small little micrologics looking version on the left, a larger one with a rack where you have plug-in modules. When you're dealing with UL5088 control panels or different industrial control panels, almost all of them have some type of a programmable device like a PLC in them. So you need to be aware of type of PLCs and how to wire to them and things like that. I do have PLC courses if you want to learn how to program them. You can look on eBay courses that I offer, and there's mainly Allen Bradley stuff I put on there. Here we have the wireway, the PLC wireway. You've got the power wiring. So what you want to do is you want to separate this. So these wireways shouldn't all be the same. You got your power on your left, and then if you have to go to the right, you run through the power wiring. If it's PLC related, you keep it off to the right-hand side of this device so that you're keeping your power and your PLC separate. That's the proper way to do that. It's a well-designed panel. And you can see at the bottom left they have that PE coming in the bottom, that earth signal. So, in addition, the previous panel showed us good proper separation, but you also want to make sure you have a minimum of 100 millimeters between the PLC and the door, right? And the door components, so that you have proper air, space so that you can dissipate the heat. When you're connecting two PLCs together, you can connect their grounds together, daisy chaining them. Continuing on with different components, you have the PLC. I started mentioning PLC, so I might as well go into a little bit more detail. The PLC is a programmable logic controller. It is an industrial hardened computer with isolated I/O. So on the left here you have switches, push buttons, leak detection inputs. Inside the PLC you have a CPU, a central processing unit, where the PLC code resides and decides what to do with the input. So it decides, should I turn a motor on or something like that. On the output you have lamps, relays, motor starters. So if you want to know how to program a PLC, you need to learn a different, first you got to pick the PLC you want to use. Is it a Siemens PLC, an Allen Bradley PLC, a GE PLC? Once you understand that, you have to understand how that software works. I have put together courses for you that are primarily Allen Bradley related PLC courses. So here we have an input, a DC input. You can see that input number 3 is energized. See how it's lit up? So the photo sensor is connected to input 3, and whenever a package crosses it, 3 turns on, and then you can decide what to do with that information. You want to make sure that that photo sensor connected wire is shielded from all other power wires, because you certainly don't want an intermittent magnetic field that cause troubles with that. So each physical device on a machine or a process line is connected to a terminal representing an I/O point on the module. So here's a rack, a PLC rack. This happens to be a Control Logics PLC. On the far left you have power supply. Then you have your input modules. Next you have your Control Logics controllers. It shows 5555 controllers. That's a real old controller. You have 66,000 series now. I think maybe even 7,000 series, I can't remember. Then you also have your output modules and your chassis there. So the unique thing about this particular processor is you can put those controllers, the CPUs, anywhere in the rack, whereas you could put only on a slick series, you can only put it in the far left. A lot of modules don't allow you this open access where you can drop those CPUs wherever you want. Might be a good thing, you might want to have all your inputs on the left and all your outputs on the far right. Maybe that's an easier way for you to wire your panel. Just whoever programs the PLC needs to know exactly where these cards are, and you can't move them around on them. Typical digital devices include your input devices could be push buttons, selector switches, or limit switches. Your output devices could be solenoids or motor starters. You have commonly shared devices. You have input modules, your controllers, and your output modules. So the control logics architecture provides a wide range of input and output modules to span many applications from high-speed digital to process control. The control logics architecture uses producer-consumer technology, which allows input information and output status to be shared among multiple control logic controllers. So you can have one controller sharing information with a lot of different controllers. And this isn't really exclusive to control logics or Allen Bradley. It could be a Siemens PLC. In this particular module, they have the 1756 digital I/O modules. You want to make sure you pick the right I/O module for the right application. For instance, the IB16 or the IB32 is a digital DC input card. It has 16 points, so the IB16 is a 24-volt DC 16-put input card. So you could also have a digital output card, which would be an OB16, or an OW is a relay version, an OW16. So there's a lot of different types of cards. Here you have your discrete cards, an IA8D, or an IA16, or an IA16I, which is isolated. There's just different varying types here that you need to consider, and you need to understand them all. And as you're going through your PLC control panel assembly, you need to ensure that you've got the right module for the right application and that you've got proper shielding on all these signals. Certainly for an analog signal, let's say that you have a analog card and you got a 0 to 5 volt DC signal. So the 0 to 5 volt DC represents 0 to 100%, or it could be 4 to 20 milliamps. It could be 4 milliamps on the bottom left represents 0%, 20 milliamps on the far right represents 100%. Different analog cards are an IF16, which is a 16 input card. You've got IF8s, or there's different types of cards for different types of analog signals. So those were inputs, and you also have analog outputs. You can control valves or linear signals or PLC, or let's say if you had a VFD and you wanted to control how fast the pump is moving, you can control the speed output based on a process input signal. Of course, you really don't need a PLC for that because some of these VFDs are very intelligent and already have these controls, but you could have an analog signal output of, let's say, 4 to 20 milliamp signal output to control a control valve. And control logics PLCs or Allen Bradleys, they have different colors. So you have red is an 8-point, in this particular example, it's an AC input. It's an 8-point input module. You have a DC, you've got the green one, it's a 16-point output module. And you also have the blue one, which is DC, it's a 32-point. So you can see the different, you can see the ST or the fault condition, right? So 0, 1, 2, 3, 4, 5, 6, 7, this is an 8-point input module with diagnostic capability. So it can tell you if there's a problem with that input. Fairly decent modules. It's a good rugged PLC. It's been around for a long time. Here you have a orange card, an AC output card. So this is a 16-point card. You've got 0 is the first input, all the way to 15 is the last input. And it gives you the card status as well. It's also got fusing, so you got your fuse inputs as well. If you have a diagnostic card, you'll have a D at the end of the module. If you have an electronic fusing on that module, you'll have an E. If you have individually isolated inputs or outputs, you'll have an I at the end of the module. So here we have a DC output card, 16 points with electronic fusing. So it's a 1756 OB16E, so it's 16. OB is output card, and it's got electronic fusing. We have a DC input card. It's an IB16D. The D is diagnostic. It's a DC input, 16-point with diagnostics. Each individual I/O module also has status indicators on the front of the module to monitor the module's condition and operating status. So you got status points and also fault diagnostic points. A red I/O fused LED on the electronically fused output module means a short or overload fault has occurred for a point or a group point or a point in a group. Right. So if you see different colors on these fuse, it indicates different situations. An amber I/O state LED on an input or output module means the point is energized. A red I/O fault LED on a diagnostic input or output module means the field side fault has occurred for this point. A lot of good information. You don't even need to know how to program it. You can just read the card's status and the color of the LEDs and quickly tell if it's wired right or not, or if it has troubles. One of the nice things is these cards, these PLC cards have removable terminal blocks, and then you can snap in pre-wired terminal, pre-wired terminal blocks, which is a really nice thing. These are pretty heavy-duty, thick cables, so you want to make sure you got plenty of room. But boy, it's simple to wire. So if you've got 32 input cards, that's a lot of wiring. You can cut that wiring down to, an hour or less to build the whole panel, because you snap and play. If it's all laid out, it'll take you less than 15 minutes to build a panel. So here's a cutaway or a little view of it here, and you can see the removable terminal block. You can either manually wire every one of these inputs, or you can buy a wiring system. So here's a wiring system where you've got the individual wires, you've got the I/O module, and they snap together, and then this interface module snaps on the DIN rail, and you're done. It's a simple application. And here's an example of an I/O module to an IFM. Different types of AIFM I/O modules, ready cables, ready to go. The other end of the individually color-coded conductors that connects to the standard terminal block. So you don't even have to wire these, are all pre-wired. This is what a modular rack looks like, or a chassis. Chassis are available in 4, 7, 10, 13, and 17 module slots, pretty wide. You want to make sure when you buy one of these slots or these racks that you give ample space around this rack, and that you size that power supply correctly, because if the power supply is undersized, then it won't function correctly. So when you mount a chassis in an enclosure, meet these minimum spacing requirements. Make sure you have 6 inches above it, 4 inches to the left, 6 inches below it. That's actually 6 to 8 inches below it. So if you've got 2 racks in there, or multiple racks, you need to separate them properly. So you want to make sure that you allow this extra space to allow heat to, properly circulate. There's different types of power supplies. So that control power supply, that PLC power supply, actually provides 1.2 volts, 3.3 volts, 5 volts, and 24 volt EC on that backplane. There's different standards. You got your PA72, PB72, PA75, PB75, PC75, PH75, and then you also have redundant type power supplies. So you get your power supply on your left, and your input modules again. So that's pretty much all we're going to talk about on PLCs. I just wanted to introduce the concept, and most importantly, the actual components that you would see when you do run into a PLC, and the required spacing. That's the key, is the required spacing. Again, if you want to learn more about PLCs and you want to learn how to program them, certainly go to my eBay site, and you can buy some of those training programs that I offer, and you'll learn how to program them as well as install them in your control panels. I think we already talked about this slide. It's just different symbology, single one-line verbiage, but I think you pretty much have seen them all, and hopefully you got it and understand this. We'll talk a little bit more about components, and you might be thinking, wow, this is about UL 508A. It is, because again, I like to go over the actual components before we go into all the details about the procedures, because if I just talked solely about the procedures, you'd get bored real quick if you haven't already. So here, let's talk about this. When you're dealing with meters, or what we'll talk about is more components: panel meters, fuses, switches, switch disconnector fuses, circuit breakers, power and control contactors, timers, relays, and accessories. And basically what we're going to talk about here is we're just going to solely talk about theory, right? So we're going to look at the control diagram, see how they're wired up, see some of the main things that have to be wired up to them. We're not going to get into the calculations here, we're just going to get into what needs to be hooked up to certain situations. So here we'll talk about panel meters, we'll talk about amp meters, voltmeters, frequency meters, kilowatt meters, power factor meters, and then energy meters. An amp meter is a device that measures or displays the current, the AC current or DC current. It connects to a CT on a current transformer on an AC circuit. So analog amp meters work based on the principle of a moving iron instrument, AC or DC, and a moving coil instrument for DC. Amp meters are either analog or digital. So here we have an amp meter connection. We have on the left, you have your A, B, C, R, Y, B, N is neutral. So the red CT is your R or A phase. You got your yellow B phase and blue C phase. You have a shorting block is to the right of it. What you want to do is you want to use ring lugs like we had talked about before. You want to use number 10 gauge wire on all CT circuits. You want to wire to a shorting block, which is what that symbol is, the little circles there that are connecting in it, and it connects it into a Y configuration. And then you want to always ground your neutral on these. So you want to create a ground. Certainly there are situations where you want a delta connected CT, but if you have a Y connected CT, always ground it. So then you have your amp selector switch there, so you've got phase A, B, and C, and your neutral connected to it. Coming out of your amp meter selector switch is one leg that goes to the amp meter, and then you've got your neutral connected back. So if you put it on phase A, it'll read phase A current. If you put it on phase B, it'll read phase B current. If you put it on phase C, it'll read phase C current. That's pretty much all there is to an amp meter. Voltmeters measures the voltage across the connected equipment. You can have analog meters or you can have digital meters. On a voltmeter, you could measure line to line like they're showing here. Not a good idea unless it's less than 120 volt AC line to ground, because you don't want that voltmeter on the door if it's 415 or something like that. If it is 415 three-phase power or 480, make sure you use a PT, a power transformer, to step that voltage down. Maybe that line-to-line voltage is high, like 15 kV or something like that. All you need is A, B, and C coming in, connected to a fuse or a terminal block there. I would fuse it myself, and then go to a selector switch, and you got your voltmeter on the secondary side of it. Frequency meter, all you need is really line and neutral on this, because all you're looking for is one phase of it. So it measures the frequency, the hertz. Is it 50 hertz or is it 60 hertz? You can have digital or analog frequency meters. So here we have phase A to neutral. You've got your fuse, your neutral link. What is a neutral link? A neutral link looks like a fuse, but it's really just a solid copper bar. And then you've got you're just looking at A to neutral here, and it'll measure 50 or 60 hertz. Kilowatt meter. Remember, kilowatts is volts times amps times the square root of 3 divided by 1,000. So if it's volts times amps, what do you need? You need your voltage and you need your current. And then you can calculate your kilowatts. Oh, I guess I said that wrong actually. It's volts times amps times power factor times the square root of 3 divided by 1,000. kVA would be volts times amps times the square root of 3. Sorry about that. So in a kilowatt meter, they need to know what the power factor is. So it measures the power consumed by the load or delivered by the source. If it's a 10 horsepower motor, we know that 0.746 kilowatts is equivalent to 1 horsepower, so it's 7.46 kilowatts is what we should see if it's running at full load. It can be an analog or digital motor. Again, you've got your current and you got your voltage inputs. Just watch out for this, because this kind of gives you the false impression that you can just run that voltage directly onto the door with that kilowatt meter. I do not recommend that. I recommend that you run into a PT first. So you got phase A, B, C on the bottom, your fuses with your neutral link goes to your kilowatt hour meter. Then you got your phase currents. You got A, B, and C phase currents going into your kilowatt meter. And what the power factor is the power factor is the phase angle difference between the current and the voltage. So if you have unity power factor or 1, then phase A current is in phase with phase A voltage. If they're displaced by 30 degrees, then you would have a 30-degree phase angle. So if you took the inverse cosine of 30, you'd have 80 or 0.8. So that would be an 80% power factor. Power factor meter. You can have a separate power factor meter, but if you have a kVA meter, or you know your amps and your volts, and you know your kilowatt, then you don't need to know your power factor. You could have just your power factor, your volts, and your amps, and then you could calculate everything, right? Because you could take your power factor times your amps times your volts times the square root of 3 divided by 1,000 would give you kW. You could take your volts times your amps times square root of 3 divided by 1,000 would be kVA. So you could get all your values. So again, a power factor meter, all it does is measures the phase angle difference between your voltage and your current. And this is a typical connection of a power factor meter. And again, it has no PT, so you want to watch out for that. Don't actually hook it up like this if it's over line to neutral. It was over 120 volts. Energy meter. So here you're looking at the total kilowatt hours, let's say. So how many kilowatts were consumed in an hour? So it's the energy meters work on the principle of electromagnetic induction or diometer type. It can be also digital or analog. Same connections as your kilowatt hour or your kilowatt meter or your power factor meter. You've got your current and your voltage required. Fuses. So these are all IEC type fuses. An HRC or HBC fuse. A fuse is a switching device that by fusion of one or more of its specifically designed components opens a circuit in which it is inserted and breaks the current when this exceeds a given value for a sufficient time. So the fuse must sense fault currents, open quickly and clear itself when a short circuit occurs, sense a normal or harmless overload because becomes excessive or prolonged, not change or alter the characteristics of the circuit during normal operation. So here we have a sine wave. You see that dashed line in a sine wave, P. So here we have our prospective peak current of the circuit. I is the current, T is time. So C, the value C, is the cutoff current. That's our desired cutoff current. T1 is the pre-arcing time, and T2 is the arcing time. And T, the capital T, is total operating time. So if you look at the T1 time, the sine wave starts to rise, right? And it detects it. It has a cutoff current. It detects it, and it stops. It opens the fuse. And then the current bleeds off. So that's your total operating time. Very fast, actually, because that's it's very quick. So you can see how quick that thing operates. A circuit breaker, typically like a 480 volt UL 489 circuit breaker, molded case breaker, operates in 5 cycles. This is less than a cycle. That's pretty fast. A medium voltage circuit breaker might operate in 3 cycles, but certainly not as fast as a fuse. So a fuse is a very, very good device and reliable device if it's installed properly, and it needs to be studied so that you look at the I squared T curves so that you don't have any nuisance tripping. Selection for proper fuse size. Criteria for selection of fuse. Ability to withstand motor starting current. Remember I told you that a motor starting current is 6 times the full load amps. So you want to make sure that you know what the motor current looks like, the curve, the starting curve looks like on a motor. And then you want to make sure that the fuse is large enough so that it doesn't touch that motor, or its time is far enough away from it so that it doesn't have issues when you're starting and stopping the motor. Or actually, when you're starting the motor, you're not going to have current on your stopping it. You need to maintain a Type 2 short circuit protection device coordination. So when you're doing your time current characteristics for the fuse links, you want to ensure you have a Type 2 short circuit protection coordination. You want to make sure you have discrimination. You also want to make sure you have low power loss. So these are all the characteristics you would have to consider if you were doing like an SKM study, or if you're just sizing a fuse. Most people don't do this trouble. They don't go through all this trouble. And what they do is they usually look at the full load amps and multiply times 1.25, and that's the size of the fuse. So ability to withstand motor starting current. The fuse link selected should withstand repeated starting currents without any deterioration. The rating of the fuse links is decided by the motor starting current and its starting time. This will depend on two factors: the type of starter. Is it direct across the line, or star delta? So if you have a motor and you rearrange the windings, if it's a three-phase motor, into a star, then you have in effect reduced its voltage. So you actually have, like, I don't remember what it is, 58% less starting current in a star to a delta. And then you need to know the motor characteristics. So here's a time current characteristics of the fuse link. So it gives you all the different values for different size fuses. So this is what they call an I²T curve. The Type 2 SCPD, or short circuit protective device coordination, is the, per IEC standards, is under fault conditions, the contactor or starter shall cause no damage to persons or installation and shall be suitable for further use. That means that it doesn't destroy itself, right? There is a type of type, I think it's type 1, where it's okay to destroy the starter. Well, you don't want to do that in this coordination. So you want to make sure the fuse is sized so that you don't destroy the contactor or the starter. Type 2 SCPDs reduces fire and safety hazard, minimizes disruption in production and system downtime, minimizes replacement costs, provides solutions for no damage protection requests. Discrimination, when we talk about discrimination, we need to make sure the fuse links should be sized in such a way that under overload conditions, the overload relay and the circuit should operate and protect the circuit, and the fuse will operate and protect under fault conditions only, short circuits. So you want to make sure that on that I²T chart, you put the overload, so you can look at the thermal overload and make sure that you don't operate the fuse before the overload has time to open. Low power loss. One of the most important factors while selecting a HRC fuse link is the power loss. The fuse link selected should preferably have low power loss. The advantage of having such a fuse link with low power loss are savings in energy, power, low temperature rise at fuse switching terminals and fuse knives. So I don't know if you've ever touched one of these fuses after it's been running for a while, but they get hot. The outer shell gets real hot. And so if you're designing a control panel, you need to factor in how hot these fuses get. So a rule of thumb, rating of a main line fuse fitted into a control panel should be fuse rating, the kVA times 1.66 minimum, kVA times 1.7 max. Fuse rating current should be 1.2 minimum, 1.22 max. So that's why most people just take the full load amps times 1.25 and they're off and running. But you could not address every condition or oversize the fuse if you're not careful. Switches and switch disconnector fuses. So here's different types of switches and switch disconnected fuses. So you can have a disconnect switch with a fuse combination. A switch is a mechanical switching device capable of making, carrying, and breaking current under normal circuit conditions, which may include specific operating overload conditions, and also carrying for a specified time current under specified abnormal circuit conditions such as those of short circuit. A switch may be capable of making but not breaking short circuit currents. So we call that a load breaking switch or non-load breaking switch. If it can't open under full load, it's a non-load breaking switch. I want to make sure you understand that. You don't want to open up a switch if it can't handle the breaking faults. You could destroy the switch. You could arc over and just weld itself shut and destroy itself. Switch fuses, rewirable switch fuses capable of breaking, carrying, and breaking normal current, switching on and off on minor loads, breaking and making and breaking under short circuit conditions. Off-load changeover switch, capable of making and carrying or breaking normal currents, switching on and off on minor loads, but for longer life of contacts it is recommended to switch on and off at no load. Making under short conditions with limited withstand capability. A double break fuse switch capable of making, carrying, and breaking normal currents, switching on and off on minor loads with added advantage of better contact area, making and breaking under short circuit conditions. So you want to make sure that you understand the type of switch you're putting in and what it's capable of opening and closing. There's different types of switches. We have on-load changeover switch capable of making, carrying, and breaking normal currents, switching on and off at rated operating currents, making under short circuit conditions with limited withstand capability or capacity. Disconnector. A disconnector is a mechanical switching device which in an open position complies with the requirements specified for the isolating function. A disconnector is capable of opening and closing a circuit with negligible current flow, so it does not cause any sufficient or significant change in voltage across the terminals of each of the poles of disconnector. It is also capable of carrying currents under normal circuit conditions and carrying for a specified time current under abnormal conditions such as those in short circuits. Disconnectors, a switch which in the open position satisfies the operating requirements specified for a disconnector. A switch disconnector fuse is a switch disconnector in which one or more poles have fuses in series and a composite unit. There's a lot of things you have to consider when you're supplying or specifying components in a control panel. And if you're designing an IC control panel, you need to understand all these different types of switches and types of fuses and what have you. Same thing for UL disconnect control panel. There's various types of disconnect fuses. So you have a switch disconnector and a switch disconnector with a fuse. I'll let you just take a look at them. You can also follow along in the printed out PDF and kind of study this on your own as well. We talked about utilizing categories of switches. The AC20, 21, 22, 23. The AC20, or DC20, 21 and 22 and 23. So switches have a different utilization category. Making and breaking capacity. So cosine F is your power factor, right? 0.95 is like a just a resistive load, if you will, slightly inductive. Voltage is U, I is current. So you don't want to exceed 1.5 times the current voltage, 1.05 times the voltage, and 0.95 power factor. That's what you're making whenever you're closing the switch. You want to make sure your load doesn't exceed that, right? If it's an AC23, it's 10 times the current with a 0.45 power factor. Why would you have a 0.45 power factor? The reason you'd have a 0.45 power factor is because an induction machine is a very low power factor when it starts. So, and it could have up to 6 to 8 times the full load amps. So it's 10 times the current, 1.05 times the voltage, and a 0.45 lagging power factor. So that's a motor. Circuit breakers. There's different types of circuit breakers. UL panels versus IEC panels are slightly different, but a lot of these circuit breakers have dual ratings nowadays. You get your miniature circuit breakers, your molded case circuit breakers, your air circuit breakers, and your residual current circuit breakers. Your miniature circuit breakers are switching devices used for switching on and off loads, making and carrying breaker normal rated current, breaking the circuit under overloads or short circuits, making under short circuit conditions. So you can close or make one of these breakers, you can close a breaker under a short circuit condition. Remember, that breaker has got to be UL 489 listed if it's going to be used as the main branch circuit protective device. If it's rated UL 1077, then it's only a supplementary protective device. A molded case breaker. In UL, a molded case breaker can never be run higher than 80% of its nameplate rating. That also applies to any molded case breaker, be it a miniature breaker or a large UL 489 breaker. The only time it can be rated at 100% of its nameplate rating is if it is stamped 100% rated breaker. If it's not stamped 100% rated breaker and it just says molded case circuit breaker, then it shall not be rated more than 80% of its full load amps. The reason is because they're not sure if it'll trip at the right time. So they limit it to 80% of its value. And remember, if this is a UL control panel, so you can see there's a CE on that on that breaker right there. So that's a European breaker. If it's got the dual rating and it's got a UL label on it, if it's UL 489 rated, then it can be a main breaker. Okay, now we're going to talk about electrical protection. Again, we still haven't really gotten into the meat of UL 508A procedures or IEC ATEX procedures or CE procedures, but the most important thing I feel is that you understand all these different components and that you understand how they're all put together before you start building a control panel. Electrical systems. The design of electrical systems to transmit the electrical energy to the utilization equipment must focus on two basic requirements. The system must be adequate to deliver each piece of equipment the necessary energy on a continuous basis under normal conditions. The system must be designed to minimize power outages and damage in the event that abnormal conditions occur on the system. So if we size the power system correctly and we specify the right components and the right fuses, then we should meet these two requirements. Could be either type 2 type starter, could be like a, make sure you got the right AC designation for the switches and the contactors. Nothing is perfect. Since nothing manufactured can be deemed to be perfect, it must be assumed that equipment will fail, which it will. Failure on any part of the electrical system can result in the uncontrolled flow of tremendous amounts of energy that can cause major damage in split seconds. And we kind of talked about that, right? If I have a 1000 kVA transformer with a 40 volt secondary and it has a 5.75% impedance, then it has the ability to deliver, assuming the primary current can deliver it, 20,000 amps. If that 20,000 amps is delivered in a split second, right? Because one cycle, if it's a 60 hertz system, is 16.67 milliseconds, then it can destroy that control panel. And you don't want to do that, because if it destroys the control panel and an operator is in there or an electrician maintenance guy's in there and he's working in there, then he's going to get molten material and shrapnel on him. You'll get an arc flash issue, right? So you want to make sure you design everything properly so that it interrupts the fault without destroying equipment or hurting anybody. Protective systems. Protective systems cannot prevent the failure of the equipment. Their primary purpose is to remove the faulted segment of the system as quickly as possible. So what that means is not everything works the way you think it should. So sometimes the equipment will be damaged. And if the equipment is damaged, if a maintenance guy's in there, he better have on the right PPE. He needs to be aware of arc flash problems, arc faults. And if he gets inside a 40 volt control panel and it's fed by a real large transformer, he can actually have shrapnel thrown at him. Not a good situation. Protective systems should prevent injuries to personnel, prevent fires, minimize the damage to the electrical equipment, and electrical systems must operate in a safe manner. What are we looking for? We're trying to detect abnormal conditions, overloads, short circuits, undervoltages, single phasing of three-phase systems. If you run a three-phase motor on and you're missing one phase, it'll destroy or burn up that motor. You want overvoltage, transient surges. An overvoltage can be caused by lightning and also can be caused by switching circuits, right? Other breakers opening and closing upstream can cause a transient surge. Incorrect synchronizing of frequencies. Incorrect phase sequence. You don't want to slam a breaker, two breakers closed, two sources closed, ABC on one, CBA on the other. Reverse power flow. You don't want to backfeed a synchronous generator and cause it to run backwards. Minimize the disturbance to the system. People and property. NEC Article 90, Introduction 90, Section 91, Purpose. Practical safeguarding. The purpose of this code is the practical safeguarding of persons and property from hazards arising from the use of electricity. Overloads. This is when the load starts drawing more power than the system was designed to provide. Let's say a system has a 100 VA transformer and the load is 150 VA. The system is overloaded by 1.5 times. This is acceptable for a few minutes, but then must be removed from the system if it continues. Overloads are not caused by electrical fault failures. So it's not a short circuit. It's just a gradual overload. Short circuit, this is caused by an electrical failure, such as the breakdown of the insulation. The fault can vary in magnitude from tens of thousands of amps, depending on the capacity of the system, to 6 times the design capacity of the system. Overloads can range up to 6 times the design capacity. Short circuits are 6 times and higher. Short circuits, any fault current in excess of 6 times or 600% are then assumed to be a result of a short circuit. Short circuits must be disconnected immediately. All circuits and equipment must be protected against overcurrents. The fuse. We already talked a little bit about the fuse in the I2T chart. The National Electrical Code defines the fuse as an overcurrent protective device with a circuit opening fusible part that is heated and severed by the passage of current flowing through it. Thus, the fuse combines the current sensing and interrupting functions into one element. Fuse is an overcurrent protective device with a circuit opening fusible part that is heated and severed by the passage of overcurrent through it. Burns it open. A fuse comprises all the parts that form a unit capable of performing a prescribed functions. It may or may not be complete device necessary to connect it into an electrical circuit. A fuse does not instantly open when the current exceeds its rating, nor should it. The fusible element within the fuse, of course, responds to the heat generated by the passage of the current through it. The heat is a function of the I2T. Thus, the fuse inherently has an inverse time current response, which is a desirable characteristic. Branch circuit per UL 508A. The conductors and components following the current, the last overcurrent protective device protecting the load. Branch circuit protection. Overcurrent protection within an ampere rating selected to protect the branch circuit. For a motor branch circuit, the overcurrent protection is required for overcurrents due to fault circuits and faults to ground only. In UL 508A, branch circuit type fuses, a fuse class of class CC, G, H, J, K, L, R, and T. These fuses are able to provide branch circuit protection. Semiconductor type, a fuse designed for the protection of semiconductor devices such as an SCR or a diode. These fuses are able to provide branch circuit protection of motor circuits containing power conversion equipment. So you could have a soft start, which is back-to-back SCR, like a thyristor, for A, B, and C phases. And you would need a semiconductor fuse. A supplementary type fuse is a miscellaneous type and miniature type fuses. These fuses are able to provide supplementary protection only. So that supplementary fuse is your UL 1077 fuse, cannot be used as a branch circuit type protection. The advantages of fuses: low initial cost, simple, no parts to maintain, compact, requires little space, high current interrupting capabilities, provides current limitation, thus materially reducing or eliminating the possibility of conductors or equipment being damaged by mechanical or thermal stresses under fault conditions, can provide good selective coordination on electrical faults, thus eliminating unnecessary shutdowns. Inherently fail-safe, that is, if they fail, they open the circuit, thus making it safe. All good examples. Disadvantages: must be replaced after each operation, longer downtime. So if you're on some remote place like a rig, you better have a lot of spare fuses, and hopefully they're sized properly and you're not having to exercise them that often. Can cause single phasing, which is detrimental for motors. If you lose phase A on a motor, a three-phase motor, the motor will fail unless you have some mechanism of detecting a phase loss. Not adjustable. Time current characteristics are fixed, so you got to select the right fuse. Affected by ambient temperatures, which may cause needless blowing of fuses. This is where a lot of people get into trouble. They size a fuse properly, but they don't consider all the heat generated in that control panel. And then that control panel gets put out in a 40 C ambient, and then the internal devices in that control panel heated up over 60 C or 50 C, and the fuse is sized for a 25 C ambient. See the problem? You need to make sure you understand that what the ambient temperatures are and how that fuse will blow in that characteristic. Problem is, in the wintertime, the internal ambient temperature might be less than in the summertime. Can be replaced by another fuse with incorrect ratings or characteristics, unless there is a rejection feature. Like the class CC fuse has a rejection feature, but there's a problem. Let's say I have a 10 amp class CC fuse, and somebody says, damn, that fuse always busts in the summertime. Let's just replace it with a 15 amp class CC fuse. It pops right in there. And now, in the wintertime, we're no longer protecting. And also, they've exceeded their values in the summertime. So, there's a real problem there. If they have nuisance tripping, they will increase the size of the fuse. Require the stocking replacement fuses for each type of used. And so if you're out there in the middle of nowhere, you need to stock these fuses. Cannot by themselves be used as an isolating means for the circuit. They must be mounted in combination with a switch. So if you have a switch fuse combination, you can put them in there, but they can't be used by themselves. So when you're designing control panel, this is something I put together. This is a little checklist, right? You want to calculate your CPD loading. You want to calculate your enclosure heating. You want to verify that you're not in solar, straight sunlight, right? You want to confirm the weight of the panel. You want to confirm all your wire sizes. You want to confirm all your UL listed or UL recognized devices. You want to ensure adequate space in and outside of the panel for maintenance. Calculate the CPT loading. Basically, add up all the loads on the CPT and ensure that you have not overloaded it. A good rule of thumb is to load it up only about 80%. I added a little CPT loading chart here. So you can see here I've got a PLC power supply, 1746, which is a Allen Bradley slick 500 series. So if you have a P4 style, then it's 200 VA, 240 VA. If you got one of them, you got 240 VA. So if you've got a PCB, a 50 VA CPT, it's 50 VA. If it's a maintenance light, it's 26 watts. Could be different for you, but I'm just saying that these are simple things that I used to use all the time. Space heater, you want to throw that in there, the VA for that. Power supply, 20 amp power supply is 828 VA. DC to DC signal conditioners, they're small, but they carry 1 VA. You get enough of them, you got some serious loads. Those big old power contactors, a 265 amp power contactor. The VA to pull in that contactor, 66 VA. Those little D-line, this is Schneider or Square D-line combination starters, the D009 to D36, they're 55 VA. How about a 10.5 inch color touchscreen, 50 VA. So here in this example, we've got a Interlock power supply, 1 amp, and 120 volt AC solenoids. We've got 5 of them at 8.1 VA each, so that's 40.5. So we have a total of 92.5 VA. Of course, that's kind of unrealistic because why would we have that, you know? But it is what it is. Just an example. It's just a lot of people don't go through this trouble. And so what you want to do is you want to add up all your loads. And on your right-hand side, if you've got 24 volt DC power supply needs, you want to add them up and make sure that you have installed the proper Interlock power supply or whatever power supply you buy. So this one says I need a requirement of 19.2 watts on my DC source. And I have a, let's see here, quantity 16 sub-watts. Okay, so then you got your total watts. So your watts, you need at least a 1 amp DC, 24 volt DC is 24 watts, so it'd be a 19.2. So you got to pick a 1 amp device, which I did, so it's 52 VA. So you can see that even you're only putting out 24 watts because it's 1 amp times 24 volt DC is 24 watts, but the power supply is so inefficient it actually draws 52 VA. Anyway, just something you need to do. A lot of people don't do this and they get in trouble. Next thing you want to do is you want to look at the enclosure heat calculations. Another thing people don't do. It's very important to determine the internal heat dissipated into the enclosure. The way we do this is to look up each component heat dissipation or efficiency. When you have large wires or cables, you need to determine the heat that they will add to the internal enclosure. And also for fuses, large power fuses can put off a lot of heat. So you need to make sure you understand that as well. So here we have something I put together. I think I used a Hoffman equation to do this, a little chart that they had. So you have a circuit breaker, 250 amp frame, 125 amp trip. According to this literature from them, it is 16.5 watts per pole. So 16.5 times 3 is 49.5 watts. That's the heat that it will reject from that breaker and put into that panel. So if you've got one of those, you've got a firing board, you've got 6 IDAC relays, you've got a phase monitor relay to protect against the loss of phase or under voltage or something like that. You've got a couple of transformers in here, CPTs, you've got a PLC, you got to add up all that watts, right? That 55 watts from that PLC is a lot harder than it looks because really you have to add up a bunch of stuff, right, to get that value. So you have to have a separate spreadsheet just for the PLC. That contactor, it's a 150 amp contactor. It has 6 watts per pole loss. So 6 times 3, 3-phase contactor, it's 18 watts. So you add them all up, and then they give you a nice little solar gain. So based on the Hoffman software, it says you have to add 15 watts for it. So it's 197.62 watts. Maximum inside enclosure temperature 60 degrees C. Why 60 degrees C? Because that's what those components are rated for. Your ambient temperature is 40 degrees C. Why 40 degrees C? What if it's 52 degrees C? A UL508A panel is only rated for 40 degrees C. Most people don't realize that. Even if it goes into, Saudi Arabia, where it could easily exceed 55 degrees C, is technically only rated for 40 degrees C. You need to be aware of that. But if you are putting it in a 50 degrees C area, you need to go ahead and plug in 50 degrees C here so you get the right temperature, internal temperature, and you don't exceed that 60 degrees C. Next, you take your enclosure of height, weight, width, depth. Is it carbon steel or is it stainless steel? 316. Or is it aluminum? Or is it plastic? These are things you need to figure out. Get your surface area of all sides. Get your input power, or your watts per square foot. And then you get your temperature rise above ambient for carbon steel. And your temperature rise for steel or stainless steel. So you can see that it's 58.3 degrees C if it's 316 stainless steel. Stainless steel is a terrible conductor of heat. Carbon steel is the best conductor of heat. So you need to make sure you do this calculation and make sure that you've factored in everything, right? Another thing you need to do is if you've got a bunch of bus bar in there, right, you need to make sure you calculate the heat dissipated by this bus bar. Here I've got a rectifier. I've got 1500 amps. I've got a 4-inch width, 40-inch length, 0.7 3/4 inch thickness, and then you've got your watts, right? So I've got so I got a total of 160.74 watts added to that control panel. So you need to factor that in. If I've got a bunch of 4-aught 200 amp cable, I have 119.04 watts added to the inside of that control panel. That's the kind of things you got to think about. Otherwise, if you don't think about all these things, that panel will overheat. Verify the solar gain. You know, obviously Hoffman or whoever the panel manufacturers, they've got great guides on this. But in general, do not put a panel in direct sunlight. Put a roof over it. Do not put a touch screen in direct sunlight. It is easier to put a small plastic enclosure around it or some type of a metal enclosure. If you put these things in direct solar, it can just really overheat them and cause all kinds of troubles. And you'll never understand why you're having so many troubles. And it might be bad grounding, might be due to thermal issues. Confirm the weight of the panel. Why would you need to do that? Well, somebody's got to mount this panel. Either they got to mount it on a frame, a steel frame. Somebody needs to understand the weight of this panel. Otherwise, it's a safety issue. So you need to give this to your civil structure engineer. So go through the whole issue of figuring out the weight. If you've got one of those NEMA 7 large, thick, explosion-proof panels, a NEMA 7 30-inch by 38-inch by 16-inch deep panel is 800 pounds. That's a big panel. So come up with your height, weight, depth, type of material. So 12-gauge steel is roughly 4.375 pounds per square foot. For 14-gauge steel, it's 3.1725 pounds per square foot. And then from there, you can actually calculate your weight. If you want to add, let's say you're putting all of this on a skidded package, you want to go ahead and add up all your glands, add up all your, your cables, your contactors, your entire enclosure weight. And so here we have an example. Our panel, if it's 12-gauge steel, it's 256 pounds. If it's 14-gauge, it's 183 pounds. Confirm the wire size. So here we have an example. We have the minimum THW in copper conductors rated at 75 degrees C installed in conduit required to serve a 230 volt, 10 horsepower induction motor, non-continuous, 1 kilowatt resistance heater on a circuit operated at 240 volt AC. What is the right size wire? Is it 4-aught? Is it 2-aught? Is it 4 AWG? Or is it 6 AWG? So you got 230 horsepower, 230 volt times 10 horsepower is 50 amps. So then you got 240 volt times that 1 kilowatt heater is 1000 watt, because 1 kilowatt is 1000 watts divided by 240 volt is 4.17 amps. You take your 50 plus your 4.17 amps is 47.17 amps, or 54.17 amps. So you need to size, the conductor needs to be able to handle 54.17 amps. What this doesn't consider is the voltage drop required, right? So it's probably C, right? I'm just guessing, 4 AWG. So there are motor schedules that you can follow. So it says here horsepower is, let's say that 10 horsepower motor, its full load amps is 15, its kilowatts is 11.5, minimum wire gauge is 6 AWG, ground wire is 8 gauge, max wire length is 141 feet. Why do they have that? Well, they want to make sure that they maintain less than 3% voltage drop. And conduit size, if you have 2 wires, is 31% fill. So they give you that as well. So here you got motor horsepower and amps, kilowatts, see columns 1 through 3. Your wire sizes, see columns 4 through 6. For the max wire length, see column 6, or the wire size is 4.4 through 5, and your conduit size is 7 through 14. It's a nice little chart. What we use is a single phase circuit conductor here. So here you've got your 240 volt AC. Remember we added up, it's 54.17 full load amps. You want to multiply that times 1.25 per 31016. I think the new code is, because it's 2011, they changed it to 31015, which is stupid. So 5417 times 1.25 is 67.7. So the conductor has to be greater than 67.7, right? And so if you slide on down, you see these blue? These blue means that it's less than 3% voltage drop, right? Those are safe areas. But you want to make sure that you size it for the conductor length, right? So that 240 volt AC at 54.17, I highlighted it for you. It is a 4 AWG is conductor capacity is 85 amps. You need to be greater than 67.7. If you went a 6, it'd be 65 based on 75 degrees C. And then it gives you your conductor effective impedance, Z. It's 0.8 power factor, and the voltage drop is 0.31%. So the correct wire size for that previous example was a number 4. So here again, you've got the minimum size THWN conductor at 75 degrees C installed in a conduit. So really, you take that, according to the table, NEC 430-248, this motor has a full load amps of 50. So according to 430.22a, specifies 125% of this, so 50 times 125. The heater is 1,000 watts divided by 240 is 4.17 amps. This load is rated non-continuous, so the current is taken as is. You don't have to multiply it times 1.25. So you just add the 62.5 plus the 4.17 amps, so that's 66.67 amps. So according to table 31015b, 16 shows a 4 AW THWN has an ampacity of 85 amps. Remember, the current conductor must carry the fault current calculated. The next size up is not permitted for conductors. So 4 AWG. Answer this question. So these questions, or this kind of line of thought, should help you be able to size different conductors in different conditions, right? So with the National Electrical Code, assume the voltage at the main distribution panel is 40 volt AC, 3-phase. Feeder F1 consists of 3 500 kc mil THWN copper-based conductors and a neutral and a steel conduit that runs a distance of 250 feet. Panel A serves a continuous balanced load of 300 amps at 0.8 power lagging power factor. The voltage at panel A is most nearly what? So what we're trying to do is figure out what the voltage drop will be, right? So if you solve this, you got 1% voltage drop, or 480 volt times 0.08 is 4.8 volts, or 480 minus 4.8 is 475 volts. We'll do a little bit more on that. So here you have different formulas, the exact formulas for calculating voltage drop. So using our little calculator sheet, we have full load amps is 300. We have at the top conductor length is 250 feet. It's a power factor of 0.8. So 300 times 1.25 is 375 amps. It is 500 MCM, remember that. So conductor length is 250, it's 300 amps, it's 40 volts. So this says that it should have a voltage drop of 100%, 1%. So 1% is what we just said, we showed before, 1% of 480. So it's 4.8. This gives you another example and how you would have to deal with the different types of conduit, right? The Z of these conductors are found on Table 9. The steel conduit, Table 9, shows a resistance of 0.029 ohms per 1,000 feet and a reactance of 0.048 ohms per 1,000 feet. The general equation is given by note 2 of table. Effective Z equals R cosine theta plus X sine theta. Therefore, Z equals 0.029, that resistance, times 0.8, the power factor. That the cosine theta is power factor, right? So 0.048 is ohms per, the reactance is 0.048 ohms per 1,000 feet, so 0.048 times 0.6 divided by the 1,000 feet, or 0.052 per 1,000 foot. So this has circuit is 250 feet. So this number must be divided by 4 because it's in 1,000 feet. So Z 0.052 divided by 4 equals 0.013. E equals I times R, so E is 300, or I is 300, remember 300 amps, times the impedance, R, resistance, impedance is the resistance, in this case 0.013, which equals 3.9 volts. But caution, this is a line to neutral voltage. It must be multiplied by the square root of 3 if it is to be compared to the line-to-line voltage. So 3.9 volts times square root of 3 is 6.8 volts. So 480 minus 6.8 is 4.73 volts. I think I said 4.75, but that's truly how you solve it right there. So there's a lot of things that you have to consider when you're sizing wires, right? To correct power factor, a capacitor is proposed to be connected to point A in a three-phase induction motor circuit shown in figure below. Why would we put a power factor correction capacitor out there? And what are some of the problems we might run into when we do it? After the addition of the capacitor, which of the following statements is most likely correct? The full load current at motor M will be significantly reduced. That's true. The full load current at motor M will be significantly reduced. That's not true. The motor overload trip settings must be reduced. That's true. Because what you've done is by adding the capacitor, you reduce the line current, the current flowing through the switch, the fuse, the contactor, and the overloads. But the current flowing to the motor is the same. The NEC requires that the capacitor be connected through a separate disconnect switch. That's not true. The motor feed conductors may be sized for a reduced ampacity. That's false, because the capacitor could fail, and if it failed, then the current goes back up to the full load amps of the motor. So there's a lot of things going on there. So A, the full load current at motor M will be significantly reduced. Not true. Be careful here. The current at the motor is not changed at all. It is only the current at point A that is changed. The motor overload trip settings should be reduced. Yes, if the overloads are not adjusted down, an actual overload condition could occur that might not be protected. So by adding the capacitor, you're actually reducing the current that the overload and the fuses see. You're not changing the kilowatts, you're changing the kVA, the kVAR, right? So as you bring, it's a power triangle, right? If you put more capacitance on an induction motor, you're actually making the kVAR less, so you're making the kVA come closer to the kW, so the power factor is increasing. If you have a higher kVA, your kW never changes. That's horsepower, right? Direct relationship. So if kVA increases, your current increases. If you decrease your kVA so it matches your kW, your current now is decreased. So if the capacitor fails, it goes back up to the higher kVA, the higher power factor rating, and your overloads need to be set so that they're less when the power factor is correct. The NEC requires that the capacitor be connected to a separate disconnect switch. Generally, this is true. It is covered in Article 460. 460.8c exception states that a disconnect is not required on the load side of the motor controller. I guess this one thumped me because I always knew that you could stick the the capacitor right at the load side of the motor, or the load side of the controller. The motor feeder conductor may be sized for a reduced ampacity. This is a total violation of the spirit of the code. If the capacitor became disconnected, the conductor would still have to be able to carry the load, and the wire would burn up. So the answer is B. An unknown wire gauge must be determined during an electrical inspection. The wire diameter is measured at 0.2591 centimeters. What is the American wire gauge standard designation? 4-aught, either 4-aught, 4 AWG, 8 AWG, or 10 AWG. So 0.2591 centimeters requires you to go to one of those tables, the tables in the back of the NEC. So if you go to Table 8, Conductor Properties, you'll see that at 10 AWG, the overall diameter is 2.588 centimeters squared. Circular mirror, or millimeters diameter. The circular mills is 10,380. The millimeter squared is 5.261. So Table 8 in Chapter 9, Conductor Properties, shows the applicable information. The overall diameter of the conductor is given in column 7 in millimeters. Problem gives the diameter as 0.2591 centimeters, which is just divided by 100 is 2.591 millimeters. So you have a 10 AWG solid conductor. Just kind of get you motivated to look at the conductor cables and the NEC. A branch circuit is to supply 20 amps of continuous load and 5 amps of non-continuous load. What minimum conductor capacity is required? So if it's 20 amps of continuous, you need to multiply times 1.25. If it's 5 amps of non-continuous, you can just take the 5 amps. So it's 20 times 1.2 is 25 amps, plus your 5 amps is a total of 30 amps. D. And indeed that is the case. So always remember your continuous and non-continuous. A 4-wire 120 volt, 240 volt / 120 volt delta connected secondary is used as a feeder for a variety of downstream circuits. Upon investigation, phase B is noted to be orange in color. This color described by NEC Article 110.15 indicates what magnitude of voltage in this case. So here we have some weird circuit, right, where they took the center of the delta and they grounded it. This is actually called the stinger leg. And the reason they call it the stinger leg is because when I was in the Navy, the Seabees, we'd call this a stinger because it always burned somebody, right? They'd get shocked. It's actually 208 volts. And it should be orange. So the appropriate code reference is given in the problem statement. If you draw a line from the top of the triangle to the middle of the base, you will find that each half is 30, 60, 90 right triangle. The long leg is square root of 3 times the short leg. Therefore, the short leg is given as 120 volts. This gives the long leg, phase B, to reference as 120 times square root of 3, or 208 volts. So it is 208 volts. It's called a stinger leg. A 200 horsepower 460 volt 3-phase continuous duty squirrel cage induction motor is designed to operate at a 0.85 power factor. The supplying branch circuit is 30.5 meters long and utilizes THHN copper conductors and a steel conduit. The voltage drop is limited to 3% in the branch circuit, leaving 2% in the feeder circuit. That's where you get the 5%, right? That's the rule. So you get 2% in the feeder circuit, 3% in the branch circuit. NEC Table 430-250 and Table 9 list the applicable data. What size cable should be used to meet the voltage drop recommendations and current requirements of the load? So here we have motor full load amps is 240 amps. So your motor was a 200 horsepower. So you got 460 volt, 240 amps. Going to this little cheat sheet or a little Excel spreadsheet we have, a system voltage 460, conductor length is 100 feet, 0.85 power factor. So 240 times 1.25 is 300. So if you slide on down here to 300, it has to be at least a 350. If it's not a 350, it can't withstand 300 amps. So I kind of cheated because I always use that simple chart, but here it is. The problem is a direct attempt at trying to get the test taker to waste valuable time. Look up the answers first before you start calculating. First of all, the motor, according to table 430-250, has a full load amps of 240 amps. 240 times 125 is 300. Of course, the answer choice of 350 is the only one that is rated for this much current. Plus, the rule of thumb is about a volt per foot. So since a 480 volt circuit, we don't get into appreciable voltage drop problems until the circuit is over 500 feet. This circuit is only 100 feet in length. There's no voltage drop consideration here, so it's 350 kc mil. Here's another example. We have a 200 horsepower motor, 460 volts. Full load current amps is 240 amps. NEMA starter would be a NEMA starter 5. Breaker size is 400 amps. Overload size would be 276 amps. If you had a space heater, it'd be about 400 watts. The space heater max current is 3.33. This is a chart we put together. We went through and put all these different motors together, and you can quickly grab from them. I think we did 240, some single phase, 460, 4160, 2400 or 2300 volts, and 13.8 kV. That's kind of the industrial sizes you'd run into. And there's your max distances, which is kind of handy, and your power and control cables and space heater requirements, and then all the rules associated why we size things the way we did. So find the ampacity of a 4-aught THWN copper conductor routed into conduit. The conductor is one of 6 current carrying conductors in the same conduit, 2 per phase. The conduit is routed to an ambient temperature of 40 degrees C. There's a bunch of problems with this problem, right? One, it's over 40 degrees C. You're building control panels for UL 508A. UL 508A only accounts for 40 degrees C. Neither here nor there. So when you size your enclosure, make sure you understand the ambient temperature. You've got more than 3 current carrying, or was it 4 to 6 current carrying conductors, you multiply it times 0.8. There's a derating factor. If it's less than, it's like 3 current carrying conductors, you don't have to derate it. Plus you have to derate for this higher ambient. If it's over 40 degrees C, you have to derate it. So you take your 4-aught and your 75 degrees C column is 230 amps. Times your 0.8, you have 4 to 6 current carrying conductors. You have to multiply times 0.8. Times that 0.82 is 43 degrees C. If it's over 30 degrees C, I believe for that chart, then you have to derate for a higher ambient. So you have 230 amps times your 0.8 for 6 carrying conductors, plus times your 0.82 for the high ambient gives you 150.88 amps, or be 151 amps. So that 4-aught is now only good for 151 amps, given this condition, right? And you need to make sure that your panel can handle 2 4-aughts per phase, right? That's some big cable. And so this gives you the charts, right? So you can see the 75° C column, copper. The 4-aught says 230 amps right there. It says you've got adjustment factor for more than 3 current carrying conductors in a raceway. So you got 4 to 6, you got 0.8. Next thing you've got is a ambient temperature correction base factor on 30° C. So the chart was based on 30° C. So if it's 41 to 45° C, 75° C column, you got to multiply it times 0.82. So again, they go through it and they say 230 times 0.8 times 0.82, which is 150.88 amps, which is 151 amps. So that is how you size conductors, or how you determine the ampacity of conductors. There's a lot to it. I went over some 3-phase motor calculations, voltage drop issues, things like that, but certainly there's other things you have to consider as well, such as the short circuit rating of that conductor. Make sure you consider that. I didn't cover it in here. I actually covered that in a understanding power concepts class, but I should probably do that one as well. So next we're going to talk about control of electrical motors. This gets into contactors, motor starters, solid state starters, BFDs, things of that nature. I'm not going to go into a lot of detail. I just want to kind of touch the topic. Different types of motor controllers. You've got magnetic units, contactors, and motor starters. You've got solid state starters, and you've got programmable starters. This gives you a picture of a circuit breaker on the right hand side, a disconnect switch, that flange connection with some pilot devices on the bottom of it, and then you've got a soft start, a magnetic controller on the far left, but that one on the far right is actually looks like a reduced voltage starter, like a static switch. Magnetic controllers are universally used, made up of components such as relays or contactors, electromagnetic coils, electromagnetic and moving armatures, which you talked about, contactors, contacts and arcing horns, spring-loaded components such as push buttons, fuses, timers, interlock switches, main operation, basically it opens and closes the electric circuit by means of the contacts. Motor starter, basically made up of contactor, special relay containing coils, contacts, pressure springs, arcing horns, and armature. You have an overload protection. You have under voltage release protection. May or may not. Difference between a contactor and a motor starter is the added overload protection or under voltage release protection in the motor starter. I guess you kind of do have an under voltage release protection, because if it drops below 85%, the coil will automatically drop out. So it does have an under voltage release protection, which could be a problem if the motor is large enough, and when it starts, if you don't size it properly for that particular system, you could inadvertently create a voltage drop due to the motor starting, and then you could drop the contactor out. So you want to make sure you design it properly. Two interesting parts of the contactor is a shaded coil. On the face of the coil there is a shading coil whose purpose is to reduce armature vibration so it doesn't chatter. You also have a blowout coil connected in series with stationary contact with purpose to blow the produced arc out when it opens. You have overload protection implemented when overheating occurs. Overheating occurs when you have a stalled rotor. If you have a stalled rotor, your current's going to rise. Low voltage, low frequency in the case of an AC motor, or an unbalanced voltage. Thermal relay. consists of heater elements connected in series with the motor. You have a bimetallic element where one piece of metal is different than the other, so they deflect at higher heater temperatures. Contacts open when bimetallic element deflects, and a reset button manually closes the contacts. So after you have a thermal overload, you have to manually reset it so that it doesn't automatically start. Undervoltage release, undervoltage protection, implemented when loss of power of low voltage occurs. Undervoltage release allows for a voltage to be restored automatically. Undervoltage protection prevents automatic restarting when voltage is restored. Here's a connection wiring diagram. It shows the physical layout on the left. It shows the wire connection numbers. So the darker lines depict the power circuits. And this is just I think this is a garage door opener, elementary wiring diagram. Elementary wiring or ladder diagram, it shows the power on vertical lines called rails. It shows the components on the horizontal lines called rungs. So you can see you have the OC and the CC. So whenever the OC is energized, the motor rotates clockwise. And whenever CC is energized, the motor rotates counterclockwise. If you reverse any two phases of that motor, it'll rotate one way or the other. So, and you also have a control transformer, that TR. So it takes that line-to-line voltage, 208 volts, steps down to 120. Note they have X2 grounded, which is proper. You have a fuse, and you have your overload, and you have your stop button. If you press the open, what will happen is, let's see, so if we press open, then the OC coil energizes. When the OC coil energizes, it latches in OC. And it's interlocked with the closed coil, right? So what happens is the motor garage door starts to go in the direction so the door opens. When it hits the limit switch, the limit switch open, it opens and disconnects the motor. Now when you're ready to close it, you press the close button. When you press the close button, CC coil energizes, which causes the CC contactor to energize, which reverses the two phases. You can see A connects to A, B connects to B, and C connects to C on the primary side of the contactor. On the load side of the contactor, OC connects directly to the motor. But on the CC, the A and C are reversed. B's are connected and the C and A are reversed. So it's A and C are reversed. So when the CC contactor closes, it reverses the motor. And so when the close is closed, CC coil energizes, which causes the CC 9 and 10 to close, seals in the close button, so you don't have to sit there and hold it the whole time. Starts rotating the other direction. The garage door closes. When it gets to the point where it hits the limit switch, it opens and it stops. We talked about diagram symbols. These are different diagram symbols. You've got disconnect switch, circuit interrupter, circuit with thermal overloads, circuit breaker with magnetic overloads, circuit breaker with thermal and magnetic overloads. You've got limit switches. You've got different types of pressure and vacuum switches, liquid level switches, flow switches, temperature switches. That's the thing about motor starters and control panels. You don't know really what the process is. And in order to understand the process, you need to understand some of the process terminology, and we'll kind of go over that a little bit. Pilot lights, push to test. I like that push to test light at the bottom. You get your selector switches, your transformers, your coils, contacts, overload relays, maintain contacts, single phase, AC motor, 3-phase squirrel cage motor, make sure you connect the ground, a wound rotor motor, type of induction motor, not connected, connected, power, you want to make the power wires heavier, control lighter, battery, the cell, annunciator, bell, buzzer, resistors, different type of resistors, different type of contacts, single pole, single throw, single pole, double throw. There's different types of terminology there, different capacitors. We talked a little bit about SCRs. Here you have a stud type SCR. You've got the cathode as the top of it. The base of it is the anode. This is really the workhorse of the control industry for DC motors, generator field regulation, variable frequency drives, and lighting system control. A 3-lead device with an anode and cathode is a standard diode, plus a third control lead is a gate. So that's what an SCR is, or a thyristor. So basically, whenever you have an AC source here, if you gate between the gate and the cathode, the SCR will turn on, and the load will see the positive portion of that waveform. Whenever the gate is turned off, because it's an AC source, it will normally turn off. That means it will naturally commutate off, because when the AC source goes negative and the gate is not applied, the anode is more negative than the cathode, and therefore it'll naturally turn off. Also have a gate turn-off device, a GTO. It's a family of the thyristor family. The only thing about it is it doesn't have to reverse, right? So your anode does not have to be the same potential as your cathode. So when you remove the gate, it'll stop. It'll turn off. And when you apply the gate, it'll turn on, which is really nice because now you can turn on and off large amounts of power without having to commutate off, right? Or force commutate off if you had like a large inverter. And so this was really the big takeoff on variable frequency drives. Now they use IGBTs, insulated gate bipolar transistors. Triac, we talked about that. It's a bidirectional SCR. It's basically two SCRs back to back, and it allows the entire AC waveform to pass. So if you had 3 of these in series with your contactor, right? One of these in series with phase A, one of them in series with phase B, one of them in series with phase C, and you slowly started increasing the gate current, you could actually slowly increase the voltage. So you have a soft start. That's what a soft start is a triac back-to-back SCRs. SCR controlling a load in a DC circuit. So in a DC circuit, once the SCR turns on, it can't turn off. So if you press the on button, you gate it, right, with respect to the negative, and what happens is it turns on, so the motor runs. And when you want to turn it off, you have to break the current, right? You have to press the off button. You have to disconnect the current. Otherwise, it'll just stay on, even without the gates. AC/DC crowbar. A AC/DC crowbar is really meant for overvoltages, but let's see how this one works. Oh yeah, it's used for overvoltage protection. It consists of an SCR placed in parallel with the output of the DC power supply for the purposes of placing a direct short circuit on the output of the supply to prevent excessive voltage from reaching the load. Damage to the SCR and power supply is prevented by the judicial placement of a fuse or substantial series resistance ahead of the SCR. So here you have your AC source, your transformer, and your rectifier. You've got a filter there. It's a T filter with a fuse. You've got your crowbarring circuit, your sensitive load. Whenever the DC voltage rises to a point where it exceeds the overvoltage limit of the load, you energize the SCR and it forces the load to 0, and then you release it, and then it goes back to 0 to open circuit again. AC motor speed control. So this would be like for a drill. Bridge rectifier, you got your bridge rectifier, your 120 volt AC. Whenever S1 is closed, it rectifies it to DC. And then you've got these a pot, that 10K potentiometer with a 50 microfarad capacitors, 2 of those, and a resistor, and your SCR. So that creates your gating circuit. So the 10K pot is when you pull that switch in and you go faster or slower, right? So as you pull it in, the resistance of the switch changes, which changes the SCR firing circuit. which causes the drill to go faster, right? PLC Introductory Laboratory. We talked a little bit about PLCs. When the push button 1 is turned on and push button 2 is off, the blue light turns on. As long as push button 2 is on, the red light turns on, independently whether push button 1 is on or off. If both push buttons are off, neither lights turn on. If you want to understand how to program a PLC to do that, you need to watch the PLC programming course. I think I've thrown in, if you order this off eBay, you'll actually get the PLC automation CD or DVD, and on it, it has instructions on how PLCs operate. So you don't have to order the larger $80 program that I sell, which the $80 program obviously is better, but at least the automation DVD does give you the basics of PLCs. So as a panel builder, you might be asked to work on switchgear, medium voltage or low voltage gear, or even high voltage gear. You want to be cautious of some of the protective schemes in these designs, and you want to make sure that you understand exactly what you're asked to do. If you're building an open panel like a back pan and they're going to install it out there, you need to make sure you understand exactly how those things work. It's very complex protective schemes involved in switchgear. So you have different electrical faults. You have phase-to-phase faults, phase-to-ground faults, phase-to-phase-to-phase faults, phase-to-phase-to-phase-to-ground faults. So the point of switchgear is to protect against these faults. Purpose of protection system: to minimize damage, leave unaffected equipment in service, maintain equipment operating limits, maintain electrical system stability. Requirements of a protective system: speed, reliability, security, and sensitivity. If it doesn't quickly open, then you have a lot of time on your hands. If you have more time on your hands, you have more arc fault current, right? You have an arc flash issue. Some terms that we use: overcurrent, overload, inverse time. First thing you need to know is about protective zones. So on a simple motor circuit, you have a simple zone. You have a fuse and you have one protective zone. So the fuse is protecting that circuit, that motor, right? And the associated cables connecting to the motor. If it blows, the fuse blows, that's what it looks like. You can see off to the left is a cartridge, and then you have a cutaway view where it shows the fuse is blown. You can have double protection, where you protect X and Y circuit breakers, or B bus protection, and you can also protect A bus protection. So the basic idea here is the current that goes into the circuit from CT 1, 2, 3, 4 to X has to be the same as the current flowing out through circuit breaker Y, CT 4, 3, 2, 1. If it's not the same, then there's a fault inside there. So is the fault between what? What bus? Is it between bus B protection or bus A protection? So these are your differential type double protection zones. Here's a zone protection, right? So you look at zone H2, bus zone H1, bus zone H3. So each relay or protective zone has to be carefully thought out. Transformer T1 is protected by zone T1. You have overlap, where you have zone T1 overlaps bus zone H1. It overlaps bus zone L1. You have a generator zone G1. So depending on where the CTs are located, you have different protective zones. Breaker failure minimizes the amount of equipment removed from service in the event of a failure. Failure determination: not started, opening in a certain time. You told it to open, but it didn't open at a certain time. Not open in a certain time. Current not broken in a certain time. So you have duplicate protection schemes. You have protection A, you have your PT, and you have your CT. You have protection B, you have your CT and PT. So they're duplicate. You can see that they're duplicate schemes here. You have initiate, You have trip, you have close. If you initiated, then action Q should happen. B should also happen. See, B is the same thing. It has the same CTs, it has the same PTs. So it's truly a duplicate protection scheme. It's a backup. That's what that's for. Why would you even need a duplicate protection scheme? It might be so important that that breaker opens that it warrants that for like a nuclear facility or something like that. You have different types of bus protection. You have overcurrent, you have differential bus protection, which is an 87B. You have backup protection, you have undervoltage protection. Overcurrent relays, what happens is you get that CT. Current flows in the primary side through the donut, just like we talked about, 2005 amps, goes out the dot side. So it goes in, goes out. So the secondary is 5 amps. When it hits a certain value, it energizes that coil and causes it to close. When it closes, it has an overcurrent situation. So if you were to walk up to an electromechanical relay and you saw that little dial turning, it's fixing to energize. It ain't going to turn very long. It should not be turning. Differential protection. Again, the current going in must be the current going out. So I equals 1P equals 2P, right? So if you look here, you got I 1P has to equal I 2P. If it's not, there's a fault inside there. So the idea is you have a 87B here, differential protection. You're protecting bus H1 between X and Y circuit breakers. So if the current flowing in is the same as the current flowing out, then the currents cancel and there's no voltage across that residual current coil. But if there's a fault, then the current circulates one opposite directions in the CT circuits, which causes it to activate. Otherwise, the currents all flow the same direction. If all the currents flow in the same direction, then there's no, they cancel each other out, right? So here's a fault condition. So they're traveling in opposite conditions, right? You can see the fault is at bus H1. Here's another example of a differential bus scheme. Here's a bus protective scheme. These are complicated schemes. It's a little easier with with the solid state or microprocessor based relays, but it can get very difficult. And so you want to make sure you understand exactly what's going on. If you are asked to work on one of these switchgear lineups, you need to understand the relaying schemes involved. And you want to make sure you don't mess up any of this. You could inadvertently disconnect a contactor or a lockout relay, an 86B, right? Lockout relay contact, and disrupt one of these zone protections. So here you have your backup relay and your differential relay. So you use the same CT and you've got that overcurrent backup relay, and then you've got your differential relay. Here's your bus under voltage protection. And your bus protection over current, differential, backup, and under voltage. Next we'll look at transformer protection. Transformer protection, you have to have instantaneous protection, differential protection, gas protection, thermal overload protection, and ground detection. Obviously, when you close the circuit breaker on a transformer, you're going to have high magnetizing inrush currents. Ratio mismatch with CTs aggravate by tap changers. Phase shifts. Transformers are affected by overfluxing and affected by overtemperature. Here's a transformer zone. So you got your transformer in the middle. You got A transformer protection. You got B transformer protection. So you got backup protection schemes. These are 87Ts is what they call them. Works just like bus differential protection. Again, the current flowing in must equal the current flowing out. If it doesn't equal, there's a fault inside the middle of it. So this is an 87T differential, transformer differential circuit. This is a typical transformer from taps. This is what an old electromechanical relay looks like. Very, very robust relays, by the way. It's a gas relay, a winding temperature relay, a ground fault protection relay, motor protection, service factor. If you have a 10 horsepower motor with a service factor of 1.15, then it can run at a maximum continuous output of 11.5 horsepower. It's rated for it. Motor protection summary, you've got instantaneous overcurrent, you got stall protection, thermal overload, phase unbalance, and grounds. You have an inverse time relay. This is what that inverse time relay looks like. It's an old electromechanical relay, like a GE or an ABB. Here you have an overload. You got your supply, you got your heater in, your bimetallic element. If the bimetallic element senses the heat and it hits a certain temperature, it activates, and it causes it to hit that little relay actuator there and go to the trip contact. Once it trips, it opens. Then a target pops up. You can see why it tripped. Ground fault protection. If you put a CT around all three phases, A, B, and C, technically there should be no current. The only time there would be a current there is if one leg goes to ground. So if that motor, one of the phases goes to ground and there's a serious imbalance in that current, then that zero sequence CT, that's what they call that when you wrap all three phases around like that, it's a zero sequence CT. If it sees that, then it'll trip on ground fault. Single phase to ground protection. You could individually look at each phase, and this is a 6 winding motor here, or 6 lead motor. You got A, and what comes in must come out. It should be 0, right? It should subtract from each other and should be 0. If one of these is not 0, that means there's a fault to ground. And that protects against a stall, right? Thermal overload and phase unbalance. So here you got your A, B, and C. You've got your heater element, your bimetallic element, and your heat shield. You got your phase unbalance contacts. You got your load indicating scale. You got your trip circuit and your overload contacts, and you got your ambient temperature compensating bimetallic element. So it has to compensate for high ambient or low ambient temperatures because it's going off of that bimetallic strip element. If it doesn't compensate for the temperature swings, then it's a false trip. Of course, with microprocessor relays, you don't have to worry about any of this, right? So here's a diagram of the unit. You got your heater, phase unbalance contacts, rotation element, your lead indicating pointer, your adjustment overhead contact. These electromechanical relays are just phenomenal. Whoever designed them originally was just super smart. Here's an MCC bucket, right? A motor starter bucket. You got your CPT, your contactor, your overload. There's a complete bucket, and you can just push it right into like one of those little spots, into those little space, MCC bucket spaces. Here's a, looks like a differential relay. So you got your time setting, your percent load for alarm, percent running load, your instantaneous overcurrent, and your ground fault current. Oh, so this is like a motor protective relay, a big old electromechanical motor protective relay. So your summary, you've got instantaneous overcurrent, stall protection, thermal overload, phase unbalance, and grounds. You know, obviously you wouldn't put a fancy relay like that on any motor. It'd have to be a fairly large motor. pretty cheap now. You can get an SEL 710 for like, I don't know, less than $2,000, and you can get all this protection. Generator protection. You got classes of turbine generator trips. You got your Class A trip generator breaker, field breaker, and turbine. Electrical trips before the output breaker. Class B trip generator output, but leave it supplying station service. Electrical faults in the switch yard. So Class A is trip generator breaker, field breaker, and turbine. Electrical trips before the output breakers. Class B is trip generator output, but leave it supplying the station service. Electrical faults in the station. Class C is you have an overexcitation, high volts per hertz, only used when generator is isolated from the grid. And Class D is trip turbine, trip generator after motoring is detected. Mechanical trip turbine trips high condenser pressure. There's a lot of things associated with generator protection. You got overcurrent, overload, differential, split phase differential, ground, rotor ground, phase unbalance, low field, under frequency, out of step, and reverse power. So here you got a healthy phase. You can see the current flows. And you got a faulted phase. The current reverses. And you've got an open circuit in the phase. You only have one current flowing. Differential protection. You got your generator 1. Current flowing in must be the current flowing out. If it's not, there's a fault in that generator. Ground fault protection. They usually put a reactor on the neutral side of it. The reason they have to have that ground fault protection device in there is because usually those generators' stator windings can't withstand the fault. So they put a reactor in series with it like that. Rotor ground fault. So they look at the field winding. They look at the exciter. They put a current limiting resistor in there, a sensitivity ground fault detection relay with a bridge and the auxiliary AC supply. Over other protections, phase unbalanced, loss of field, under frequency, out of step. Reverse power. Reverse power is like a 32. You don't want utility to drive the generator. You want the generator to push power out, not be pushed in. Relays misspelled. Generator protection, overcurrent, overload, differential, split phase, differential, ground, rotor ground, phase unbalance, low field, and under frequency, out of step, and reverse power. A lot of things to consider when you're doing generator protective schemes. What we'll do is we'll move into basic process control. So far we've talked about some of the components that you use to build a control panel, and we talked about the PLCs that you might put in a PLC control panel. Something you want to know about basic process control is because what you're doing is building a control panel to control some type of process, be it a motor starter starting and stopping, or some type of a total, an actual closed loop type process control. Table of contents, we'll go over an introduction. We'll do process disturbances, control terminology, feedback control, feed forward control, and then process dynamics. What you have is process and control variables. You have manual control systems, like somebody would get in there and turn something on or off. You have automatic control systems, so based on some feedback, the system would automatically fill up a tank, let's say, and then allow it to drain back down and then fill it back up. You have closed loop and open loop process control systems. Your HVA system on your house is pretty much an open loop process, whereas a closed loop process would be some continuous feedback where you would just automatically adjust each time and try to maintain a certain set point. Process and control variables. Instrumentation provides the various indications used to operate a facility. In some cases, operators record these indications for use in a day-to-day operation of the facility. The information recorded helps the operator evaluate the current condition of the system and take actions if the conditions are not as expected. So when you make a control panel, you're going to have instrumentation that connects to that control panel directly to the PLC, and these operators could technically go out there and record all this data, or you could bring it all into the PLC control panel and store it into a historian type PC, a CPU or something. Requiring the operator to take all of the required corrective actions is impractical, especially if the system is fairly complicated, or sometimes impossible, especially if a large number of indicators must be monitored. So if you're trying to measure temperatures, on a rotor or a generator, you might have 6 RTD temperatures coming in, and then you might have 2 bearings, the front end bearing, the rear end bearing, and then you might also have all the voltage values and all the current values, and it's impractical for somebody to try and predict when they should shut the generator down, or when they should open a control valve or something like that. For this reason, most systems are controlled automatically once they are operated under normal conditions. Automatic controls greatly reduce the burden on the operator and make his or her job manageable. Process variables requiring control in a system include, but are not limited to, flow, level, temperature, and pressure. So we'll go into great detail on different types of flow transmitters or flow measurements, level measurements, temperature, and pressure. So if you've got a pump, they might be controlling the pump based on flow, or they might be trying to control the pump based on some level, tank level. Some systems do not require all their process variables to be controlled. One example of a system that doesn't need to be continuously controlled is the central HVAC system, or central heating system. A basic heating system operates on temperature and disregards the other atmospheric parameters of the house. The thermostat monitors the temperature of the house. When the temperature drops to a value selected by the occupant of the house, the thermostat, the temperature activates to raise the temperature of the house. When the temperature reaches the desired value, the system just turns off. So it's not continuously running, it's just an on-off type system. And so let's just say that the temperature outside drops significantly, really fast, or raises real high. It takes a while for your system to catch up because it's doing an on-off type situation. It might stay on too long or stay off too long. Automatic control systems neither replace nor relieve the operator of the responsibility for maintaining the facility. The operation of the control systems is periodically checked to verify proper operation. If a control system fails, the operator must be able to take over and control the process manually. So the operators need to understand exactly how the process works in case that control system fails. If you've got a bad transmitter or feedback loop and the system starts to run out of control, the operator has to quickly put it in manual and manually control it. In most cases, understanding how the control system works aids the operator in determining if the system is operating properly and which actions are required to maintain the system in a safe operating condition. A control system is a system of integrated elements whose function is to maintain a process variable at a desired value or within a desired range of values. The control system monitors a process variable or variables, then causes some action to occur to maintain the desired system parameter. And we'll talk about closed loop feedback loops and different, the output of the control loop, the feedback of the loop, the summing junction, the set point, things of that nature to talk about a control system. In the example of the central heating unit, the system monitors the temperature of the house using a thermostat. When the temperature of the house drops to a preset value, the furnace turns on, providing a heat source. The temperature of the house increases until the switch in the thermostat causes the furnace to turn off. Two terms which help define a control system are input and output. Control system input is the stimulus applied to a control system from an external source to produce a specified response from the control system. In the case of the central heating unit, the control system input is the temperature of the house as monitored by the thermostat. Control system output is the actual response maintained from a control system. In the example above, the temperature dropping to a preset value on the thermostat causes the furnace to turn on, providing heat to raise the temperature of the house. In the case of facilities, the input and output are defined by the purpose of the control system. A knowledge of the input and output of the control system enables the components of the system to be identified. A control system may have more than one input or output. An example of a simple manual control system is operator watching the level of a tank. If the level drops, the operator opens the water supply valve until the level is then where the operator wanted it. The key is that the valve or level is not automatically controlled. The operator must manually correct the process, the tank level. Closed loop process control systems and open loop process control systems. Control systems are classified by the control action, which is the quantity responsible for activating the control system to produce the output. The two general classifications are open loop and closed loop control systems. An open loop control system, so you can see a figure here where you have a chemical pump, the pump speed controller, and then the chemical storage tank. So an open loop control system is one in which the control action is independent of the output. So there's not a closed loop. They're not all tied together here. An example of an open loop control system is a chemical addition pump with a variable speed control. The feed rate of the chemicals that maintain proper chemistry of the system is determined by the operator, who is not part of the control system. If the chemistry of the system changes, the pump cannot respond by adjusting its feed rate, speed, without operator action. So here they have a tank full of chemicals, and they increase and decrease the speed of the pump to provide injection into the system. But the operator has to measure the chemicals in the system to understand if he needs to increase or decrease the speed of the pump. A closed loop control system is one in which control action is dependent on the output. Take a look at this flow control, this tank level. So here you have a closed loop system. You have a tank full of water. You have a level transmitter. LT is level transmitter. It provides some level signal, could be a 4 to 20 milliamp signal, 0 to 5 volt DC signal to your level controller. Then the level controller gives you an output signal, and it just simply turns the level control valve on or off. That level control valve could be on or off, or it could be a valve that actually modulates open and closed, right? So it could slowly open and close, and you could come to a desired set point. Might be 55% open or 75% open. So in this figure 2 shows an example of a closed loop control system. The control system maintains water level in the storage tank. The system performs this test by continuously sensing the level in the tank and adjusting a supply valve to add more or less water in the tank. The desired level is preset by an operator, so it's not part of the system. So where the water is going is called demand by the system. So some water is being used by the whole process. And so the function of this little one control loop is just to maintain tank level. Feedback is information in a closed loop. Figure 3, feedback is a closed loop control system about the condition of the process variable. So here's figure 3. You have your process water storage tank. Your feedback, actual tank level, goes into the control system. You have a set point, which is your desired tank level, and this is like a summing junction, right? So if one is greater than the other, then it either takes a positive or negative output on the output of the system and provides your corrective action, your control signal to the level control valve. So again, that can be an on-off situation where the valve is on or off, or it can be a 4 to 20 milliamp analog signal so that it actually modulates the control valve. Automatic control systems, this variable is compared with a desired condition to produce the proper control action on the process. Information is continually fed back to the control system in response to control action. In the previous example, the actual storage tank water level sensed by the level transmitter is a feedback to the level controller. This feedback is compared with the desired level to produce the required control action that will position the level control as needed to maintain the desired level. So again, we show that closed loop. You can see it's completely closed. If for some reason the transmitter fails, then this loop fails, and then somebody has to come in, like the operator has to come in and override and put it in a manual system or manual mode and control the tank the old-fashioned way, manually. An automatic control system is a preset closed-loop system that requires no operator action. This assumes the process remains in the normal range of the control system. An automatic control system has two process variables associated with it, a controlled variable and a manipulated variable. Going back up to the assumes the process remains in the normal range for the control system, what you do is you have different alarm conditions, right? So if you hit a high or high, a high might be alarm. So if you have a high tank level, you say, oh, there's an alarm that might tell an operator, hey, there's something wrong with this system. For some reason, it's getting to a high level. If it gets to a high level, you might want to just shut the thing down, the system down. You could have a low level as well. So a low level would notify the operator that it's a problem. A low level would say, hey, there's really a problem here. We can't maintain the tank level, shut it down. If you run a pump without fluid in it, if it's a centrifugal pump, you could burn that pump up. A control variable is the process variable that is maintained at a specified value or within a specified range. In the previous example, the storage tank level is the control variable. A manipulated variable is the process variable that is acted on by the control system to maintain the control variable at the specified value or within the specified range. In the previous example, the flow rate of water supplies the tank is the manipulated variable. In any automatic control system, the four basic functions that occur are measurement, comparison, computation, and correction. So in the water tank level control system in the example above, the level transmitter measures the level within the tank. The level transmitter sends a signal representing the tank level to the level control device, where it is compared to the desired tank level. The level control device then computes how far to open the supply valve to correct any difference between the actual and desired tank levels. Three functional elements needed to perform the function of an automatic control system are a measuring element, an error detection element, and a final control element. So in a PLC type control system, the measuring element, the level transmitter would go directly to the PLC input card. The error detection element would be a PID instruction inside the PLC card, inside the CPU you program. And then the final control element would be the output card as well as the valve itself. So here's a relationship between these elements and the functions they perform in an automatic control system. So here you have in the far left you have your input, and then on your far right you have your output. And so your input goes to your final control element. Then you got your process, you have disturbances, you got the levels changing and what have you. Goes back around your feedback loop to your measuring element, to your error detection, your desired value, and then back to your final control element. So that's a complete closed loop feedback system. I guess I just threw this in there so you can see a better view of it. The measuring element performs a measuring function by sensing and evaluating the controlled variable. The error detection element first compares the value of the controlled variable to the desired value. The desired value would be your set point, and then signals an error if a deviation exists between the actual and desired values. So this is like a summing junction. The final control element responds to the error signal by correcting the manipulated variable of the process. And then that's your total relationship again. And it just keeps going over and over. An automatic controller is an error-sensitive, self-correcting device. It takes a signal from the process and feeds it back into the process. Therefore, closed-loop control is referred to as a feedback control. Summary: a control system is a system of integrated elements whose function is to maintain a process variable at a desired value or within a desired range of values. Control system input is the stimulus applied to a control system from an external source to produce a specified response from the control system. Control system output is the actual response obtained from a control system. An open loop control system is one in which the control action is independent of the output. A closed loop control system is one in which control action is dependent on the output. Feedback is information in a closed loop control system about the condition of the process variable. A controlled variable is the process variable that is maintained at a specified value or within a specified range. Control system input is a stimulus applied to a control system from an external source to produce a specified response from the control system. Process disturbance. You have a set point and steady state, you have process disturbance, and then you have control system reaction to a process disturbance. Set point and steady state, process disturbance, and then control system reaction to a process disturbance. Some of the terminology you'll need to know on control systems is the set point, the steady state, the error, the derivative, cycle, cycling, cycling life, control point, offset, and hunting. You got feed forward control, so you have manual feed forward control or automatic feed forward control. In process dynamics, you have your process characteristics, you have your resistance, capacitance, dead time, process response curves, and process control response. Protection of the electrical system. All electrical systems have the common purpose of providing electrical energy to the utilization equipment as safely and reliably as economically feasible. So, just like when we talk about control panels and the circuit breakers and the fuses and all the safety equipment in there, each process loop or process control loop has a safety feature as well, because if you're not aware of your process and you abruptly change the output of a motor, it could affect the process and create a hazardous condition for operators or for personnel in the field. So you need to understand your process. Again, obviously UL or IEC is not going to go through and explain all the control systems to you. The reason I do it is just for introduction purposes, so that you're aware that a lot of these control panels that you make are tied inherently to a process, and you need to understand these terms so that you can be designing better control panels. So again, we're going to hash over the basic process control. We talked about the inflow to a tank, the level controlled variable in the pump, and then the overflow. Closed loop automatic control, open loop manual control, and person takes the place of the controller. So in a manual control, believe it or not, I shipped a unit out to Brazil on a rig, and they actually had one guy in charge of maintaining the tank level, and that's all he did was just increase and decrease the valve. I thought it was really odd, because all they had to do is throw it in automatic and they wouldn't have to worry about it. Feedback control. You have your set point, goes to a comparator, generates an error, so it has the set point minus the measurement signal, goes to an amplifier, which drives a manipulated variable, which goes to the process tank. You have disturbances, and then you have your output variable. Back to your process sensor, back to your comparator. So you have a complete closed loop feedback system here. Feedback control action after an error exists. So when you have a feedback, or you say feedback, you are making a control action after the error exists. So the disturbance occurs, maybe the tank drops in level, then you make action, you make a control action. feed forward is reacting to the disturbance before the error occurs. So you look at the error, you know about it, and you go ahead and act on it. So there's two different ways of doing this. Typical on-off control system is here you have an electrically operated solenoid valve. It can be either open or closed, on or off, right? So if P1 closes, the solenoid valve energizes and opens, and then P1 opens at L2. So what they're telling you is that when it hits to L1, P1 closes so that you're going to fill the tank back up. Your desired set point is between L1 and L2, level 1 and level 2. And then your output is going out, Q out. Q in is just more liquid into that tank. And all you're trying to do is maintain that level between L1 and L2. Obviously, it's going to cycle. It's going to go on and off, right? So you're going to have a periodic control where you're cycling that valve on and off. It's kind of hard on things when you do that, but just the nature of an on-off control system. So here's a typical on-off response. Your set point is in the middle. Then you've got L2, your level 2 set point, your level 1 set point. So whenever it hits the level 1, you're going to fill back up, right? And then you're going to hit the level 2, you're going to turn back off, and you're going to cycle. Sinusoidal cycle time. So that's called your periodic time. You can have proportional control. So here, if you have true level control of an open tank and you have a modulated control valve, here you have this is 20 to 100 kilopascals. So basically what you're doing is you're looking at the level transmitter. So you've got a signal coming out of the level transmitter and you're modulating that valve open and closed. So now you're able to actually set a set point and you're actually able to try and fine tune the valve's position so that you hit the optimum value so you don't have that cycling. So here's a simple proportional system. You get your inflow comes in. You've got a pivot like a toilet bowl. This would be a good example of a toilet bowl. So you can see the float valve as it comes down, it allows more liquid to add to the tank, and then as it comes up, it stops the liquid. So here's an open tank control. So we have the level transmitter, we have a level indicating control, and then we have our analog output, our valve. And this is your control action. You have direct action or reverse action. So in the direct action, still the same setup right here, but you have your A/C. And then you got your reverse on the bottom. So here's a proportional control. These circles with the X's through are summing junctions. And so basically they're like little comparators, right? So you've got your set point comes in, and that's like an adjustment on a knob, or somebody adjusts an input, could be a touch screen. You've got your measurement value. The difference between those becomes your error. That goes into the KE symbol. That's your control section there. And then you have another summing junction that says, look at your bias, look at your output, or your control action, your proportional control. K is proportional. And then you have your output. So your formula for that is M equals K times SP minus M, right? Plus your bias. Proportional band and gain. The proportional band, the input change required to change the output 100%, is called a proportional band. So you got your change in output divided by the change in input is your gain. So gain equals 100% of proportional band. Narrow, wide, high, and low. So you have a wide proportional band, low gain, or a narrow proportional band, high gain. A little illustration of how that would work. Here's a proportional control response curve. So you've got your level original set point. You got your output flow, your input flow. You've got your time. So your input and output. New mass balance occurs here. And then you've got your offset. There's a lot of variables associated with this. And really, hopefully what I've done here is just kind of got you introduced to these topics and so that when you're designing a control panel, you can start asking more questions about what it's actually controlling so that you understand all the details. The proportional response with narrow proportional band, and that would give you your level or set point. So you can see what's happening is your desired set point can never actually be attained, right? So you've got that offset associated with it. And so you can never quite get there. Response versus PB proportional control only. So here you have a step disturbance at the top. You're going along, everything's fine, and then boom, they've got a step disturbance, right? So your set point, your wide PB, if you have wide proportional band, it would fall off right there, and then you'd have an offset. If you have a moderate proportional band, it would cycle, it would oscillate, and then it would set down, go to an offset. If you have a narrow proportional band, it would just oscillate and never come back to the proper setting. So that's kind of an interesting control response, right? Quarter to decay response curve. So here you have a disturbance, right? Your system response. So you have A, and then you have quarter of A, and then you have 1/16 of A. If you were able to measure this, you could actually make decisions based on this. So the next thing, so far we've only talked about proportional control. The next thing to talk about would be reset or integral, because what we're describing is a PID, proportional integral derivative, right? So with just a true proportional control, you will never be able to close that offset. You need to get rid of the offset. Reset or integral. So if we have response curve with proportional control only, we've talked about this, you have your step disturbance here, and then your set point, and then your response kind of oscillates a little bit, and then it settles down. Well, it settles down, but it never quite gets back to the set point, to the desired value. It's always below it. Additional control signal restores process to the set point. So if you if you have that reset action right there, then when your set point drops and then it comes back up, then you remove your offset removed. So by adding the integral action, which is the integration, you can actually remove that offset. Now we have your integral action. So before we had just the KE, the proportional control. Now we have the integral control. We call this a PI controller. The integral is above the KE. So again, you have your set point, goes to the summing junction. Your measurement value comes to the summing junction, generates an error. The error goes to the proportional controller, and then it sends a signal to the integral controller, or formula or module, and then the output of that goes to the actual final summing junction. You have your proportional coming in, you've got your integral coming in, you've got your bias coming in, and then you have your output. So again, this is a complete PI control loop. Units, we have to go over the units, is minutes per repeat, or MPR, the length of time that it will take the integrator to add an amount equal to the proportional response. You have repeats per minute, or RPM, the number of times a proportional response is repeated in 1 minute. Proportional plus reset, or PI, open loop response. So here you have your error, you have a disturbance, and what happens is you have the KE response, proportional response. If you have a fast reset, a normal reset, or a slow reset, this would be the angle of the response. So if you have a fast integral, a normal integral, or a slow integral time. You also have your reset windup, or instability because of a lag. So that concludes the PI Now what we could have is just a PD or a PID, a combination of them all. The rate or derivative. You had your proportional derivative open loop control. So here we add a derivative control. So you have your input, you have a change in the input, and then you have your output responds to it. You have a derivative, so the derivative actually acts before, and then you have your proportional action, and then your derivative ceases as the error stops changing. So whenever the error is changing, the derivative is changing. This is what a derivative control would look like. Again, you've got your proportional in the middle, you've got your integral on the top, and then you've got your derivative on the bottom. That's a complete PID control symbol. Still have your set point, summing junction on the far left, set point goes, and then you got your measurement coming in, you've got an error signal. The error signal goes to the proportional signal sends it out to the integral and also to the derivative. These three PID outputs are summed together, which go to another summing junction to your bias and then finally to your output. For a simple flow control system, here they're showing an orifice plate, if you will, a flow control, and you have your control valve, you get your flow control, and you get your flow transmitter. And you see that square root sign? The square root is required to correct for the flow calculation. The open loop responsive proportional plus derivative PD action to rapidly changing. So here you have a process starting at T0 to T1 to T2. You have a rapid change in the error signal. So you can kind of see at the chart what's happening. You've got your rate action A to B. When you have that A to B change, that's what happens on the control signal. And then you've got your proportional action from A to B, so it ramps up slowly. Then you've got your rate action due to the cessation of the increase in E, the error. When the error changes, you have that derivative kicking in. And then you got your rate action, so it drops below. And then you got proportional action again. You got rate action again due to the cessation of increase in E. And then finally your control signal stables out or steadies out. Large system under proportional and proportional plus derivative control. So here you have your set point. It dips. So you got proportional plus derivative. If the dotted line is just proportional only, right? So if you have proportional plus derivative, it's a little better. You can see it rises up, it comes back down, and starts to steady out. So the only thing that you're missing here is your actual integral, right? So your reset. Multiple control modes. Virtually all controls have a proportional response. Integral and derivative are added to improve performance. Majority have proportional and integral. A PI control loop is about the easiest to set up. And the way you set this up is you set the derivative, and the integral to 0, or as close to 0 as you can. You start increasing the P until you get some oscillation, until it actually oscillates, like you saw in the earlier slides. Once you see it oscillating, you cut that value in half. Let's say it oscillates at 10. So you set it at 5. Then what you do is you say, okay, now my new set point or my proportional value is 5. So I'll add 2.5 of integral. And that's probably the easiest way to set a control loop. And just leave the D out of it. Rarely do you ever need D. This type of PI control and that method of tuning that loop, what I just described, works on just about every controller. Some typical heat exchangers have derivative added, but they're real rare. I rarely see a requirement for derivative. Open tank level control with valve and inflow. So here you got your valve, you got your level transmitter, you got your level indicating control, you've got your set point. That level indicating control is actually where your derivative, your actual PI controller resides. So it actually has the set point, the derivative, the set point, and the integral values in it. And so you just have a closed loop. Typical flow control loop. So now when you're looking at, some people call them P&IDs, piping and instrumentation drawings. Some people call them flow diagrams. Some people call them MF drawings, which is just a flow drawing. You can actually read you can communicate with them by looking at their flow diagrams. So when you look at this, you know that they have a flow transmitter, they have a flow indicating control system, they have some set point, they have an analog out. You could replace that FIC control loop right there with a PLC. So you could take the flow transmitter input and you could take and bring that into the input of your PLC, and then you could take the output of your PLC and analog output card and control that flow valve, and then you could create a PID loop inside your PLC control panel. Pressure control, constant bleed. So these are more pneumatic type things, right? So they got a constant bleed, so they're always just letting certain pressure off of that pressure valve. What's it closed? You got a split range feed and bleed pressure control valve. Pressure transmitter at the top. Got your pressure your PIC controller. Got your set point. You got two control valves. You got an inlet control valve and an outlet control valve. So the desired thing to do here is to control the pressure in that pressure vessel. Here you have a hot bleed cold service water heat exchanger. So you got cold water coming in, you've got hot bleed coming in, hot water coming in, and then you've got your cold bleed water coming out. You're looking at the temperature transmitter. The TT is temperature transmitter, goes to a TC, temperature controller. You've got some desired set point, and then you've got your automatic control valve on the top. So you adjust how much cold water you run across that heat exchanger. And just as they pointed out before, in a heat exchanger, you might add some D, right? So if you start seeing some error, you might want to react to that a little bit quicker. Okay, so next thing we're going to do is we're going to just talk a little bit about pressure measurement. Then we'll talk about temperature measurements, level transmitters, things like that. And then we'll get back into the UL508A material and the IC material. These are different types of pressure measurement devices. Pressure, you can think of it as a scale, right? You have the absolute scale or you have the gauge scale. So you need to understand what you're measuring against. Here you have a type of tube that measures the actual pressure and allows you to measure it. There's a tube gauge. You can see in the back side of that, you can actually see that tube and how it causes that gauge to change. There's instrumentation shops that repair these and work on them, and you always want to get them calibrated by an approved instrumentation shop. Here's some different shaped tubes for different instruments and different gauges. You can have bellows where the pressure is actually pushing up on a bellow and that motion is measured. So here's different types of gauges, the bellow gauges. You have a diaphragm in there, so the pressure is pushing up on the diaphragm and it deflects and it changes that motion, right? Like a strain gauge. Here's a diaphragm differential gauge. Here's a switch, pressure switch. You'd use a pressure switch for like a high pressure set point or low pressure set point. Here's a capsule. You've got your continuous seam. The pressure comes in, pushes on that flexible membrane, and then you get some motion. It's not a very good picture, but it's another capsule picture. A differential pressure cell. You get your high pressure in the one side and your low pressure on the other side. And what you're doing is the silicone oil filled diaphragm there, the metal diaphragm, actually moves, and that movement causes that force bar to move. And then you've got a detector that gives you a 4 to 20 milliamp signal output. This is what you primarily see a Rosemont or there's just a bunch of different people that make these transmitters. But here's a pressure transmitter, and this thing is, you usually can have all kinds of different controls like heart control and communication protocols. and it'll give you a 4 to 20 milliamp signal output. Extremely accurate devices. Here's a pressure transmitter installation. You got your control pressure valve, got your isolation valve, you go to an impulse line, goes to your pressure transmitter, you're vented, and then you get a 4 to 20 milliamp signal input to your analog input card on your PLC. Here's what a strain gauge would look like. Again, you've got your area, and your cross-sectional area decreases as you put pressure on it. Therefore, the resistance in ohms increases. So when you have a strain gauge, that's what it's doing. It's actually looking at the pressure or the displacement of that media. Here's a strain gauge DP cell. You got liquid fill, process steel diaphragm, sensing capsular element, your overpressure stop, your strain gauge, your compensation circuit board, and your electric amplifier. There's also capacitance type cells, right? Where you can actually measure the pressure by a capacitance cell. Operating environments, certainly you want to understand the vibration, the temperature, and the vapor content. Failures and abnormalities. You could have an overpressure that could cause an instrument to fail. You could have a blocked sensing lines. You could have leaking sensing lines and loss of electrical power. So knowing what the failures and abnormalities are, you need to design into your system a way to say, hey, if I lose my 4 to 20 milliamp signal, if it goes below 4 milliamps, there's transmitter trouble. And we need to alert them on that, because you don't want to lose a protective scheme, right? You don't want to lose the ability to detect pressure. Flow measurements. So before we talked about pressure, now we'll talk about flow. So there's many methods of flow measurements. The Bernoulli's equation, a statement of energy conservation, is the main one. And this is where you have one of those Daniel orifice plate tubes, big differential tubes. So here you have a flange connection, and you've got some orifice plate in the middle. And you can see that the pointed side of the orifice plate is on the high side, and then the flared side is on the low side. And so it actually creates a differential pressure across that orifice plate. And so as the gas flows through it, you need to know what kind of liquid it is, or gas, or whatever it is. And then from there, you can calculate the flow of gas. So the problem is you usually have a high loss, high pressure associated with this. So here you have an orifice plate, and you've got your high pressure sensing line and your low pressure sensing line. And there's that sharp edge in the bevel of the orifice plate. You need to go in there every once in a while and pull these apart and calibrate them. Typical orifice plates. Here's beveled edge on the orifice plate. Here's a typical transmitter installation, where you have your flow coming through, goes to the orifice plate. You've got a high and a low pressure point. A differential pressure is basically what it is. So this would be a DP, a differential pressure transmitter, DPT. And then you've got your equalized valve. You've got your high pressure block valve. Usually the equalized valve and the high pressure valve, and those two high pressure and isolating valves, and it's all part of a manifold. And then you got your actual flow transmitter at the bottom. Flange taps. Avenia contractia taps. So they're telling you that it needs to be 1 times the diameter, usually 1/2 times the diameter. Pros and cons of Daniel's meter tube is a high delta P, lots of data, low cost, easy replacements, high pressure loss, and erosion. So your cons are high pressure loss and erosion. Your pros are high delta P, lots of data, low cost, and easy replacement. You have a Venturi tube, and a Venturi tube is similar to an orifice plate, but the problem is it's not as accurate, right? And it'll slowly kind of just erode, right? So you have high pressure and low pressure. You got your flow nozzle. You can have elbow taps. PID tube is another type of method of measuring flow. So you see the flow at the top, and as it goes around it, it actually has a low pressure at the bottom and a high pressure on the other side. You can have an annubar. An annubar works real nice. So you have your, it's actually a tube, like a tube with different holes in it. And so what happens is the velocity profile comes flying by this, right? And it actually puts a high pressure and a low pressure, and it causes that differential change on that annubar. So by looking at this with a differential pressure transmitter, you can determine the flow of that gas or whatever it is you're looking at, or air or whatever. This is what an annubar would look like. Here's another view of it. Here's one where you could slide it into a pipe, bolt it down. Here's another annubar. Here's an output of the transmitter, delta P. So you have these two points where you're looking at it as a DP. So you've got a flow transmitter. So if you look both the high pressure and the low pressure side, and it's calibrated, you'll know exactly what the flow is in that pipe. You got your square root extractor. Remember that square root sign we saw earlier? So it's not a perfect linear signal there. So at 100%, you get 20 milliamps. 86.8% is 17.66 milliamps. 70.76% is 15.3 milliamps. And then you got 50.6% is 12 milliamps. You can see the input from the flow transmitter versus the output of the actual transmitter. This would be a flow loop with a square root extractor. So if you had your flow transmitter, high pressure, low pressure, just like we did, and we sent that forward to 20 milliamp signal, send it through a square root extractor, and then you would get your 20 milliamp signal output. Gives you a graph of your square root extractor. The output equals the square root of the input. Could have a cutoff relay, cutoff point, square root curve, low end. So it's linear. So 0.5 to 1 is a very linear curve right there. See that? But anything below that is nonlinear. Effective process conditions. Flow measurements are inferential. Pressure, measure a pressure drop and infer a flow. Effect by density of the fluid. So you need to know what kind of fluid you're pumping, right? And there's things like bubbles and things like that can mess up your flow. You need to know the temperature, you need to know the pressure, you need to know the increasing density increases the indication of flow rate. So if the temperature increases or decreases, the density of the liquid can actually change as well. Density compensation. So you can put an RTD out there. You can have a differential pressure cell. You can look at your low pressure sensing line and your high pressure sensing line and your pressure cell. And by measuring the temperature and measuring these different values, you can actually compensate for the density changes based on temperature. Flow measurement errors, you have erosion, overranging the DP cell, vapor formation in the throat, clogging, plugged or leaked impulse lines. Next we have the level measurement. We're almost through with this, and again, the point of showing you all these symbols and transmitters and theory is so that you can have a better appreciation for how a control panel works and not just worry about, fully understand it and make a better control panel. So when you have inferential level measurement, you have the liquid density and the height of the liquid, and then you've got your pressure gauge at the bottom of it. So your density times gravity times the height is your pressure, or your level. So you're actually measuring the liquid level with a pressure gauge. Three valve manifold, you have your process high pressure side, you've got your process low pressure side, and you've got your three valves, and then you've got your level transmitter. So the output of the level transmitter would be a 4 to 20 milliamp signal. That three valve manifold is something you would buy, and it comes in as little handles on it as a block of stainless steel or different types of metal. Open tank measurement, you have atmospheric pressure pressing on top. You've got your liquid of the weight density, the height of the tank. You've got your isolation valve, and then you get your level transmitter. And then you've got your low pressure is vented to atmosphere. So from there you can actually measure the pressure of the height times the density times the gravity gives you your pressure, and then you can compare between your high pressure and your low pressure. So you basically, on an open tank level measurement, you have a differential pressure transmitter. Closed tank level measurement, you got your pressure on the top, and it can change. So if that tank fills, that pressure can increase, right? So you need to know what the low pressure impulse line looks like. You need to know at the bottom of the tank the actual height of the liquid, and goes to your level transmitter. You can have a dry leg system. So you got your isolation valve at the top, you got your isolation valve at the bottom, you've got your three valve manifold, you got your high pressure, your low pressure on the manifold side, you got your isolating valve, normally open, a knockout pot, and then a drain valve, which is normally checked or closed. A wet leg. So here on the wet leg, so that's a lot of work to build something for a tank level. Isolating valve at the top, isolating valve 1, slope towards the main tank. You've got your bottom valve, your isolating valve at the bottom. You've got your three valve manifold. Again, you got your level transmitter, DP, high and low pressure. And then you've got your drain valve, your steam or electric heating line. You want to make sure that line doesn't freeze up on you. And then you've got your pressure release valve at the top. So that's called the wet leg as opposed to the dry leg. Zero suppression. So here you just at the tank level, an isolation valve. You've got an extra value there, XM, a height difference. You got your high pressure impulse line, and then you got your vented to atmosphere on the low pressure line side. Zero elevation. Here you have your high pressure line on one side and your low pressure on the other side. And so you've got hot water inlet to the tank. Steam comes out of the bottom. You need to know the height of the tank. You need to have a steam output. You need to look at the condensate pot, right? And you have to have that line, the LP impulse line, filled with H2O. Have it filled with water all the time, and then it's on the low pressure side, and you need to know that dimension as well. So from there you can calibrate that level transmitter to know what the level is in that tank. You can have bubblers. So here you have a constant differential pressure relay. You have some supply gas line, could be air. You have a bubbler tube. You have some reference and some height. And then you got a high pressure line, and then you vent to your low pressure line to atmosphere. And then you get another 4 to 20 milliamp signal. So it depends, why do they have so many different variables here on how to measure tank level? Because one works better for a certain process than another. That's why they do it. Effective temperature. So if you have your atmospheric pressure on the top, you have your liquid density, P1, and temperature, T1. So as the temperature increases or decreases, will have an effect on the density of the liquid. So you need to know that. Temperature effects in a wet leg. Again, you've got your process temperature T1, liquid density P1. You've got to know the H1 level. You got your gas, your P gas at the top, your pressure of the gas at the top. You've got your wet leg over there, low pressure line full of water, and then your low pressure goes to one side of the level transmitter. The high pressure side goes to the high pressure side. Abnormalities, transmitter installed backwards, that would mess it up. Overpressure, sensing lines blocked and drained. So what you want to do is you want to make sure that when you install a new transmitter, a level transmitter, you physically measure the liquid in there. You got to know the level of the liquid, and by measuring it in the liquid, you can calibrate that instrument. So you have to have an I&E guy go out there and calibrate that level transmitter. Once it gives you good feedback and you feel comfortable with it, then you can actually use it. You have to check it every once in a while as well. So these I&E level transmitter guys, or transmitter, I&E guys would go out there and check all these control valves and level transmitters and different pressure transmitters, flow transmitters, to make sure everything is calibrated properly and is functioning properly. Last thing is temperature measurement. One of the most common things is an RTD, resistive temperature device. So here we have a 2-wire RTD. We have some device out in the field connecting wires. We have the control room, or the control panel, and then we've got that little bridge there. And so that bridge is able to solve for the missing resistance RTD value. It's like a Wheatstone bridge. You have a 3-wire RTD, and the reason you have a 3-wire RTD is because you're interested in knowing and correcting for the length of that wire. So you want to know, because you can see at the bottom RW2 and RW3, they're connected to the same point at the RTD. RW1 is connected to the top point. You're interested in only RW1 or the actual resistance of the RTD. So it could be 0 to 100 ohms, a platinum RTD. So what you need to do is you have to subtract the lead length to make sure you're not introducing error. Thermocouples. Thermocouples are just 2 pieces of metal smashed together, and you have a millivolt difference because of a temperature difference. So metal A is pressed against metal B, and when you have a junction 1 at temperature T1 and a junction 2 at temperature T2, as the temperature changes, you have a millivolt signal coming off of that thermocouple. And so it's got a specified range. They're not as accurate as an RTD. Temperature measurement. Here you have a measurement of a junction at a process temperature. So here is another, it's a thermocouple. See how it's smashed together? So you got metal A and metal B. And then in the control room, you've got a reference junction. So you can do temperature compensation. And then you get your actual temperature transmitter. It sends out a 4 to 20 milliamp signal. Practical instrument. So again, you got your summing junction in the field. Metal A, metal B. One thing you want to make sure of, if you're using thermocouples, each thermocouple has a different type of metal. The terminal blocks that you use should be compatible with those metals. Don't introduce a different metal on your thermocouple. So go all the way to your PLC, or if you can't go all the way to the PLC, make sure you use the same special thermocouple metal for that particular thermocouple. You got a thermal well. So a thermal well can be used on an RTD or a thermocouple. So basically you got the transmitter at the top, the connection block, and then it goes into it, and then the thermal well is actually a metal bodied threaded section that can screw right into the process pipe, and then that will measure and allow you to slide this RTD element inside that fluid in the medium. It still has to go through that metal. So here's a RTD in the background. So the RTD slides all the way in. See that? And then here you got one with a thermocouple on it. You do have a response time, so the bare response would respond quicker, but the sensor in the well responds slower because it takes time for that metal to heat up and to change temperature. So by putting on a thermal well, you actually have a delay, a time delay in response. You don't know exactly, if it's steady state and it just slowly changes and then it stays there for a while, you'll be okay. it'll eventually catch up. But if it's rapidly changing, you can't see it. Failure modes. RTDs read low for a short circuit. RTDs read high for an open circuit. RTDs read low for power supply failure. Thermocouple open or short circuit causes low readings. So what you want to do is you want to make sure that you understand what these failure modes are and that you implement in your controls to ensure that you can detect when you have a failure. So here's a pressure cylinder example. Here you have some liquid being heated up, and so the actuator changes states from A to B. So that movement in and pressure changes due to the expansion of the liquid as it heats up. Here you have an engine thermostat example. When the liquid, the glycol, ethylene, or radiator fluid flows around and it heats up, it gets to a point where it pops open and allows the flow to be directed towards the radiator. Bimetallic strips, you have the top section and the bottom section. So as it's heated up, the strips heat up at different or change, deflect at different points, and so it bends up. It has a direction of movement. Here's an example of a bimetallic strip switch. So here you have a wire connected to one side of it on the base, and as the material heats up, that bimetallic strip lifts up and connects to the contact, which closes the circuit. Here's a coiled bimetallic strip for like on your house. This is an old house with a mercury switch. So as the metallic strip or the bimetallic strip heats up, it changes the deflection on that little coil, that uncoiled bimetallic strip. So it changes and it clicks, and when it hits to a point where the liquid mercury slides down and touches the contacts, and then the air conditioner starts or stops, or the HV or the heater starts and stops. Here's another type of strip where you actually have a twisting motion, so it twists as it heats up, and it has a pointer, and you can calibrate that as well. So that's it. That's all the history or the components we're going to talk about, or theory. Now we're going to strictly talk about IC and UL panels. We're on slide 540, so we're more than halfway there. So that's what we're going to do, is talk about the differences between IC and UL. Here you have two panels. This presentation was actually put together by Siemens, and it's really a I don't know if it's a presentation so much as something you can download off their website. You have your IC panel on the left and you have your UL panel on the right, and they basically open the doors. Siemens offers different protective devices, circuit breakers, fuses, disconnector switches, overloads. You have different switching devices like contactors, soft starters. You have different monitoring devices like a monitoring relay. You have safety systems, right? So if you have a requirement like the old EN 1050 requirement, risk mitigation, so if you have a device that will cut somebody's hand off, you need to make sure you put in a safety system. And then you have the other miscellaneous devices like the rotary operating mechanisms, or the bus bars or terminal blocks, things of that nature. When you're designing a system, first you need to understand what the line system configurations are. What is the power feeding me? You need to understand the organization and standards. Is it UL or IEC? You need to understand what the difference between a branch circuit and a feeder circuit. You need to understand the difference, what the UL mark looks like. You need to understand how to apply the short circuit rating, the SCCR rating. You have to understand where the panel is going to be installed. Is it going to be installed in the near the coast, so you have salt-laden air? Is it going to be real hot? Is it going to be in 50 degrees C ambient or 40 degrees C ambient, or is it going to be a lot of rain? You need to understand the control circuits. They need to be 24 volt DC or 24 volt AC or 120 volt AC. You need to understand the lines and cables, and then you need to understand commissioning acceptance. Okay, so if it's an IEC system, then you have TT systems or TN systems, grounded Y. If it's an IT system, ungrounded Y. So that's the differentiation on an IEC system. On UL, it's a varying deal. You can have 208/120, you can have 240/120, you can have 480Y/277 volts, you can have a wide variety of circuit configurations. Here's an example of a Y grounded transformer. So the line-to-line voltage here is 480. The line-to-neutral voltage is 277. You just take the line-to-line voltage, 480 divided by the square root of 3 is 277. You can do that on 600 volt or 480 volt systems. You can also have a corner grounded delta, and sometimes they have ungrounded delta systems as well. So the point of this is, if you have a 480Y system / 277 volt system, then the devices you can use in those systems are the ones that are rated 480/277 or 600/347 or 600 volt and 480 volt systems. But if you have a corner grounded delta, you can only use the devices that are 400 volt and 600 volt rated. You can't use any of those slash ratings. Residential systems, you can have a 240/120 volt single phase system. So here you have devices with 240 volts if the devices are connected between the line conductors. If the devices are 120 volts, if the line is connected between the line and the ground or the tap. Ungrounded Ys, if you have an ungrounded Y, you're not permitted to use that the 277 volt or the 377 volt rated equipment. You must use only 600 volt and 480 volt systems. And that applies to the ungrounded delta as well. So it's imperative that you understand the utility feeding your control panel and what configuration it is in, and also find out the impedance value of that transformer like we pointed out before. Because if you know the impedance and the kVA and what size conductors are feeding you, you can actually do a rough calculation for the available short circuit current. We talked about NFPA, National Fire Protection Association. We talked about UL Laboratories. We talked about CSA, Canadian Standard Association. And then, of course, the NRT, the NERDL, the National Recognized Testing Laboratories. Give you a second to read that. So when you're building an NEC or NFPA 70 panel, you're going to follow NFPA 79 and you're going to follow UL 508A standards. UL 508A draws from the NEC. The NEC draws from the IEEE standards. I don't know if you knew that or not. So if you have UL 508A panel, you're going to be installing a UL 489 rated breaker. If you're building an IEC panel, you need to follow the 6364-1 standards, and hence the 60204-1 and 61439-1 standards. You'll notice that components almost always have dual ratings. So they'll have the NEC and then they'll have the IEC, or the UL and the IEC ratings. So they'll have Senelec rated, or they'll have a CE on it, or they'll have a UL, or the backwards RU symbol on it. We talked about feeder circuits and branch circuits. This is a nice little diagram because it shows you where that red line is. The top of the red line actually differentiates the feeder circuits. The branch circuits below it. So you can kind of take a look at that. The next one is the creepages and the clearances. A lot of people don't put enough clearance in these panels, and they don't separate the line-to-line voltage far enough. So if you're putting in your own circuit, your own bus bar or something like that, you need to make sure that you separate it by at least 1 inch if it's 480 volt or 600 volt system. If you're installing like a through air, it's 1 inch. If it's a 0 to 125 volts, it's a ½ inch. So this is for the feeder circuits. If it's the branch circuits, you don't have to go quite as far. So you can do through air is only a 1/16 of an inch for 0 to 125 volt DC systems, and 3/8 of an inch for 301 to 600 volt systems. So it depends if it's a feeder circuit or a branch circuit, and that depends on the distances. These are all the different symbols you'll see. UL, ULC, which is Canadian. So the mark is applied to products tested for compliance with Canadian UL safety requirements. So if you have a CUL listing, then you can have the CUL/US. And then you've got the recognized component testing symbol, which is your backwards RU. So typically you'll be putting a label on that says UL or CUL/US. If you go CUL/US, then you're covered, right? Because you certainly want to make sure that you cover both the Canadian and the UL standards. You can also, I don't know if this has changed or not, but back when I used to build panels, you can self-certify a CE panel. You can also self-certify an ATEX panel, which is for hazardous markets, right? For hazardous areas, up to zone 2. You can't self-certify zone 1 or zone 0. Requirements for the NEC just basically states that you now have to calculate your SCCR values. So either the SCCR value comes with the panel, an individual panel already UL tested. They actually test that panel by itself. It's a very expensive option. Option 2 is you use pre-tested versions of buying such tested standard industrial control panels. And option 3, which is probably the most common thing used, is you actually go through the methods and you actually determine what your short circuit rating is. So when you determine your short circuit rating, you must list it on your control panel, must be listed on your report. The smallest value determines the total short circuit rating of the panel. And that's the bottom line. So if you have a UL 489 65K rated circuit breaker, and you come directly out of the bottom of that breaker, and you have some power distribution blocks that are rated for 10 kA, that control panel is rated 10 kA. It's not rated for that circuit breaker rating. So you need to make sure you're aware of that. If you don't have an SSR value, then the UL table SB 4.1 actually has them for you. So you can actually follow their little values for you. You can also go to the manufacturer and find out if they have a series rating tests. They might have 2 devices that are put in series, both with lower short circuit ratings, but when they're combined together, they have a higher series ratings. The actual type of ingression, right, the type of enclosure you're using, UL uses types, IEC uses IP ratings, right? So if you have a Type 4, that's a NEMA 4 panel, which is dust-proof and waterproof. It's not corrosion-proof, but just dust-proof and waterproof. It could be painted carbon steel, and you could hit it with a high jet spray hose. If you were like cleaning your truck, you could put your control panel on the back, spray it off. It shouldn't get any water inside that control panel. And then the equivalent with the IP would be the IP65. You can't install if you're designing a CE panel and the application requires an IP65, you can't just say, oh, I'm going to put in a NEMA 4 panel or Type 4 panel, because they don't work that way, right? You can only install one that's labeled IP65, and you can install one that says Type 4, but you can't take a Type 4 and put it in an IP65. And I don't even think you can take an IP65 and put it in a Type 4 area. So you need to make sure that your panel is dual rated. That's the easiest way to get past it. Here's a diagram from the UL standard. It shows the Class 1 control circuits and Class 2 control circuits. So a Class 1 control circuit is for general control circuits. It is a control circuit to the load side of the BCPM, the branch circuit protective device. Maximum voltage in this area is 600 volts. Maximum current power is typically 15 amps. You don't want to go any higher than that. Control circuits connected to the outgoing side of the load transformer. Control circuits connected to the outgoing side of the control transformer / power supply. So those are your Class 1 control circuits. Class 2 control circuits are really for limited power. Devices approved for use for Class 2 may only be used in these control circuits with limited power. So typically you're looking at a maximum of 30 volts RMS, and devices that are used entirely in Class 2 circuits do not have to be checked via an authorized jurisdiction, right? So an unlisted component can be used in a Class 2 circuit. So if you've got something that you use, like a printed circuit board or something, and it is fed from a Class 2 circuit, a circuit that is a UL 5065-1 or 3 control panel or control power supply, and it has a secondary voltage of 30 volt RMS or less, then the components can be used as unlisted components. I've had people want to do that, but I rarely ever do it. Low voltage, limited energy circuits control circuit with protected extra low voltage. So here you have control circuit with a maximum 30 volts RMS or 42 volt peak voltage, or a DC direct voltage with a maximum power of 100 VA. So it can't draw a lot of power, right? 5 amps or 20 volts or less. But if you have a situation where you have a unlisted component that you really want to use, you can power it from a limited class 2 control circuit. Wires and bus bars are typically made from copper in UL 508A. Exceptions, bus bars and panels can also be made of aluminum. The internal wires, all internal wires must be approved for 90 degrees C and correspond to one of the following types. So the wire itself has to be approved for 90 degrees C, but you don't want to size it for 90 degrees C. In that column that we talked about earlier, you want to size it in the 75 degrees C column. If it's 100 amps or less, then you want to size it for the 60 degrees C column, but you still have to use 90 degrees C rated cable. So you can use MTW, machine tool wire, you can use rubber insulated wire, you can use thermoplastic insulated wire, and make sure that you keep the spool of wire, or you take a picture of it, a photocopy of it, so that they can trace it back and say, this wire was used in that panel. So, and then there's wiring methods, NFPA 79, Article 13, or UL 508A, Article 28, 29, and 38. And UL 508A wires in the main circuit must not be any smaller than 14 AWG. You want to make sure you're no smaller than that. Typically what I use in power circuits is 12 and larger, and control circuits I would use 14. Wire sizes and current carrying capacity. So a 14 gauge wire is in the 60 degrees C column is rated for 15 amps. If it's 75 degrees C, it's also rated for 15 amps. So if it's a 4-aught, it is rated for 230 amps for copper and 180 amps for aluminum. Pretty good chart. Just remember, when you start bundling cables together, you have to derate. So you have to go back to the NEC and you have to derate. So if you have more than 4 to 6 current carrying conductors, you have to derate, I think was 0.8. If your ambient is higher than 40 degrees C or higher than 30 degrees C for that column, then you have to derate that as well. Every electrical machine or system in the USA is checked by an inspector known as a authority having jurisdiction before it can be commissioned. So the authority having jurisdiction in a refinery in Texas could be the electrical, the person that works for that refinery, right? Their electrical person. So sometimes authority having jurisdiction is not a municipal person or a state person, right? It can be just solely somebody that works in that refinery. If they own that refinery, they are the local authority. Acceptance is based on the NEC, the relevant applicable specified sections of NFPA 79, and in the USA, acceptance is a legal requirement. So if you have an OEM, an original equipment manufacturer, and you work for a manufacturing shop, and you have a panel listed and labeled by an NRTL, typically it will be accepted on site. You can actually ship something that's not UL listed and then have a company like Met Laboratories or UL even go out there and test it, but it's extremely expensive, right? So you want to be careful of that. You want to make sure that if you have a requirement to build a control panel, and that panel has to be UL listed, make sure you're building it in a UL certified shop, right? Okay, so we talked about those miniature circuit breakers. You can see they're both in the IC and the UL panels. And those miniature circuit breakers, if they're UL, they have to be that UL 489 if they're used in the branch circuit protection in the main feeder section. So IEC will use this is for Siemens 5SY4 miniature circuit breaker, and the UL is the 5SJ4 miniature circuit breaker. So you got to watch out which one you use and which one's allowed in different panels. Gives you your different ratings, so 0.3 to 63 amps. And that so that 5SJ4 miniature UL breaker is rated for UL 489. It's a pretty good breaker. Rated capacity up to 14 kA and up to 15 kA for rated switching capacity. Rated voltage 480 volt Y to 277 volt AC. So you want to watch out on that. If you've got an ungrounded delta system feeding this system, you can't use this breaker, right? It's not rated for that. The IEC rating says it's up to 25 kA according to EN 60947-2. Here's some more breakers. Those are nice little breakers. Just need to make sure you use them in the right place. So here's your main switch or main circuit breaker, right? So they've got it over there on the left, the IEC breaker, and over on the right they got the UL breaker. So on the IEC standard, you can use that 3VL circuit breaker, and you can also use the 3VL circuit breaker for the UL standard. But they look different. You can see that they do look different. 16 amps to 1600 amps, up to 690 volts. Switching capacity for 400 volts at 100 kA. That's 100,000 amps. 3 and 4 pole devices. Sometimes in the IC version they want you to switch that neutral. In America we don't switch that neutral. The set value IR for the overcurrent release is in percent, and the set value IR for the overcurrent release in the UL version is set in amperes. So it's also a pretty stout looking breaker. Both of them are stout looking breakers. Gives you some examples of where they can be used. Main and emergency off switch, system generator protection, starter combinations, etc. So here's some other circuit breakers as system protection. So these are kind of cool because it acts like a circuit breaker, but it also acts like a circuit breaker / motor starter. You can actually add that little motor starter on the bottom of it. So this is a 3RV2 circuit breaker. If you're going to use a UL standard, you have to use a 3RV27/28 circuit breaker. Rated up to 40 amps on the IEC version, rated only up to 22 amps on the UL version. So you need to really understand what you're using here, right? It says it can handle that 65 kA rating. Pretty cool. And there's your breakers again, some more standards and where they can be used. For transformer protection. On that IEC panel you can use it as a protected combination motor controller when you have the additional terminal blocks. Here's your 3RV1 circuit breaker. It's a different type of circuit breaker, and you see they highlight where it's being used. So you can kind of go through this on your own. I don't need to go through all this, but it's up to 100 amps. And they vary from different manufacturers. Maybe you don't like using Siemens, maybe you like Allen Bradley, or maybe you like Eaton equipment, or maybe you like Schneider equipment. Could be that the equipment is only specified by the manufacturer or the end client. They want you to use a certain brand, or maybe they don't really care. Here's your sockets. I love putting sockets, receptacles and control panels, because it's so nice when you're out there and you're in the middle of nowhere and you can just plug directly into it. So you're really doing your service guys a big favor by installing that. Of course, the IEC standard, they have their certain type of socket versus the UL standard. But both of them snap right on that DIN rail, which is really nice. The IEC is rated up to 240 volts, up to 16 amps. And that operating voltage on a UL one is 125 volts AC up to 15 amps. You'd have a pretty big CPT to feed that one. So they give you your approvals. So here you can see that your IEC is approved for IEC 60204-1, and it's also the UL's UL 498. It's also CSA C22.2. So it's got that dual rating. Bus bar systems. I don't think there is any UL requirements for bus bar other than spacing and maybe the size, physical size of it. but they do have approved bus bars that you can use, and you can tap off of these bus bars. Just remember, when you put bus bars in here and you're running current through them, you can actually add heat to the panel, so you need to understand all of that. So here's different bus bars and different characteristics about them. The characteristics are only applicable to IEC applications. They must not be used for UL applications. Your contactor. Here's a contactor where you can actually start and stop something. It's got EC ratings and UL ratings. So the EC rating is up to 50 amps, or the IEC rating is up to 50 amps, up to 690 volts, whereas the CSA and UL rating is only up to 42 amps. Probably the same starter. I don't know why they derate one of them. And it's got multiple ratings. See that? Your load feeders, your motor starter protection and contactors. Kind of nice. They look cool. They snap in there, and they've got little finger protection so you don't get shocked. Here's your load feeder. So you got an actual disconnect switch on the top where you can actually open and close it like a circuit breaker, and it's also got the contactor on the bottom. And there's your in-feeder system. Here's a fuseless load feeder consisting of the 3R-V2 circuit breaker and the 3R-T2 contactor. That's really nice. So here's your load feeder, the different approvals. You've got your IC approval, CSA approval, and UL approval. So it says that this particular load feeder can be used in a combination motor controller type F. Remember, we talked about the type E and the type F controllers. High flexibility in-feed systems. There's the approval for your in-feed systems. Next, you got your terminal blocks. There's a wide variety of different terminal blocks. Color coded. You can see the green is your grounds, your green/yellow. In IECs, you have to use the green/yellow. UL doesn't really care. Space-saving combinations. These are nice. Some of those blocks, terminal blocks, are large. They can get up to 192 amps. Make sure you look at them real carefully because they'll have the dual rating, but each IEC versus UL rating is slightly different. So you want to make sure you download every symbol or every terminal block and understand. You got screw type terminals. You got different ratings for them. Spring loaded terminals. And again, you want to use a spring loaded terminal maybe on a genset or on the side of a Waukesha engine. That engine would be vibrating all the time, and it'll just shake those terminal screws loose. Fixed terminal blocks. You can assemble them and put bus bars between them and stuff like that. Compact starter, an in-feed system. That's what one of those compact starters looks like. Kind of nice. The compact starter. So it's an integral starter. It's got everything in it. So universal fuseless motor feeder combines the circuit breaker, contactor, and overload relays all into one little enclosure. So there's actually two of them there side by side. Rated up to 690 volts, up to 32 amps. Nice. That's a nice motor starter. Short circuit capacity, up to 53 Ka. That's pretty high. So your IEC approvals and your UL approvals. So this self-protected combination motor controllers are good for type E. Remember, the other one was type F. So you need to understand whether your client cares if he wants a type E or type F. One's cheaper than the other. One will allow that contactor to destroy itself. The other one will make sure that that contactor stays intact after a short circuit. And also look at that, it's suitable for tap conductor protection, right? Look up in the NEC what a tap conductor is and how far they can be, and there's a bunch of rules associated with them. Here's your compact starter in-feed system where you can plug these little starters into it. So you got one feed goes off to the left right there. You can just feed it one time, and it's got the bus bar, and then you snap them in there, and you don't have to worry about individually wiring them all. It can be used for UL 508A and Canadian CSA standards. There's a motor starter protection and a 3R2 contactor or on a bus bar with in-feed. So here you have a bus bar with this combination starter. You can snap it in there. Never used one of those. Never used a bus bar like that. Here's an in-feed for like a device selection in-feed. Here's a load feeder with a bus bar adapter. So you take this device and you plug it in there, and then you snap it on that bus bar. Here's a circuit breaker and a contactor combination. Here's a circuit breaker as a motor circuit breaker. It's rated up to 40 amps, up to 32 amps with that assembly. It's IEC 690 volt AC rated. It's 600 volt AC UL CSA. Its short circuit strength is up to 100 kA. That's high. Screw type connection systems is 40 amps. Ring type lugs are up to 32 amps. It's a nice little device. Here's your manual, a full UL application. You can take these and connect them together. Your bus bar adapter. Soft starter. So a soft starter is basically back-to-back SCRs, and it gradually allows the voltage to rise on the starter, on the motor. Here's what a soft starter looks like. So it can go all the way up to 1,214 amps, depending on the size and temperature. Operating voltage up to 690 volts AC. Usually you see 690 volt AC only in Canada. Rated frequency 50 or 60 hertz. Inside Delta circuit to reduce size and device costs. Easy to install and integrate into motor feeders. It has both ratings, the IEC and the UL and the CSA ratings. Remember, when you're dealing with soft starts, you should use the semiconductor fuses, right? So here's a semiconductor fuse. You don't have to use them, but it's recommended if the soft start doesn't have that capability. So these are fuses to protect power semiconductors against the effects of short circuits, high-speed switch-off characteristics. So if the soft start requires it, you have to use this semiconductor power fuse. Up to 100 amps. Different links, right? You can have a fuse link, fuse holder, and fuse bases, and they have the dual ratings. Class CC fuse system, so the small little, up to 30 amps, I think, the Class CC fuse. So it is uninterrupted duty. Only 80% of the rated current is permitted per the NEC 210.20. Interesting. Rated up to 600 volts and has a capacity, breaking capacity of 200 kA. No IEC approval for this. It cannot be used in a IEC panel. It can only be used in UL or CSA panels. Distributed I/O motor starters. So here you see a distributed I/O motor starter where you can actually snap things into it. And it's kind of clever. It takes up a lot of room though, but it'll fit right in there. I mean, it's all relative. So this is a multifunction motor starter for distributed drive solutions. Standard motor starters or high feature motor starters or fail-safe motor starter. It interfaces with that Profibus. So if you've got a Siemens PLC that communicates Profibus, you can snap Profibus right into this, and then you don't have to wire up all the feedback signals. You can get all these signals back to the PLC via Profibus. That's an attraction. Approved for IEC, UL, and Canadian standards. This special Neosed fuse system is probably just IEC only, right? So can't use that in UL. I don't think I've ever even seen one of those. So you can see it's used in DIN and VDE, which is German, the German standards and the IEC standards. So this would be the equivalent of our little small little devices, right? Our miniature circuit breakers or miniature fuses, the Class CC fuses, but this is their version of the Class CC fuses, right? So it's not a UL-CSA approval. So you need to make sure you don't use it. A safety relay. A safety relay is where you have a requirement for a seal rating, a seal 1, 2, 3 rating, could be seal 0 rating. If you've got a device that can accidentally cut somebody's hand off, right, and it's a type of a machine that would actually drop something and somebody's hand could get in there, then you have to design it per the EN risk mitigation standards. The old one is the EN 1050. Now they're all safety instrumented system standards. And you have to install a safety relay that has a certain seal rating. So here you have a safety system here. So it's a solid state, a safety relay with a solid state relay or contact relay enabling circuit plus special functions. So you have to understand what you're doing when you're dealing with safety relays. And they have real high ratings, like higher seal ratings, like seal ratings. So here it meets the approval of the ISO 13849-1. It also meets IEC safety integrity level. So that's what it is. The 61508 actually replaces the old EN 1050. So, and in this particular safety relay, it's got a seal 3 rating. It's also approved for UL and CSA standards. PLC usually has about a seal 2 rating. You know, a good PLC, like a Control Logics PLC, and it has to be programmed certain ways. So to get a seal 3 rating is pretty damn high. So you need to, if you're going to deal with seal rated systems or seal at safety integrity level 3 or 2 or 1, you need to understand IEC 61508 very well. So here's another safety instrumented system. So it's a modular safety system. And this is still more safety systems, a Cirrus design. It's complies with the seal 3 rating. Got the interface for Profibus. Got your ISO approval, your IEC 61508 approval for seal 3, and it also has UL/CSA approval. Motor management systems, current voltage measuring modules. We talked about voltmeters, kilowatt meters, power factor meters, amp meters. That's what this thing does. It measures current voltage. So it's a motor management system. Interesting that it goes up to a seal 3 rating. So it's a safety integrity level of seal 3. That's actually interesting. But the motor might be real critical, that if that motor shuts down, then certain things have to shut down before it shuts down or at the same time it shuts down. Otherwise you could release harmful gases into the environment. So that's why a lot of control companies are actually putting their arms around power systems and saying, hey, you guys are really integral parts of the safety instrumented systems. So it's becoming more and more reality for us to deal with. So it meets most of these safety requirements. Again, you can see it's a seal 3 to IEC, and it's approved for all these different standards. You got a current and voltage measuring module for motor management systems. Fuse switch connects. There's a HRC fuse switch connector. We're almost through with these different devices that Siemens has. It's just kind of nice to kind of go through these because you might not know something like this is even available. So this is really nice because it's completely finger safe. You can put your hands all over that and not get shocked. That's a pretty neat concept. It's UL 512 rated. It's CSA C22.2 rated. And it can be used in a CE or ATEX panel or UL 508A panel. Solid state switching devices. There's a solid state switching device. Up to 100 million operating cycles. That's pretty cool. Because if you open and close a contactor a lot, it'll fail. So this is a solid state switching device used for frequent switching of motors, small drives, and valves. Wear-free and noiseless switching for high system availability, up to 16 amps. That's pretty cool. It's IC and CSA and UL rated. You have an overload relay. Your overload relays in both the IC and the UL panel. Solid state overload relay for inverse time delayed overload protection of three-phase motors. 0.4 to 40 amps, 690 volts. It's got all the IC and the UL and the CSA approval. Get your monitoring relay. So here's a monitor relay for optimum protection of machines and systems. Measures for overload and underload monitoring. It's kind of nice. It's got a high interrupt rating of 100 kA with 690 volt. It's got all the ratings. IC, CSA, and UL. Bus mounted base. This is only applicable to the IC. This is for that special fuse they have. So here's a bus mounted base for that fuse system for IC. Pretty nice. More mounted base systems. You don't see these in UL panels. You only see them in IC panels, not UL or CSA. Position switch. So you wanted to have a position switch up there. It's suitable for both UL or IEC panels. To prevent protective door opening at random or accidentally when there might still be a prevailing risk due to the operating status of the machine and system. So you can actually lock the system so that somebody can't get in there and open and close it. Has all the ratings. Power supplies. These are both in the UL and the IEC panels. Typically about 24 volt DC. Can be 1, 2, or 3 phase line voltages. You know, the voltage, output voltages vary 5, 12, 48 volts if I recall. Rated output current from 2 to 40 amps or so. That's pretty big. Rated output voltage 24 volt DC plus or minus 3%. Rated input voltage up to 550 volt AC. That's nice because you get one power supply and you can cover both UL or IEC voltages without having to worry about it. Here's some of that information. Version from other outputs voltages including 5, 12, and 48 volt DC are available. So this particular one is just a 24 volt DC output plus or minus 3%, 2 to 40 amps, and it's got that rated input voltage of, you know, up to 550 volt AC. So here they mention certified in accordance with ATEX guidelines. So what is ATEX? ATEX is a hazardous panel, similar to the UL 508 panel, but for Class 1 Div 2 control panel applications. You can actually have UL or MET perform a hazardous investigation on your facility, and you can start building hazardous rated panels. A CE general purpose panel would be CE rated. If you put that panel in a hazardous location, you put a purge system on it or something like that, then you would have to comply with ATEX guidelines. Here's a pack measuring instrument, the 7km. Sits on the door. You can get all the information about that particular incoming voltage. So it measures the 3 and 4 wire systems, TN, TT, and IT, 50 and 60 hertz up to 690 volts. Approval IEC, CSA, and UL. An enclosure type 5 for UL 50. Interesting. Emergency stop push buttons. The IEC, they have the yellow and the red, right? And UL, they usually have just the red, but They're kind of dual rated anyway. I kind of like that IEC push button, that ESD. That's rated up to 10 amps. The UL and the CSA ratings are 10 amps, 300 volts. It's got all the dual ratings. Main and emergency off switch. So if you have a main switch, you can have that little handle there, and it has to be color coded a certain color for CE. Right? For UL panels, it doesn't have to be colored that way. The main disconnect circuit there. So you can actually put this mechanism on the door. You have to line it up, and it'll plug into that mechanism. And with the door closed, you can open and close the main power to this panel. Here's your rotary mechanism with emergency off version versus the standard version. And rotary actuators. You just want to make sure that when you're building a UL 508 panel that the height of that handle doesn't exceed, I think it's 79 inches, 6 foot 5 inches or something. We'll see that later. Approval IEC 6024-1, CSA and UL. Lines and cables. And that's it. That's all the components in those panels, so the IEC and the UL panels. It's a nice little overview. You can go to Siemens and download the original files and download their catalogs and everything. Just make sure that you understand all the components and make sure that you utilize the correct components in the correct places. Okay, so here's a Eaton guide. It's specifically designed for UL 508 control panel design guide. You can download it straight from Eaton. It's not going to go over all the Eaton components like the Siemens guide did, but it will kind of give you a breakdown of the main feeders and the groups and the different branch, the control circuits and stuff like that. It's a pretty good guide that you can follow. So here you have the designing of the main panel. So you've got your main feeder at the top, get your branch circuits, your motor starters, your other branch protective systems, your individual circuits for motor loads. You might have some lighting loads or heater loads, and then you've got some control circuits. So that would be like a motors panel where you could have a single motor as well. So what we'll do is we'll talk about sizing the feeder. So I don't know if you can read that or not, but basically what you do is you take the largest motor size, right? Let's say it's 125 amps, and then you sum up all the different loads, and that is your feeder size, right? So take the largest motor, whatever the largest load is, and multiply that times that full load amps times 1.25, and then sum the rest of them all at full load, and that should be the size of your feeder. And you can zoom into this. This is page 705. They give you different part numbers for the different feeder circuits. So breaker and fuse disconnect selection. Give you your group motor designs and the rules associated with group motor designs. So if you're using a class CC fuse, you can use it 300% of the full load amps. If you're using a breaker, you want to use 250% of the largest motor full load amps. You can read through this. And here's the individual part numbers and their ratings for these different part numbers from Eaton. Individual circuit motor loads, they have different rules for that. So here's a UL 508A type F combination motor starter. And here's your branch circuits and the rules associated with those different branch circuit types. And some of the part numbers that you could use to solve some of these problems. Here's some of your branch circuit motor protection devices. So you can, this is kind of nice because it gives you everything you need to know. It gives you the actual part number for the motor circuit protector, the contactor, gives you the thermal contactor part number. Schneider has similar things like this as well. Here's your branch motor selective for 230 volt AC, for 480 volt AC, and it says for 460 volt AC. Heater and lighting load circuits. So if you have a heater circuit, not less than 125% of the heater load would be your protective device. Not more than, I think that says 60 amps. For lighting, it should not exceed 15 amps. It shall not exceed the ampacity of the anticipated field wiring. So here's some of the contactors you can use in there for these lighting lights. Power circuit wiring, we talked about that a little bit. Nothing less than 14 AWG. You want to size it 125% of the full load amps. Field wiring, you don't want to use anything smaller than 14 AWG. Again, you want to use 125% of the full load amps. But you can sit there and read this and the different types of conductors. Here's full load motor running currents in amperes corresponding with various AC horsepower ratings. It's kind of a nice little chart. Basically what I do if I don't have a chart handy is I just say, oh, horsepower equals kVA. It's a rule of thumb, right? So then I just solve for kVA and get my amps. I'm usually a little high on that, but it works. Get you in the ballpark anyway. Ampacities and insulated conductors. So again, this is based on a 75°C copper column. You know, you want to be aware that if you are installing a circuit that's 100 amps or less, you can use this. You're supposed to use a 60°C column, and you're supposed to use 90°C rated conductors, right? The insulation rating. But and also, if you have multiple conductors in a bundled together, you have to derate. And also if you have high temperature applications, or just you're in a higher than normal ambient temperature. In Houston, it's 40°C. It's 104 degrees F all the time. It's 104 degrees F right now as I was talking about this. And it's wet and it's humid, so you need to be aware of those things. You have different accessories that you can snap onto these modules. For you're designing the control circuit, so you need to look at the CPT size, right? And remember we talked about that earlier. We said that you need to take and add up all your loads and make sure you size that CPT so that it's only running at 80%. So you got some room for some growth, right? Here's common control circuits. We talked about this already. We actually went through this. I think you probably understand this already. Here's sizing a control power transformer. So, and this is a good point. You've got to factor in the inrush VA, because what will happen is you might have loads that have high inrush current, and that CPT needs to be sized for that. So that's a good point right there. So what they say is take the CPA or the CPT inrush VA equals inrush VA squared plus the sealed VA squared, right? And then square root that. So that's a very good point. So make sure that you look not only at the individual sealed loads. The sealed is you energize the coil and it's been sitting there for a second, right? And it stabilizes out at a certain value. The minute you apply it, the inrush current can grow high, right? It can increase significantly. For a motor, the inrush current can be, 6 times the full load amps. The sealed value would be the full load amps for that. So that's a very good point that you should consider that. I should have mentioned that earlier. And then here's sizing protection for your CPTs. And basically what you want to do is, follow the UL 508A, or NEC has a chart as well. I think it's a 450 table. We'll get to it here shortly. And it depends on if you're providing only primary protection or only secondary protection, or both primary and secondary protection. Power control, the power control power selection. They give you some great ideas here: nominal load plus sealed load. So they address the sealed load and the nominal load and the inrush load. Very good points here. Usually you're covered though if you size it for 80%. If you add up all the loads and you size that transformer so that it's only running about 80% of the full load amps, usually that is okay, but you still should look at inrush current to make sure that it can withstand it. Size and protection for power supplies. Usually it's 1.25 times the full load current that the power supply will draw. Just remember, if it's a 10-watt power supply, it might draw 20 VA. So you got to be aware of that. Wire selection. There are certain colors that you should use, right? So here you got black is all ungrounded control circuit conductors operating at supply voltage. Red is ungrounded AC control circuits operating at voltage less than the supply voltage. Blue is ungrounded DC control circuits. You make sure that you understand that blue can also be intrinsically safe circuits, right? I talk about intrinsically safe circuits in the area classification training course that I put on. Yellow or orange is ungrounded control circuits, or foreign power, if you will. White or gray could be a neutral. White with a blue stripe. Not everybody follows these guidelines, but you want to make sure that that you don't use like a green on a hot leg or something. There are certain NEC requirements. You got logic control pilot device selection. So they're telling you what part number that you could, or what category number, catalog number you'll go to. Logic control, relays, timers, terminal block selection. You know, Eaton, Schneider, Siemens, Allen Bradley, ABB, all of them have wonderful parts. They're very similar. You just got to make sure that you're using them in the right application, and that if you're designing a UL 508 control panel, that they're all UL listed or UL recognized components. And you got your different logic controllers, your PLCs. So it looks like they got the old Tweedo. It's a square D version. I know Allen Bradley even has a little Pico that looks like that. And they've got a nicer, bigger module. I probably ought to look at the Eaton PLC controls. Those look kind of interesting. Has a nice little guide here on sizing the branch protection for single motor and control circuits. So depending on the type of fuse you're using, if you have a non-time delay fuse, like a Class CC fuse, you can go up to 300% of the full load amps. You can just read through this. It's a good guide right here. It's a very well written guide. Use some nice formulas and conversions. So for direct current, they give you a value. For single phase AC, they give you the value. For three phase, they give you the value that 1.72 or 73 is the square root of 3. Voltage drop calculations. So you can make your own little spreadsheets and what have you. Then you got conversions from 1 inch is 2.54 centimeters. Then you got your ICUL types versus the IP types. Again, caution, don't assume that you can put an IP rated panel in a UL area or an NEC area and vice versa. Make sure they're dual rated. So here they give you different wire and torque sizes. The torque on terminal blocks and breakers and all these components, you have to list the torque rating. That's something, well, it's not new anymore. It's probably back in 2001 they started requiring that. But you actually have to label in your drawing or in the proper area to market where these torque values are. Here's some more values. So that's it on the Eaton agenda. Now what we'll do is we'll go through another Eaton PowerPoint presentation I found online. It'll go over who is UL and what the role do they play, what is a UL 508A standard, implementing the implementation of the standard, component selection, that short circuit rating, we talked about that, common application questions, and how Eaton can help. I'm not affiliated with Eaton. I'm not affiliated with Siemens. I'm not affiliated with any manufacturer. Just wanted to make sure that that's clear. So, UL's role. Who is UL and what role do they play? They're an independent testing laboratory. They're third-party certified, USA-centric, going beyond CUL, consistent with the NEC, and offers a variety of listing services. So, if you're making industrial control panels, it's UL 508A. If you're making a panel board, it's UL 67, etc. The UL 508A standard. It is an industrial control panel assembly which may contain motor controllers, overload relays, fuse disconnects, circuit breakers, buttons, switches, timers, and controllers, like a PLC, wiring, terminals, enclosures. Four parts. The standard's broken up into 4 parts. You got part 1 is general use, part 2 is specific use, part 3 is specific component requirements, and then part 4 is that short circuit rating requirement. Your guidelines for construction and designing the design. First edition was released in April 2001. It was later revised in September 2005. It's subsets of the guideline. You have general use, specific use, enclosures, industrial machinery, crane control, service equipment use, flame control, like a boiler or something, marine use, air conditioning and refrigeration, and elevation and control. Manufacturers that adhere to these requirements are eligible for UL 508A listing of their product. Just because you designed a UL 508A doesn't mean that you can stick a sticker on it, right? You have to have a third-party certified agency come and inspect it. So you have to sign an agreement with UL or MET or TUV or some agency like that that's OSHA approved. If you're doing a UL 508A industrial machinery, the following types of machines are identified as industrial machinery: metal working machine tools, machines that cut or form metal, plastic machinery, wood machinery, assembly machines, material handling machines, inspection and testing machines. Panels for industrial machinery are rated 600 volts or less. So if you have a panel going into Canadian areas and it is a 690 volt system, then the UL 508A standard doesn't really apply. So you need to use Canadian standards. Up to 40 degrees C. So if you're putting this panel in a Saudi Arabia and its ambient is up to 50 degrees C or 55 degrees C, you're in trouble because a lot of these components are only rated for 60 degrees C that you put inside the control panel. UL 508 industrial rating does not include panels for hazardous locations, NRBX, which is covered in UL 698A. So if you're building a UL 508A industrial control panel and you want to make it so that it's suitable for installation into a hazardous area like a Class 1 Div 2 area, you have to get additional certification and you have to be certified to install it per UL 698A. So, and I guess the easiest way to put this is UL 508A panels are good for general purpose panels or general purpose areas. CE panels are also suitable for general purpose areas. Hazardous rated panels are for Class 1 Div 2 or Div 1 rated areas. ATEX panels are hazardous locations for, you can do self-certification for Zone 2, but you can't do it for Zone 1 or Zone 0. So either way, you should have a certified agency helping you step you through this process. We talked about this before, the control circuit versus the power circuit. So you've got the different Class 1 control circuit and the Class 2 control circuit, and then the power circuit. The branch circuit versus the feeder circuit. So there's different rules that apply to the feeder circuit versus the branch circuit. Control circuit versus the power circuit component selection. So you have to use certain components that are rated for power circuits, right? Or for the control circuits. When you start looking up UL 508A category control numbers, you'll find that they have these odd little numbers or letters. So the category control numbers are 4 to 5 digit alphanumeric code, identifies product categories in UL listed product and recognized component directory. The AAAA with no suspects is listed. If it's got a 2 at the end of it, it's a recognized component. If it has a 7 at the end of it, it is a listed for Canada. If it has a 8 at the end of it, it is recognized for Canada. For example, NITW is CCN for CCN is the category control number for industrial control panels, and DIVQ for branch circuit protection UL 489 devices. So when you go to the UL.com website and you search for different components, you'll find these different CCN numbers. This is how you get to the UL website. Click that. Then you will come to your UL resource for UL certification information. Tremendous amount of good information out there. I strongly suggest that you search this site and understand this site. This is where you're going to get a lot of the data and the files for your files. You know, you want to keep. You're going to be building things over and over and over, and you're going to use the same types of components over and over and over. So you might as well have somebody go through and pull all these certifications for you. Here's a breakdown of it. So here, if you go to Eaton, and in Eaton they have circuit breakers, molded case circuit breaker enclosure. So you can see it's a DIVO.E7819. So here they're actually listed there. But there's other companies too, right? And there's their full DVQ continued, so that's suitable for UL 489 devices. It's a circuit breaker that's suitable for UL 489. So applying the standard before we apply control circuit versus power circuit component selection that can be used in UL 508 control panels is the category number. So it's always, when you're digging through this industrial 508 control panel section, it'll say, you know, if you're designing a circuit for a feeder circuit or for a power circuit, you need to comply with category numbers DIVQ, let's say. So make sure you understand when you see DIVQ, this is leading you back to that UL.com website, and you can actually search for vendors that are qualified that have already gone through this listing process or recognized process. So here it is example. So in paragraph 31.1.1, it says component description listed molded case circuit breaker. The standard is UL 489. The category, the CCN number is a DIVQ. So if a branch circuit protection, you can use a DVQ molded case breaker. Just you can't use those supplementary protectors. The supplementary protectors are like for UL 1077, right? So, and no MMPSs. So here's a a supplementary protector, the UL 1077, right? So we talked about that. So it says that category number for a UL 1077 device is a QVNU2. So watch out for that. A glass fuse would fall into that category. NEC 210 branch circuit protection, panel board with UL 489 molded case circuit breakers. So you can see that it's fed from a UL 489 molded case circuit breaker. For supplementary protection applications, supplementary protectors are used are to be used for overcurrent protection within the appliance or the electrical equipment. So you want to install it inside your panel. It's not the primary protection, where branch circuit protection is already provided or not required. So you can follow this. So the definition of a branch circuit in NEC Article 210, the circuit protection between the final overcurrent device protecting the circuit and the outlets. And then the supplementary protection per NEC Article 24010 is where used, it shall not be used as suitable for branch circuit overcurrent protection devices or in the place of a branch circuit protective device in Article 210. They're just not as robust and they'll fail. So here's a good example. It kind of shows you where you can use a UL 489 and where you can use a 1077. So on a control power transformer, you can put a UL 1077 device like a fuse. On the secondary side, you can put it. And the only reason you can put that UL 1077 on that fuse, on the primary side of that fuse, is because you have a UL 489 breaker at the main MCB. Otherwise, you wouldn't want to do that either. You can use them for PLC I/O, contactor coils, relays, and for the pretty much for the power stuff, you want to use the UL 489 rated stuff. Branch circuit protection, component selection, but what about sizing, feeder protection, branch protection, components and transformers? And then you've got to deal with short circuit protection, panel ratings, new standard requirements effective April 2006. Panel builders will have to label with a value. So it used to be that we didn't have to actually put the value on there. Now you have to put the short circuit rating on the panel. And that way it allows the electrician or the installing company, contractor installing that panel, they can look at that short circuit rating and say, hey, wait a second, guys, I've got an MCC with 65 kA rated equipment breakers feeding this panel and it's only rated 10 kA. I've got a problem. So requirements making short circuit rating, or SCCR short circuit rating of industrial control panels, is to provide info for safe installation and inspection of panels based on application, available fault current to the panel. What you don't want to do is have a panel that can't withstand that short circuit current, and for some reason the output of that panel, that control panel you built, is shorted out, like a shorted motor or something, and the available fault current from that MCC or that switchgear destroys your panel and causes flying debris and arc flash issues. So components not to be considered in short circuit current ratings are transformers, reactors, dry type capacitors, resistors, varistors, and voltmeters. So you don't really care about those. You don't have to include them in your assessment. So here we have fault current in a system. So we have a 2500 kVA transformer with an impedance of 5.75%. It's 12,470 volt Y, a delta primary, 470 volt Y/277 volt secondary. We have calculated fault at the secondary side of that, unlimited fault current on the primary side. That's, you know, I guess it's a safe way to do this if you just say, hey, I've got unlimited fault current on the primary side. That way the secondary side is always going to be a value you can count on. So we have 12 feet of 3200 amp copper feeder busway, and then we have, it says there it's got 52,296 amps at that fault. So that's quite a lot. Let me get a calculator on that. Just double check that real quick. So I got 25,000 times 1,000 divided by, in parentheses, 480 times 1.732 in parentheses equals. So my secondary amps on that transformer at 40 volt AC is 3007 amps. That's pretty high. Hence why we need that 3200 amp copper feeder bus. So then we divide that by 0.0575, which is the impedance of that transformer, and that gives us 52,297 amps. So they put 52,296 amps. So the reason they have slightly less than me probably is because they've included the impedance of that copper busway, 12 feet of copper busway. So any impedance will reduce the fault current, right? So you can see there's different values here. If you have a 150 amp breaker, it drops it down to 10,968 amps. fault current. You've got 100 feet of 1 conductor number 2 copper wire. You've got at your 200 amp side there, you've got steel conduit, number 4 copper, calculated at 100% motor contributions. That's interesting too. Some people don't actually factor that in, and you might be looking at this going, hey, Vince, why do they have 64,328 amps underneath that 200 amp breaker, and they only have 52,296 amps at the secondary side of that breaker, that 3,200 amp breaker? And the reason is if you have motors, when those motors see a fault, an upstream fault, they actually become generators for up to 5 to 8 cycles, and so they can deliver fault current and deliver it upstream to the fault. So you always want to assume, you want to do your calculated 100% motor contribution. So that's a smart thing that Eaton did there. OEM panel builder determines the SSR rating on the panel by short circuit test of the panel construction. Who can do a short circuit test? UL, MET, or some authorized third party in RTL, not the manufacturer. Obtain documented tested combinations of components. So Eaton and Schneider and Siemens all have documented combination series ratings that they can publish and allow you to use in your control panel. Or you got to follow that UL 508A Supplement B requirements, right? So all components in the power circuits must have a rating. Ratings of starters are typically based on horsepower rating. Supplement SB table SB41 provides tables of components without short circuit ratings. So if you've looked at all the equipment and you can't see a short circuit rating, you can always go to this UL table right here, and it says bus bars are 10 kA rated. Circuit breaker, including GFCI type, 5 kA rated. It's pretty low. So it might behoove you to dig in and find these different short circuit ratings, right? Terminal blocks or power distribution blocks are only 10 kA rated. That's one of the big things that gets people in trouble, is they put those power distribution blocks, and they, years ago they weren't rated more than about 10 kA, but now they've got some that are rated up to 100 kA, so you need to make sure you're picking the right one. So compare the SSR of all power components of the SSR of branch CPD, your circuit protective device. Use the smaller value for line side of branch CPD, and then there's your overall. So if you got branch circuit single, branch CPD no, the lowest SCCR for any component, power component, or control over current protective device. So this gives you little rules of how you can determine that value. And the gist of this is, find out what size transformers feeding your control panel or feeding that, MCC. And if you don't have SKM software, or you don't have ETAP software, or some type of an advanced software you can do an analysis on it, or you haven't been really paid to do that, then at least do a basic idea. Ask the user, who's buying the panel from you. Ask them for their short circuit value. So they'll give you that short circuit value. They'll tell you what that circuit breaker should be rated for. And then from that, you need to design the panel so that it has a short circuit rating that is compatible with the client's requirements. And then applying the standard feeder components that limit short circuit, power transformers, current limiting breakers, and fuses. So limiting short circuit current using power transformers. So rating less than 10 kVA, secondary voltage not specified, secondary device greater than 5 kA, short circuit rating on line side of circuit, use rating on primary over current device. So you can go through this. Current limiting circuit breakers. So we have short circuit rating on the line side of the feeder circuit breaker if SSR of the feeder breaker is, if the peak let through is less than SSR or load side components, and SCCR of the load side components is greater than or equal to SCCR of feeder breaker. If the smaller SCCR of the branch circuit protective device is, if number 1 exists except for B, SCCR of the load side component is less than SCCR of the feeder breaker. If the smaller Smallest SCCR of any branch circuit on the load side of the feeder breaker where neither 1 or 2 exists. So these are how you come up with those SCCR values. And here they give you a sample plots for current limiting circuit breakers and the let-through values. So you get your available short circuit current, and you can follow up. You can see this, how that's read. Maximum peak let-through current in amperes on the left, available short circuit current on the right in RMS symmetrical amperes. So here, if you wanted to go through this process, you obtain plots of a maximum let-through values for the specific current limiting circuit breaker from the manufacturer. Select the available short circuit current from the horizontal axis on the bottom of the chart that is equal to the short circuit current of the industrial control panel. Move vertically to the intersection with the curve corresponding to the rating voltage of the circuit breaker that is not less than the rated voltage of the industrial control panel. Move horizontally left to the intersection with the vertical axis to determine the peak let-through current or I squared T value. So Eaton current limiting breakers, new labeling per UL508A, current limiting, let-through curves, high AIC breakers, lowest let-through values, target completion, end of 2005. So this is something that they went after. One test is better than 1,000,000 calculations, and you can see the calculations are a little hard to do. Certainly a lot of people don't even think about them, and you could inadvertently be putting your company at risk, right? So by applying these standards and having a company go through and help you step through them, you're actually doing risk mitigation, right? Especially for insurance companies and stuff like that. They would prefer to, companies use a UL listed outfit versus non-UL listed. Applying the standards. So here you got your fuses. So peak let-through currents, IP, and clearing I squared T for fuses. So if you have a class R 30 amp fuse, it gives you between a threshold of 50 Ka, and it gives you your I squared T times 10 to the 3, so it's 10,000 amps, right? To 6,000 amps. Same criteria for the breakers, except use table instead of curve to determine the values. And here's a breakdown. It shows you the curve, and it shows you your current limiting threshold and your IP value, 2.3 times IRMS symmetrical value. So available fault current, so if you have 100 K short circuit current through that 600 amps, it'll allow 45 K to get through. So current limiting. Here again we have a fuse, like we had pointed out earlier. It trips pretty quick. So you're talking less than a quarter of a cycle here, it's offline. So you got that available fault current rises real high, and for a breaker, it might leave it online for 3 to 5 cycles, depending on the breaker. If it's a molded case 480 volt breaker, it might stay on for 5 seconds. Whereas if it's a 3-cycle breaker, it's still a long time, right? Compared to this, fuse drops it pretty quick. So here we have a diagram on the left is a common circuit that we could use in a typical control panel. We have a EGH 125 amp 65K rated breaker. We have an HMCP circuit breaker with an IT type 10Ka device there, and a contactor at the bottom, 5Ka, and a 10Ka QC type breaker. And it looks like we had a control power transformer, 5 kVA. And so this will kind of step us through this and determine what the short circuit rating of that panel would be. So your feeder circuit is 400 volt AC, 50 KAIC. So you know it's 50 KAIC, so you're trying to determine what your panel is, and you've got these motors on the bottom of this panel. First step is to determine the SCCR rating of each device. This can be done by looking at the device label. So if you look at the device label, it will actually be labeled on there. If the device is not marked UL, provides it. So if it's not marked UL and you don't have a device rating on it, then you have to use that table, which is really, really conservative. So here in this breaker example, we know that the main breaker is 65 Ka, the starter is rated 10 Ka, the contactor is rated 5 Ka and the QC breaker is rated 10 Ka. We need to determine the short circuit rating of the HMCP and the PLC. The PLC can be ignored because it's in the control circuit. The starter information states that when used in conjunction with an HMCP, it carries a rating of 65 Ka. Therefore, the panel rating is 5 Ka. So, that's pretty low. I bet you thought we had a 65 Ka rated panel. But the reason we don't is because we've got that 5 Ka there. So starter information states that when used in conjunction with HMCP, it carries a rating of 65 Ka. So where's the 5 Ka? So main breaker is 65 Ka, starter is rated 10 Ka, contactor is rated 5 Ka, and QC breaker is 10 Ka. So it's the contactor. It's that 5 Ka contactor that's driving our short circuit rating down. Interesting. Step 2, calculate the available short circuit. When taking into account current limiting components like CPTs, fuses, and circuit breakers, the available fault current is 50 Ka. Per UL 508 guidelines, a power transformer rated at 5 kVA or lower will limit fault to 2 Ka on the secondary side of the transformer. Therefore, because the rating of all the devices on the secondary of the transformer are greater than 2 Ka, the SCR of the panel in this example would be 65 Ka. Let's follow the same procedure and determine the SSR using a fuse. As a breaker example, we can eliminate the branch circuit feeding the transformer since it limits the current to 2 Ka. We need to determine the 100 amp fuse will limit the current enough to protect the starter rated at 10 Ka. So they got that RK1 100 amp fuse in series with that IT 10 Ka. From table SB42, we can determine that a 50 Ka IP for class R 100 amp fuse is 14 Ka, therefore the panel would need to be rated at 10 Ka. Summary for this example, we can see that using an HMCP in combination with a starter allows for a higher short circuit rating. The bottom line is that this standard is not about breakers versus fuses, but rather determining the short circuit rating of the components in the panel and then assigning the short circuit rating to the panel used upon the guidelines in the UL 508 standard. The intent of this standard is to provide an additional level of safety for you and your customers. So it's kind of confusing here. So to recap on this, for SSER, power circuit and only area of concern is our only area of concern. Control circuits have small ampacity devices, small wire, and greater impedance due to the amount of wire in which they will limit the current. For branch protection, greater than 30 amps for any 10 Ka or less device. Fuses don't limit current to necessary level. Thus, breakers and fuses are on a level playing field. Breaker and starter combinations can offer higher interrupt ratings. Just make sure that you go and get the breaker series ratings from the manufacturer. For branch circuit protections at greater than 30 amps or less than 30 amps for any 10 Ka or less devices, rate panel 10 Ka or lowest device. Use CL breakers, current limiting breakers, or fuses to boost rating if unsure of available fault current. Note, many motor loads require Class R fuses. Why use a breaker? Prevent single phasing. You can't just bust one pole, it'd be really rare. Provides motor protection, provides ground fault detection, resettable. So if you have a circuit breaker that has ground fault circuit protection or the ability to detect it, you can detect it. It's resettable. It's dead front, no exposed parts, space savings, uptime, accessorization, and testable. So a circuit breaker provides a lot of good things for a motor control panel. And certainly people would be more wanting to use them. Also, they can be used as an isolation source. You can lock them out. or you can't really lock out a fuse. Breaker terminal options. You can get these multi-wire connections for the secondary side. And you can connect multiple wires off of them instead of just one wire. UL 508A, common issues panel manufacturers make when building UL 508A control panels. And here we have a general overview of the standard. So we're just driving it home, the UL 508A standards. That's the primary purpose of this course, is to help you become familiar with the UL 508A standards and help you be able to maybe apply to a MET certification company or something. Okay, so obviously this UL 508A code is for safety. It's a widespread acceptance by local authorities. So if you say you're a UL 508A control house and you've got the Canadian standards, so you're ULC or CUL US, you are elevating your ability to sell panels. Mark it as evidence that a product complies with an accepted standard. Let me reemphasize, it doesn't make it work, it just means that it's safe. Compatible with NEC, comprehensive service. UL Mark is recognized worldwide. It's a one-stop shopping for North America and Canada. So if you've got a UL, CUL US listed control panel, that's impressive. That's an impressive certification, and it's something to be cherished and point out to your salesman that you have that capability. So these are the different logos, right? So if it's a classified panel, it's UL classified. It's just listed, it's UL or recognized. Field evaluation, the FEP, field evaluated product. That means that if you shipped a panel and you didn't have UL capability and you sent a UL investigator or MET Laboratories or some NRTL out there, then they would put a field evaluated product label on it. Preliminary evaluation, evaluation at the manufacturer's facility, and then evaluation at the installation site. That's a very expensive process. You're probably better off becoming a UL listed program than to perform field evaluation. List it, or you could pass the cost on to your client. Listing programs provides evidence of a third-party certification. It's a one-of-a-kind panel or standardized designs, open and closed panels, and an advertisement. So if it's a listed program, you know, you have a unique control panel. You might be just UL recognized. So a typical, you know, process, if you wanted to become a UL shop, you would get a client request. So the MET Laboratories or UL would get a client request. They would respond by giving you application forms. They would open up an engineering project. Then they would do an engineering visit and maybe a seminar. And they would do some testing if it was necessary, and then prepare the report and then do a final review. You get monthly or I don't remember what it was exactly. You get client visits, these follow-up services under field rep supervision. So they'll pop in and they'll just start checking things. And so it's somewhat of a distraction because you got to stop what you're doing. You got to pull all your files and you got to walk them through, and they might flag a system or flag a design you're doing, which could slow production down, but it is what it is. So frequency of visits required 1 per quarter, maximum 3 per quarter. So every time they visit you, they send you a bill. So make sure that you have your ducks in a row and you're ready for these guys when they show up, because they can start increasing the number of visits that they have. If panel is shipped without a label, you must ship it back to the manufacturing location or request a field inspection. So don't ship the label out there and have it installed. Don't ever do that. You can't do that. It has to be in your facility. What is an industrial control panel? It's motor controllers, overload relays, fuse disconnects, circuit breakers, button switches, timers and controllers, wiring, terminals, and closures, just as we talked about on that Eaton UL 508A section. So this section right here is straight out of the NEC. It's Article 430. So a UL panel can be as short, small as just one motor control center, or it can be all the way up to the motor feeder, part E, all the way through part C, right? So it can be just as simply part B and D, or part G and part B and G there, or part E, part 1, part D, part B, part G, part F, part G, part A. Well, not part A, because you don't care about that, because that's the actual motor in the field. So there you go. So it's broken out where you start out at the very top. So if you're wondering on motor feeder short circuit and ground fault protection and the rules associated with that in the NEC, go to Part E of Article 430 of the NEC. UL 508A standard for industrial control equipment. UL 508AC is for power conversion equipment, like an inverter or rectifier or something like that, or solar panels, chargers, things like that. UL 508B is the outline of investigation relays for use in information technology equipment, IT type stuff. What you would probably fall into is a motor industrial control panel, UL 508A, and it's been updated. Obviously this is a little old. This first edition was April 25th, 2001, and it was revised in 2005 and I think 2006. Maybe it's been revised again, I don't even know. Industrial control procedure. You got UL 508A, you got different parts within that procedure. Part 1 is the general use, Part 2 is specific use. Supplement SA and Appendix A are specific component requirements. Then you've got that Supplement SB is short circuit ratings, and Appendix B is used for unlisted components. Then you've got your descriptive procedure, information to provide specific components not covered in UL 508A. So here's a breakdown. You got Part 1, general use industrial control panels. Part 2, specific industrial control panels. So you might have crane control panels or air conditioning equipment, things like that. You want to make sure that, if you're doing a fire pump controllers, you're using the QYZS components. It's not intended for, an industrial control panel. So this is a common mistake, right? Usually, components for industrial control panels have that NRBX the CCN code. So here's another breakdown, which is just basically go through this. Got listed components bear the listed mark of UL, required marking, UL's green book directory for listed products. So if you look at the green book, you'll find all the electrical construction equipment directory. The orange book is the electrical appliance and utilization directory. And then for your recognized components, you'll follow the yellow book. Yellow book is primarily what you follow. Nowadays with everything online, you can pretty much find everything online and go directly to ul.com and find out if it's recognized. So components are not required to bear backwards UR, right? So if they're recognized components, they don't have to have that UR. Conditions acceptability, they just have to be listed or recognized in the UL website or the yellow books. Unevaluated components, they're neither listed nor recognized. So I guess they have the dice here, you're taking a gamble, right? But as long as you put it in one of those limited circuits, the class 2 circuits, then you can use an unevaluated component as long as it's 30 volt AC or lower. But again, I don't like taking gambles, so if it's not listed or UL recognized, I won't use it. Your category control number, CCN, we talked about this, are 4 or 5 digit numbers. So if it's listed, it will have no suffix. If it's recognized, it'll have with a 2, it'll have you'll know it's recognized. If it's got a 7 at the end, it's listed for Canada, and if it's got an 8, it's listed recognized for Canada. So, and these are the different breakdowns. So if you're NIMX, your industrial control equipment. NITW is industrial control panels, industrial control panel enclosures. Terminal blocks would fall into the XCFR2 section, etc. Component requirements, you got SA1 listed components, SA2 recognized components, SA3 other components, and they give you a breakdown on these tables. So table SA1, UL508A, is an enclosure listed junction and pull boxes. Per UL 50, its CCN number is BGUZ. These enclosures are not required to have doors and would not be able to house power circuit fuses and similar components. So you want to make sure you're using the right enclosure. So for a listed industrial control panel enclosure, it needs to be NITW. And here's some more examples of that section. And you got your component requirements, SA1, SA2, SA3, SA1 listed components. You got your components that comply with specific requirements. So if you have a ground fault circuit interrupter, paragraph reference 28.6.6, UL standard UL 943, its CCN number is KCXS, then it can only be used in the Class A receptacle type only. Recognized devices noted. So there's a bunch of rules on what you can use and what you can't use and where you can use it. You need to be aware of that. So electrical components other than covered in SA1 and SA2. You got mechanical parts having no electrical connections and containing no liquids or flammable gases. Polymeric mechanical parts. So direct supported insulated materials per section 13. Insulator in lieu of spacings and mechanical barriers. So here we kind of break it out. Part 1, general use panels. General use panels are, you have the introduction, the construction, rating, and marks. Again, it's only good for 40 degrees C panels, 600 volt or less, and it follows NEC. Gives you a breakdown of all the different components and what they are in a control panel. And so number 1 is your load, right? Your motor or whatever it is. 2 is your field terminations. So if you look at 2, you have multiple 2s, right? You have a 2 right there above that motor. You also have 2s in the control circuits, right? And 2 over on the far hand right. So you want to make sure that when you're doing field wiring terminals that you understand that they comply with different types of circuits, power and branch circuits. Section 8 is corrosion protection. Section 9, support and securement of components. Section 10 is spacing, and Section 11 is conduit bushings. Insulation barriers, often used in lieu of through air spacing. So they give you direct support on our, guidance on when you're using these insulated barriers. Intended for direct support, maintain position and or support uninsulated live parts. All generic insulating materials are suitable for use as barriers. Materials fall into as long as they're per table 13.1. Grounding, general. Terminals must be suitable for field wiring. Continuity between all non-current carrying metal parts by metal to metal contact or internal bonding wire. Internal bonding conductor must be sized per table 15.1 or no smaller than input power wiring. Cord connected equipment must have grounding conductor with molded on attached plug, no polarized plugs. There's a lot of rules there. Section 14, grounding general. Terminal size shall be in accordance with table 15.1 based on the overcurrent protection provided for field wiring conductors. Exception is terminal need not be larger than that size for the input wiring. Marking in accordance with paragraph 54.5 shall be provided. Bonding conductors' color shall reflect normal conventions. So if you have a bonding grounding conductor, it needs to be green or green and yellow, right? I like the green with the yellow stripe. Grounding size of terminal for bonding conductors. Terminal size, again, is 15.1 based on the overcurrent protection device. Rating of branch circuit protection specifies drawings when not provided. Amp rating equal to ampacity of field wiring anticipated and when use branch circuit protection is provided. Transformer secondary grounding. You are required to ground the secondary side of that transformer. There are some cases that you can't ground that secondary. Some PC boards just won't allow it, like on a rectifier firing board. Required for secondary circuits containing field wiring terminals. Secondary voltage is less than 50 volts and primary is ungrounded, or primary voltage is greater than 150 volts to ground. That's when you require it. Secondary voltage is greater than or equal to 50 volts and the secondary circuit is able to be grounded and the voltage is to ground is less than or equal to 150 volts. So this is what they're talking about. Primary voltage is greater than 150, secondary is less than 50, or greater than 50, and volts to ground is greater than or less than or equal to 150. So you can see they grounded it. And that ground wire size has to be like a number 10 or something. Transformer secondary grounded conductor required when secondary is 3-phase 4-wire Y connected and center point is used as a conductor. Secondary is 3-phase 4-wire delta connected and midpoint of one phase is grounded. Wire size per 75-1 based on secondary current rating. Exception for control transformers rated less than or equal to 1 kVA, 14 AWG may be used as bonding conductor. In addition, a bonding conductor need not be larger than the secondary phase conductors. So that's the exception there. Identification of grounding and ground terminals. Wire binding screw acceptable for 10 AWG or smaller wires. For field wiring connections to grounding secondary circuits, the grounding side common lead wire insulation shall be white or gray. Enclosures need to be UL 50 rated, so make sure you buy UL listed control panels per UL 508A. Hinge door requirements, you need to make sure that that hinge door has that you're using a hinge door for power circuit fuses, circuit breakers and power circuits, motor overload devices, and timers, chart recorders accessible. Some doors are not hinged, and the whole door can come off, and it can be no door at all, and you don't want to do that. So that's not a good requirement. Enclosure openings, type 1 enclosure conduit openings for standard dimensions. So a type 1 enclosure opening is an EMA 1. When provided, conduit fittings shall comply with UL 514B. For other than type 1 enclosures shall have conduit openings filled per table 19.1. So if you have an enclosure type 2 or 3R, then you need to follow these rules. All holes in conduit shall be below all uninsulated live parts. Conduit openings shall have the lowest uninsulated live parts shall be provided with conduit fittings having an environment rated that complies with table 19.1, or the enclosure shall be marked in 53.2 with instructions for installer to apply fittings complying with A or B. So if you have a 4X, all holes or conduits shall be provided with conduit fittings having an environmental rating that complies with table 19.2 or as specified in the enclosure manufacturer. The enclosure shall be marked as in 53.3 with instructions to apply fittings complying with D. So sometimes we're not the ones that apply these conduit openings, so you need to make sure that your end user is aware of this, that they can't just go poking a hole in the top of the panel or something. And here's opening for components and enclosures with environmental ratings other than type 1. So if it's rain type or wet location, so you need to make sure that they use the proper enclosure and conduit fittings. Enclosures may be derated, so you can derate. You can just go up there and say, I call this a type 1, which is what one of the inspectors used to do to us all the time, but they quit doing it. Distance between uninsulated live parts and enclosure openings. So you got minimum distance from opening to uninsulated live parts is a 1/2 inch. You need to go through these tables. Ventilation openings. Ventilated enclosure is considered to be type 1 unless otherwise investigated. So if you've added a filter and a fan, it's now a type 1, unless there's a UL listing on that ventilation, that air and fan, that makes it a NEMA 4X. I suspect somebody has something like that. Forced ventilation cannot be directed to the operator space. 30 inches centered on operator from floor to 6.5 inches high. Ventilation openings and panels containing power circuit components shall comply with section 22. Ventilation openings shall comply with accessibility requirements. Barriers used with ventilation openings. Must provide barrier for ventilation openings less than or equal to 12 inches from marking parts. Barrier must be constructed of 0.053 inches of thick sheet steel, 0.025 inches of thick sheet aluminum, 0.125 inches of thick polycarbonate, or a 1/4 inch thick material other than polycarbonate. Barriers used with ventilation openings. So here you have a ventilation opening. You got your live part at the top, and you can see there's a slight angle there. So that's acceptable. And another acceptable method would be the ventilation opening there, where you can't, you just can't stick your hand in there and touch that live part, right? Observation windows, type 1 unless otherwise evaluated. So if you have an observation window that you've put in there, like a glass or a Lexan type window, it has to be rated by UL. Otherwise, you're going to derate that panel to type 1, even if it's a NEMA 4X panel. And obviously, you have to follow all these rules, right? You have to have a 5 VA flame rating less than or equal to 380 square inches, mechanically secured, adhesive requirements, additional investigation. So if you use some type of a glue or a double-sided tape, you're going to run into troubles. Bonding, polymetric enclosures require bonding between all conduit openings. So if you have a fiberglass NEMA 4X panel and you have a bunch of those conduit fittings, those what do they call those? Myers hubs. You need to make sure that they all have that ground kit, and you jumper all the grounds together, and then you bond that to a suitable Burndy grounding post. Wire bending space. You got to make sure you've got plenty of wire bending space per table 25.1. Enclosure environmental control devices. You got fans, heaters, air conditioning devices. They have to be, if they're a fan and blower, they have to be per UL 507. Just a fan motor per UL 1004. Fan/motor thermally protected, impedance protected, or motor overload protection per section 34. Enclosure air conditioners shall comply with UL 484. So you can install these ventilation devices and cooling devices, but they need to be special UL listed devices. Enclosure environmental controls. Again, the enclosure heater shall comply with UL 499, mounted at least 2 inches away from all plastic materials. Internal wiring greater than 200 degrees C. So if you've got a little space heater in there, you need to make sure that it's got that special heater wire. Enclosure environmental controls. Air filters required when panel contains drives, PLC power supplies, or IT equipment, and panel or any other integral component has a fan. Enclosure thermal insulation secured by mechanical means greater than or equal to 1/2 inch away from uninsulated live parts. Enclosure maintenance lights. If you have an incandescent lamp holder, it needs to be UL 496 listed. Fluorescent lights need to be UL 1598 listed. Lighting voltages shall be less than or equal to 150 volts. And they have to comply with power circuit requirements unless specified from a secondary or control transformer. Field terminals or field wiring. Terminals must be provided for connection of wire in the field to input and output circuits. They need to be accessible. The connections made without disturbing other equipment. So when your field guys are connecting, they shouldn't be having multiple wires that they're having to deal with. They have no wires on their field side, and they can easily connect to it. Terminal blocks shall comply with UL 1059 and will be suitable for field wiring. Pressure wire connectors, if components other than terminal blocks, must comply with UL 486A, B, and E, or E. So if you're using those pressure type wire connectors, they have to be UL listed appropriately. So here you have field wiring. If you have a USC 10 catalog number, then it's a 10 to 8 gauge wire, copper, and it's rated for field wiring. That FW is for field wiring. You have to have a torque value specified. Voltage is 600 volts. Amps, in this case, we said USCC 10 is a 50 amps. It's the UG is I think it's called user guide, I think, and it's B and C. And then you got for the CA standards is 2. So marking, company name or trademark, and catalog designation. So these field wiring terminal blocks have to be rated for that, and you have to pull the terminal acceptability charts for them. Wire range. Make sure that the wire size or range of the wire sizes for which the terminal block has been evaluated. So don't try to stick something in there that's too big or too small. Make sure that the wire type has been investigated. For if it's only for copper, make sure they can only use copper. If it's copper or aluminum, then they can use either one. Factory or field wiring. These terminal blocks are rated for code 1 factory wiring only, or code 2 for both factory and field wiring. If your head's not getting dizzy by now, it should, because this is a lot of stuff. This UL508 thing is so hard to make a mistake on. So, like the UG is the use group, right? So, and there's so many areas where you can make a mistake. So you really want to have somebody like an NRTL in your facility inspecting your devices and helping you get through this process. Torque, TQ, the tightening torques for the field values. You always want to provide that torque value. The V, voltage. Terminal blocks have voltage ratings for which they have been found acceptable, so you don't want to exceed that. The UG is the user group, right, or use group. Current A is a maximum value of per pole current for which the terminal block has been found acceptable. You don't want to exceed that. So you have different use groups, the type of end-use application for which the specified voltage and levels. So if you have a use group of B, that's for commercial appliances, including business equipment, electronic data, or processing equipment and the like. For most of the stuff we have, it's a use group C, so it's industrial general use. So again, you got your USC10 is 14 to 8 gauge wire, copper. Your FW, your field wiring, it's suitable for field wiring. It's got a torque value, voltage is 600 volts, amps is 50 amps. It's got a use group of B and C, so the B and C is for industrial panels, and then it's got that CA rating at the end of it. Field wiring, wire binding screw, number 8 screw for 10 AWG and smaller wire, number 6 screws for use of 14 gauge AWG. Assume all conductors will be copper and 14 AWG minimum. So make sure that they know that that's what they're going to be. So don't put a field wiring terminal block out there that can only handle a 16 gauge wire. Conductor size power circuits for motors, fixed electrical space heating equipment, and lighting loads. Field wiring shall be based on 125% of full load amps. Other load must be 100% of amp rating minimum for listed devices provided with a marked wire range. The wire range shall accommodate the necessary wire size. So size per table 28.1, load side of Y delta starter based on 58% of full load amps. So take your full load amps times 125% times 58%. Separation of circuits between class 1 and class 2 circuits. So you need to have uninsulated live parts or any other circuits, and factory installed conductors unless all conductors rated for highest use voltage. If you've got cord connected equipment, so you've got some type of a 10 AWG 2 conductor with a ground cord. So use is permitted, use is not permitted or contained in the NEC. You have to look it up. S and SJ hard and junior hard service terminates on an attached plug that complies with UL 4898 and UL 1682, provided with strain relief so somebody can't tug on it, right, and then pull it out of its connector. Outdoor use requires outdoor or W marking on the cable. Type 6 and 6P requires water resistant marking on the cable. Type 12, 12K, and 16 requires O marking on the cable. And you have to size them per section 28.3 in tables 28.2 and 28.3. Field wiring some more. Interconnecting cables terminating connectors external to the enclosure on which there are one or more exposed contacts shall not constitute a risk of shock between any exposed contact and earth on either the connector or the receptacle while the connector is out of its receptacle. If you got receptacles, it may be general use or multi-pin type, complying with UL 498. And you can read through this as you want. Must be film multi-type, must comply with paragraphs 28.5 and 8. Must be marked accordingly. GFC type requires an outdoor use type panels. The internal wiring should be copper, should be rated for voltages involved, has to be rated a minimum 90 degrees C, has to be listed machine tool wire or general use wire, recognized American wire, AMWM, welding cable, or bus bars. Those are the types of cables you can use. If you're going to do a soldered mechanical secured connection, we talked about this before, you must wrap around that post 180 degrees. You can go a little bit further if you want. You can go up to 250 degrees C or even almost close to a full circle, but you must have at least 180 degrees C around it. Then you can put it. Wire bonding screws using solid wire or stranded wire with stranded screws or strands secured. Terminals and components with pressure connectors or quick connects. Crimp-on connectors, closed loop type or fork type where the ends engage the terminal screw or head and Here's a common mistake. You have a spool of wire, you feel good about it, but you don't keep the traceability. You don't keep the paperwork in the files after the unit ships. So make sure you copy which spool of wire you're using and keep that with the files for that control panel. Internal wiring, you want to make sure that you route it away from sharp edges or through grommets. If subjected to movement, minimum of 1/32 inch thick insulation. Stranded wire separated from other conductors and circuits operating at different voltage levels, unless all the conductors rated for the highest use voltage. So there's one of those problems that I have with UL. So you've got all your wiring is rated for 600 volts, but some of the wires are sensitive PLC circuits. Per UL, you can bundle them all up into a one wireway, but you might have magnetic interference and noise problems and all kinds of control problems. So again, UL doesn't care if it functions, they just make sure that it's safe and nobody's going to get shocked. So sizing minimum 18 AWG. This is internal wiring, is 18 AWG. Size per table 29.1. Bus bars per 29.6.2, 100 amps per inch squared cross-sectional area. That's pretty conservative, 1,000 amps per inch squared cross-sectional area. So if you have a 1 inch by 1 inch by 1 inch, you can carry 1,000 amps with that bus bar. Disconnect switches. Main disconnect is optional. If not provided, the BCP, branch circuit protection, may also be omitted. Need instruction on the wiring diagram that the protective device and disconnect switch is to be provided by a installer for each ungrounded conductor. The handle, if operated vertically, the position, the very highest position it can be on, can't be any higher than 79 inches. So that UL guy right there is pretty doggone tall. Disconnect switches, limited inverse time circuit breaker. Its CCN code is DIVQ. Recognized instantaneous trip circuits, a DKPU2 when tested as part of the combination motor controller. Listed miscellaneous switch, WPZX, and molded case switch, WJAZ. Your disconnect switches, manual motor controlled marker suitable of motor disconnect, NLRV, only when installed on the load side of the branch circuit device. Self-protected combination motor controller, NKJH, note disconnect handles and operating mechanisms shall comply with the requirements of UL 489 or UL 98 for use with a disconnecting device involved. Sizing of disconnect switches. Circuit breakers, full load amps, less than or equal to 80% of the breaker rating. Molded case switch units, miscellaneous switch and manual motor controllers rated 150% of full load amps. Self-protected combination motor controllers may be used up to 100% of the mark rating. A lot of people mess up on this because those molded case circuit breakers can only be rated for 80% of its full load amp rating. So if it's a 100 amp breaker, you can only run it at 80 amps. And that's an RMS value. Disconnect switches. Location opens all ungrounded lines. provided for each source, grouped in one location if more than one, and interlocked or provided with warning markings per paragraph 55.4. Branch circuit protection. If they're listed, they have to be listed. Inverse time breakers, DIVQ, recognized instantaneous trip breakers would be the DKPU2 when tested as part of a combination motor controller. Listed branch circuit fuses, class CC, JK, and RK5, etc. Their code would be a JDDZ. Semiconductor fuses, JFHR and JFHR2 when used on variable speed motor drives circuits, and whose installation instructions recommend their use. Self-protected combination motor controllers will be NKJH. Branch circuit protection. Device not suitable for branch circuit protection is a supplementary protection device, a QVNU2, also known as a mini circuit breakers or IECC style circuit breakers. So there are many circuit breakers that are UL489 rated, so we've seen that before. So I guess when they put out this original presentation, those weren't applicable. Miscellaneous miniature microfuses, or IZLT2, manual motor controllers and instantaneous trip mechanisms are NLRV, all which cannot be used as branch circuit protection. They're circuit protection. Branch circuit protection, single motor circuit based on component restrictions of motor controller or based on table 31.1 for drives not marked with specific branch circuit protection requirements. Use table 31.1 based on drive input current ratings. Note, when using self-protected combination motor controllers, must provide cautionary markings per paragraph 55.7. Make sure you go over that whole section on markings. Note, when using instantaneous trip circuit breakers as part of the investigated combination motor controller, trip settings must be set based on the rating determined above and cautionary markings provided in paragraph 55.6. A lot of things to consider here. Branch circuit protection, motor groups, 20 amp, 125 volt, 15 amp, 600 volt. All motors rated 6 full load amps or less, and branch circuit protection is coordinated with motor controller restrictions. Rating and type of branch circuit protection coordinated with motor controller restrictions. So, group installation markings. This is what you should put. Suitable for motor group installation on a circuit capable of delivering not more than X RMS symmetrical amps, and then you fill in these values, right? May include, when protected by class, the type of fuse rated at whatever the amp is. Motor groups. All motor control devices marked for a group installation and the size of the branch circuit protection does not exceed the smaller of the two ratings determined above. Size of the branch circuit protection equals the sum of the branch circuit protection required for the largest motor plus the full load amps of all the other loads. So what you do is you take the largest motor, and what I always do is I multiply it times 1.25, and then I take the full load sum of all the full load amps of all the other loads. Size and type of branch circuit protection is specified in the group installation marking on all the power components. Branch circuit protection, motor groups, drives incorporating 2 or more common bus inverter sections. The smaller of the following: sum of the BCP or branch circuit protection determined by the largest motor plus the full load amps of all the other motors reflected back to the input cannot exceed the maximum specified branch circuit protection per the installation instructions. Receptacles. Branch circuit protection device rated not more than ampere rating of the receptacle. So if you have a 20 amp branch circuit protection device, may protect a 15 amp receptacle. Branch circuit protection device may be rated less than rating of receptacle if intended for use with a specific piece of equipment and marked per paragraph 59.1. Heater loads, not less than 125% of the heater load current. So when you install that branch circuit protection, it can't be less than 125%, not larger than 60 amps. This does not apply to industrial ovens or furnaces. This harmonizes requirements with NFPA 86. Not larger than the capacity of field wiring. So, branch circuit protection again for appliance load. This is giving you all the requirements for these branch circuit protection over current. So it's marked on the appliance, not more than 20 amps for appliance rated less than 13.3 amps, 150% for appliances rated greater than 13.3 amps. Lighting loads, max 20 amps for incandescent, fluorescent, high intensity discharge lamps loads and not exceed rating of an intended file wiring. Max 50 amps for heavy duty incandescent or infrared lamps and not exceed rating of intended field wiring. Overcurrent protection of feeder. Listed inverse time breaker, DIVG, a DIVQ, branch circuit type fuse, JDDZ, cannot be manual motor controller or combination motor controller, those NKJH style motor controllers. On a load controller listed and recognized per UL 508A or UL 508AC, see Table 33.1 for various types of loads and suitable load controllers. And you also have the Y delta motor controller. Motor protection. Provide for each motor, mechanically, electrically operated overload relay, trips at 115% of full load amps. May be provided as part of a drive, not all drives have motor overload protection. Drives are marked or the installation instructions indicate motor overload is provided. This table is straight out of the NEC Article 450, overcurrent protection on primary side of Table 35.1. So if you have a transformer, then you're only protecting the primary side. If it has 9 amps on the primary current, then you can go only to a maximum of 125%. If it is a maximum of 2 to 8.99 amps, then you can put 167% fuse size. If it's less than 2 amps, you can go up to 300%. If branch circuit protection is provided on the primary side only, secondary windings must be single phase or 3-phase delta with primary connected in delta also. The secondary wire sizes per 29.2 based on the branch circuit protection reflected from primary to secondary side, otherwise protect per 35.22. So, overcurrent protection on primary and secondary side. So here you have a transformer that has both primary and secondary fusing. So if you have 9 or more amps, your branch circuit protection needs to be at least 2, or it cannot exceed 2.5% or 250%, 2.5 times the full load amps. On the secondary side, if it's 9 or more amps, it would be 125%. So this table's slightly different now. It's changed. You can look at Article 450 and take a look at that table as well in the new NEC. I'm sure the new UL standard has changed slightly as well. Capacitors. Oil filled must be recognized components per CYWT2 when in series with motor windings rated minimum 5 kA when used in motor circuit. When connected directly across the line rated minimum 10 kA. Dry type capacitors connected across the line shall comply with dielectric voltage withstand test per UL 508A per UL 508. Resistors including brake resistors and Y delta transition. A braking resistor we talked about in that variable frequency training class. Resistor body considered to be an uninsulated live part. Insulating materials and internal wiring shall not contact resistor body. Internal wiring for duty cycle resistors size per Table 29.1 based on full load amps multiplied by derating factor of Table 36.1. Surge control devices. MOVs recognized. They must, going to install surge protection, they need to be UL recognized XUHT2. Metal oxide surge arresters need to comply with IEEE C6211 1993. All other surge arresters shall comply with IEEE C62.1. Surge arresters connected via minimum 14 AWG wire. Field wiring terminals. Field wiring terminals suitable for field wiring, same as the power circuits. Terminals suitable for minimum 14 AWG. For terminals rated less than 10 AWG, size and marking per Table 37.1. Terminals for connection to Class 2 circuits shall be suitable for field wiring or shall be segregated. Minimum separation. Permanent 2-inch separation between Class 1 and Class 2 field installed wiring is maintained. Separate conduit openings for Class 2 conductors. So if you're going to try and do a Class 2 circuit, you really got to do some separation here. Internal wiring, same as Section 29, except for 16 AWG or smaller may be 60 degrees C. Class 2 and low voltage limited energy circuits may use power limited circuit cables and communication cables when separated or permanent segregation from internal wiring or other circuits. Electronic programmable I/O and static control devices rated less than 5 amps may be sized per table 38.1. Disconnecting means control circuits supplied with separate source shall be provided with a disconnect means per section 30. Section 40, overcurrent protection. Types of branch circuit protection devices. Miscellaneous microfuses, supplementary protectors. When provided on load side, a branch circuit protection device must be evaluated for intended use. Short circuit rating is a concern. Overcurrent protection. Location, all ungrounded lines. Load side of branch circuit protection. Sizing, less than 20 amps for branch circuit protection devices and non-isolated secondary sources. Based on wire size, fused at 100% per table 29.1 or 38.1. General use receptacles and control circuits have protection rated not greater than rating of receptacles and are intended for programming and diagnostic use only and are marked per 59.3. Review application based on markings and supplementary protector. Overcurrent protection. The following parts for the QVNU2 guide card. Max amps. The designation in the amp rating for each protector or family of protectors has been tested. Trip current, TC. Trip current is coded as percentage of the amp rating. 0 is trip current is less than 125% of amp rating. 1 is tripping current is in the range of 125% to 135% of trip rating. 2 is trip current is more than 135% of amp rating. Sizing of overcurrent protection. Common control circuit protection size per table 29.1 or 38.1 or may apply on branch circuit protection per table 41.1 without remote control devices. May rely on branch circuit protection per 41.2 with remote control devices. So here you have branch circuit protection. You got your starter, you got your motor, you got your control wires. Do not leave the enclosure. Size branch circuit protection per table 41.1. Control wires leave the control enclosure, then you need to size branch circuit protection per table 41.2. Note same values on table 29.1 except for 14 and 12 AWG. So if you've got a remote start-stop station, then you're leaving the panel, right? Overcurrent protection control circuits. Control transformer with isolation secondary, primary side only per table 42.1. Primary protection may provide secondary conductor protection based on primary protection reflected into the secondary side. Reflected protection must correspond with wire size on table 29.1. Primary and secondary side per table 42.2. Overcurrent protection control circuits. Power supplies installed in enclosures that is non-ventilated, ventilated and non-fan forced or fan forced with filtered ventilation. Output fuses less than or greater than or less than or equal than 50%. Power supplies evaluated at UL 508 and UL 508C need not be restricted as noted above. Low voltage limited energy circuits, section 43, control transformer per UL 506. Power supplies per UL 1012, also UL 6095 and UL 508A. Isolated secondary source per UL 508A. Sealed batteries per UL 1989. Lithium batteries per UL 1642. Current transformers per UL 506 and current transformers with a 5 amp secondary winding. Low voltage limited energy circuits per section 43. Maximum open circuit voltage of 30 volts RMS. Over current protection size per table 43.1. So open circuit voltage peak 0 to 20. Maximum current device amperes is 5 amps. 20.1 to 42.4 peak is 100 per VA. So where V is equal to the peak or DC open circuit voltage, secondary voltage. So it's 100%, right? Section 43, low voltage limited energy circuits, components, and wiring limited within LVLE circuit and not required to be investigated. Internal wiring shall be separated from all other circuits per paragraphs 29.5 and 38.1. Field wiring terminals or LVLE circuits shall be segregated from other circuits or shall be marked for use with Class 1 wiring. Class 2 circuits evaluated per UL 1585 or UL 1310. Components and wiring located within Class 2 circuits are not required to be investigated. Internal wiring shall be separated from other circuits per paragraph 29.5 and 38.1, field wiring terminals of Class 2 circuits shall be segregated from other circuits or shall be marked for use with Class 1 wiring. 45, Section 45 covers switching devices, types, relays, contacts, push buttons, solid-state relays, timers evaluated per UL 508, and intended for general industrial use, snap and special use switches evaluated per UL 1054, clock-operated switches evaluated per UL 917, temperature-controlled evaluation per UL 873, process control equipment evaluated per UL 3121-1. Switching devices, ratings, voltage and current rating applicable to the load, controlled and corresponding to the type of load is specified in Table 45.1. Note standard pilot duty rating designations, Table 45.2 and 45.3. Note horsepower and VA rating conversions on Table 45.4. Location, contacts arranged to open the ungrounded conductor. Switching devices under voltage protection. Hard start required following under voltage, power failure or motor overload relay cycling. Exception 1, blower motors with fully guarded moving parts. Exception 2, pump applications. Exception 3, lighting applications. Loads. Pilot light per UL 508, lamp holders per UL 496, electrically operated valves per UL 429, solenoid evaluated for the intended use, time recording indicating and recording devices per UL 863, electrically operated counters, audible signals, operating coils connected to the grounded sides of the control circuit, and rating of the control circuit as marked on the coil. So you got to make sure you specify the right component and make sure it's UL listed or records. Miscellaneous devices such as surge control devices, TVSS, MOVs per UL 1449, EMI filters per UL 1283, and dry type capacitors must comply with dielectric voltage withstand test per UL 508. Resistors comply with paragraphs 36.2.1 through 36.2.3. Section 48 is pneumatic switching devices for greater than 300 psi must comply with UL 508. Section 49, supply ratings. Each supply source shall be rated in volts, total full load amps, amperes or horsepower rating of the largest motor number of phases and frequency, motor rating per table 50.1, short circuit rating required after April 2006, see supplement SB. Section 50, individual load ratings, output terminals to each individual motor load rated in volts and amperes or volts and horsepower, output terminals to be each individual lighting and heater load rated in volts and amperes or volts and watts, output terminals to each individual control circuit rated in volts and amperes or volts and volt amperes. Section 51, rating for control circuit outputs, output terminal loads rated in volts and amperes or volts and volt amps. Section 52, general markings, manufacturer's name, complete electrical rating of each source, the field wiring diagram number, the factory identification, and the enclosure type rating. See Table 52.1 for specific marking requirements. This is a big area where people mess up and they don't put the proper markings on a panel. Enclosure markings, enclosure type ratings other than type 1 conduit hub, panel sections, polymetric enclosures, continuity of grounding. Section 54, field wiring terminal markings, copper, copper aluminum, 60 degrees C and 75 degrees C, terminal torque ratings, and ground terminals. Cautionary markings, cautionary warnings, at least at 1/8 inch high. Multiple sources would be a cautionary warning. Instantaneous trip circuit breakers used for branch circuit protection. Self-protected combination motor controllers. Section 56, fuse holder markings, the voltage and the current for miscellaneous fuse holders. Current only for branch circuit protection fuse holders. So you want to have a little diagram or a plate where you list all your different fuses and the types of fuses that they can install with the voltage and current ratings of each one. Section 57, switch markings, on or off. You want to make sure that the switch that you buy or the disconnect switch actually shows on or off. Switch not intended to be operated under load or marked do not operate under load. Section 58, overload relay heater table markings. Again, just like your fuse table, you need to have a table inside that control panel that shows you required overload heater table. So required for overload relays having replaceable current elements. You don't want somebody to put the wrong element there. Receptacle markings. General use receptacles protected by branch circuit protection rated less than the rating of the receptacle and intended for use in control circuits marked with the ampere rating of the branch circuit protection. Multi-pin receptacles marked to identify the intended load connections. Receptacles rated more than 20 amps rated for disconnecting use only, not for current interrupting. Field provided components, section 60. Panels where the disconnect means branch circuit protection or motor overload protection is provided for the installer shall be marked to include the size and type of the protection. Wiring diagrams showing components not provided on the panel are marked to indicate they are provided by installer. Section 61, your schematic wiring diagrams. You want to provide complete wiring diagrams and put them in that little door of the UL. Here's a breakout of specific uses. Section 63, general requirements. Requirements cover type 1 metallic enclosures, only sheet metal and cast. All other materials rating evaluated per UL 50 may be modified by enclosure openings. Section 19, ventilation openings. Section 21, observation windows. Section 23, polymetric enclosures must be evaluated per UL 508 or per UL 508. Cast metal enclosures minimum 1/8 inch thick, 1/4 inch thick conduit openings. General requirements, sheet metal enclosures minimum thickness. For non-ferrous, you have a different thickness. You have to have supported versus non-supported surfaces. Do not confuse supported surfaces with supporting frame. Fasteners for doors and covers must be captive. Doors greater than 48 inches long shall be provided with closures at 2 or more points. 63, section 63, general requirements. Flanges are noted in table 63.3. Flanges run the entire length of all edges. Gaskets must be used in lieu of required spacings between mating enclosures, door base, and surfaces. Markings, specific enclosure marking type required. Special use panels. If you have special use panels like industrial machinery, you want to follow section 65 to 72. Service equipment, follow section 73 to 79. Elevator controls is section 80. Flame control, section 81 to 83. Marine use is 84 to 87. And air conditioning and refrigeration equipment is section 88 to 92. And then you've got your short circuit current ratings. We've already gone through this. How do I calculate a short circuit current rating of a control panel? There's those 3 steps that we follow. Determine the individual short circuit rating of each individual component in a system. All power circuit components, including disconnect switches, branch circuit protective devices, branch circuit fuse holders, load controllers, motor overload relays, terminal blocks, and bus bars shall have a short circuit rating expressed in ampere or kiloamperes and the voltage. You can exclude transformers, dry type capacitors, resistors, voltages, varistors, and voltmeters. Calculate the available short circuit when taking into account current limiting components like control power transformers, fuses, and circuit breakers. Compare the values obtained in the steps 1 and 2 to determine the overall short circuit rating of the panel. The lowest rated SCCR of the device within the control panel must be the one that is marked on the panel. Short circuit current ratings. These requirements cover industrial control panels provided with short circuit current ratings. These requirements supplement and in most cases modify the requirements contained elsewhere in the standard. Construction internal wiring connections. All terminals of power circuit wiring connectors and components shall be torqued to the manufacturer's specified value or crimped accordingly to the manufacturer's instructions. Overcurrent protection of control circuits. A panel with a short circuit rating that exceeds 10,000 amps and having a common control circuit not isolated with provisions for field wiring connections for remote control devices shall be provided with branch circuit protection devices having a short circuit current rating equal to the overall panel short circuit current rating. Ratings. The short circuit current rating of the overall industrial control panel shall be determined based on: first, establishing the short circuit current ratings of the individual power circuit components as specified in SB42. Second, modifying the available short circuit current within the portion of the circuit in this panel due to the presence of current limiting components as specified in SB43 when applicable. And third, determining the overall panel short circuit rating as specified in SB44. Short circuit current ratings of individual power circuit components. All power circuit components, including disconnect switches, branch circuit protective devices, branch circuit fuse holders, load controllers, motor overload relays, terminal blocks, and bus bars shall have a short circuit current rating expressed in amperes or kiloamperes, and the voltage. Exception again is power transformers, reactors, current transformers, dry type capacitors, resistors, varistors, and voltmeters, and are not required to have a short circuit current rating. Short circuit current rating of individual power components. The short circuit current rating of the components shall be listed by one of the following methods: a short circuit current rating marked on the component or on instructions provided with the component, a short circuit current rating determined by the voltage rating of the component and the assumed short circuit current table from SB41, or the short circuit current rating of individual power components, the short circuit current rating of the load controller, motor overload relay, or combination motor controller that has been investigated in accordance with the performance requirements, including short circuit test requirements for standard fault currents or high fault currents specified in UL 508, a standard for industrial control and prescribed in the manufacturer's procedure. So these actually have series rated values, right, and they've been tested. High fault short circuit current ratings for a motor controller on an overload relay or a combination motor controller as specified in SB 42.2a or c shall only be used as a short circuit current rating of the component when the specified branch circuit protective device is provided. Short circuit current ratings of individual power components. Exception 1. When specified branch circuit protection related to the high fault current circuit current rating is a class CCG, J, L, RK1, RK5, or T fuse, a fuse of a different class is able to be used at the same high fault rating where the peak let-through current of the new fuse is not greater than that of specified fuse. See Table 2B42 for maximum let-through currents. The exception 2 is the specified branch circuit protection is able to be provided in the field when the panel is marked in accordance with SB 512. Feeder components that limit the short circuit current available. A power transformer that has an isolated secondary winding is able to limit the short circuit current to the isolated secondary fuse as follows. For a power transformer rated not more than 10 kVA, the maximum available short current on the secondary current circuit is limited to 5 kA. For a power transformer rated not more than 5 kVA and a 120 volt AC maximum secondary voltage, the maximum available short circuit current is limited to 2 kA. So most of your CPTs fall into that class. Feeder components that limit the short circuit current available: a listed circuit breaker rated 15 amps or 20 amps, 600 volts or less, and marked current limiting is able to limit the short circuit current available on the load side to 5 kA or 10 kA respectively. A class CCG, J, L, RK1, RK5, and T fuse is able to limit the available short circuit current on the load side of the fuse to be the peak let-through current corresponding to the specific fuse class employed from Table 2B42 based on the current rating of the fuse and the available short circuit current on the line side of the fuse. Determined for each branch circuit, the smallest short circuit current rating on the power circuit components on the load side of the branch circuit protective device shall be determined and compared with the short circuit rating of the branch circuit protective device. The smaller of the two ratings shall be assigned to the line side of the branch circuit protective device. For the isolated secondary circuit of the power transformer as specified in SB 431, the smallest short circuit current value rating of all power circuit components on the load side of the power transformer shall be determined and compared with the short circuit current rating of the power transformer secondary. The ratings of the power circuit components shall not be less than the available short circuit current of the transformer. The short circuit current rating of the primary branch circuit protective devices is able to be assigned to the line side of the power transformer circuit. For the feeder circuit, the smallest short circuit current rating of all branch circuit connected to the source voltage is determined in SB 441 and SB 442, and any feeder components such as disconnecting switches, bus bars, terminal blocks, and feeder overcurrent protected devices shall be determined. The short circuit current rating of the panel shall not exceed the rating of the smallest device or circuit. You have an exception number 1 for feeder circuit protected by a circuit breaker as specified in SB 432. The short circuit current rating of the load side power circuit components and branch circuits shall not be less than the available short circuit current specified in SB 432. The short circuit current rating on the listed circuit breaker is able to be assigned to the line side of the branch circuit protection, and any additional line side components shall be evaluated as specified in SB 443. Another exception for a feeder circuit protector based on the class CC, G, J, L, RK1, RK5, L, or T fuses as specified in SB 433, the short circuit current rating of these load side power circuit components and branch circuits shall not be less than the peak let-through current of the fuse. The short circuit current rating of the fuse or the maximum available current used to determine the peak let-through current from table for SB 42. Whichever is lower shall be assigned to the line side of the fuse, and any additional line side components shall be evaluated to SB 443. Markings. The nameplate rating of the industrial control panel shall include short circuit current, NKA RMS symmetrical volt maximum or the equivalent. An industrial control panel marked with a high fault current short circuit current rating and is not provided with the required branch circuit protective device or specified in the exception SB 423 shall be marked with a type and size of branch circuit protection required to be installed in the field. So if you're requiring somebody to install some branch protection, you would need to tell them what size they have to provide and what type of style they have to provide. This marking shall be included as part of the marking in SB 511. Cautionary markings. An industrial control panel with a short circuit current rating based on the high fault current short circuit current rating of one or more components as specified in SB 423 shall be marked with the word warning and the following statement: risk of fire or electric shock. The opening of the branch circuit protective device may be an indication that a fault current has been interrupted. All current carrying parts and other components protected by this device should be examined and replaced if damaged. If burnout or a current element of an overcurrent relay occurs, the complete overload relay must be replaced. There's some exceptions to these markings. An instantaneous trip circuit breaker used as a branch circuit protection for a combination motor controller shall be marked as specified in 55.6, and self-protected combination motor controllers shall be marked as specified in 55.7. We're almost complete with this. Finally, we have Appendix B, use of unlisted components, and then descriptive procedures information that you would provide, but if you were doing this procedure. After we complete this this section of the UL 508A code, we'll do one more UL 508A code user guide, and then we'll get into CE and IEC control panels. So you've seen this before. Basically, you have it identifies all the different components here, and it lists them off to the right-hand side. So, use of unevaluated components. Sometimes components just flat out aren't UL or UL recognized, and you still need to use them. So, components that are not eligible, that function to cause the opening of a circuit in case of an overload, including running a motor overload, short circuit, or ground fault, where additional safety concerns are present: risk of implosion of a cathode ray tube, risk of explosion, flammable liquids or gases, risk of rupture, high pressures greater than 300 psi. Components not eligible are listed or recognized components used at ratings other than those for which they were evaluated, that have any electrical connection to a power circuit. Any circuit containing a motor or heater is considered a power circuit, or they are located entirely within a circuit that is isolated from the control circuit voltage, where the ground fault circuit interrupter is installed. Use of unevaluated components, components that are eligible, switching and other type control devices within the control circuit that controls loads and other circuitry. These devices are not connected to external devices other than specified in B24, meters, recording devices, and similar components. Use of unevaluated components enclosures. Components shall be completely enclosed within the industrial control panel. Exception 1, the component is able to extend through an opening in the industrial control panel enclosure when the component housing material is fabricated from a polymetric material, the exposed area of which does not exceed 30 square inches, or metal or glass, the exposed area of which does not exceed 100 square inches. Enclosures. Components shall be completely enclosed within the industrial control panel. Exception 2, components of an open type industrial control panel with a sub-enclosure that completely encloses the component, or barriers complying with the requirements for ventilation openings, where a ventilation opening is able to be located at any point in the front of this or to the sides of the unevaluated component. When they talk about an open type industrial control panel, they're talking about the back pan. They're not talking about a totally enclosed panel. So you can be certified to design an open type industrial control panel, and you just happen to set that open type industrial control panel, that back pan, in a NEMA or a type 4 panel if you want. Type. Enclosures. The component shall be connected within the control circuit of the industrial control panel. All inputs to or outputs from the unevaluated component shall be connected to the control circuit components that comply with the component segments of the standard SA1.1 through SA2.5 as shown in figure B21 and described in B22 and B2.4. Transformers. Listed, recognized, or special investigation isolation type transformers, maximum 240 volt secondary. One side of secondary is grounded. Ground fault circuit interrupter, GFCI, listed, class A, 6 milliamp trip, provided in the secondary of the transformer, if receptacle style, load connected to screw terminals, not plugged in. Marking, not for external use, not accessible from outside of the enclosure. Voltages involved, less than 30 volt RMS, 42.4 volts peak, and all ungrounded conductors that extend beyond the enclosure must be protected by a fuse. Fuse rated no more than 0.5 amps within the panel, and fuse located as close as possible to the field wiring terminals, and marked close to fuse. Caution to reduce the risk of fire and replacement. Only the same type of fuse and rating of the fuse or equivalent. Exception, isolated inputs from sensing devices, i.e. transducers, tachometers, thermocouples, etc., need not be fused as noted above. Unevaluated components may be connected to external power source if the voltages involved are less than 30 volts RMS and marked at field wiring terminals. Caution to reduce the risk of electric shock. Connections to these terminals shall not involve potential of greater than 30 volts RMS or 42.4 volts peak between live parts of opposite polarity and between a live part and ground or equivalent. Unevaluated components may be connected to internal power source, that is a low voltage limited energy source, or a class 2 transformer provided as part of the industrial control panel is not required to be fused as noted above. Markings. Warning, use of the following components is dependent upon additional protection afforded by ground fault circuit interrupter and the overcurrent protection device provided. Do not remove or defeat these protective components. So you put the component and the identification, and then you list them all. The ground fault circuit interrupter should be checked periodically for proper operation. Responsibility of the panel manufacturer. Conduct appropriate tests to determine that the GFCI will protect against all likely ground faults. Review application to determine that the overcurrent protection will protect against possible short circuits. Maintain records of all use of unevaluated components, and repeated use may result in a request for product submittal. So you can use it once or twice, right? But if you keep doing it as part of your design, they're going to want you to do a product submittal and just get it evaluated, get it enlisted. So it's not a stopgap all, I just don't even use them. I just flat out don't use unlisted components. I always get them listed or make them part of my procedure. Met Laboratories is pretty good. So if you have a printed circuit board and you designed it per UL standards, they'll look at the spacing, they'll look at all the information that you used in that PC printed circuit board, and they'll run some tests on it, and then they'll say, okay, you can use your printed circuit board in your control panel. And so it's listed for that use. So the next guide is a guide by Siemens. It's a UL 508A guide. It's an excellent guide. I just took their PDF copy and put it in here, and I'm not going to really lean on it very hard. We've gone over everything. You might take a look at it on your own. Certainly you can follow along with the printed out version if you bought the printed out version from or if you went online and got it from Siemens or something. So again, this document covers the guidelines for UL 508A. The scope, we've talked about that. It does not exceed 40 degrees C for the ambient temperature and nothing greater than 600 volts. Complies with National Electrical Code. Gives you different types of connections, how to connect any, different things external of the control panel. Gives you different types of, like conduit or strain reliefs or, different cable tray, what have you. Motor start types in rush current. General motor starter types are across the line. Full voltage non-reversing, cross-line reversing, cross-line reverse type or reverse STR or full voltage reversing, and rush current reducing motor starters. If you want to reduce that motor starter, you can have a part winding, PW, a 2-speed device, a reactor resistance, a Y delta, or an auto starter. You can also have like a soft start or a VFD. Your ambient temperature specified in these standards are measured at 3 to 4 feet around the outside of the industrial control panel. Again, it's based on the NEC. It goes over different NEC articles here. Talks about the authority having jurisdiction, the inspection, the acceptance. We actually saw this before. Listed panel builder, who is a listed panel builder, preliminary acceptance of UL inspectors, authority and responsibility, definitions, ANSI, CSA, ETL, FM, Joint Industrial Council. We went over all of this. We went over UL 489, 508, 508C. We went over the NEC and FPA 70. We went over the different voltage types, 3-phase, 4-wire, 3-phase, 3-wire with a delta grounded leg, electrical circuits. We went over electric circuits with straight voltages and slash voltages. We went over the voltage and frequency details, network tolerances. For AC, voltage of 90% to 110% rated voltage. Sometimes you're not sure how much you can really withstand, so these are things that you could put in your manual. Frequency 60 Hertz, 99% to 101% continuous. Relative humidity 60% to 95% non-condensing. Altitude 1,000 meters. Voltage interruptions 3 milliseconds in intervals greater than 1 second. Voltage dip 20% for 1 full wave. Harmonics max is 10% of rated voltage up to the 5th harmonic. If you don't know what harmonics are, go to that variable frequency drive training class I give, and I explain harmonics pretty decent. So it gives you different voltages. It gives you different grounding and incoming feeders. Service grounds. Separate your service ground from your equipment ground. Some of these when they do those 3-coat epoxy coating paintings, that actually passes a Megger test, so you want to watch out for the special painting on our skids. Basic information about UL, you can go on there, ul.com, ul.com/database. There's a lot of good stuff right there, good websites right there. Different markings. Different markings here, the actual UL marks. Use of UL approved devices, general rules, UL listed variations, UL recognized, that yellow book, they talk about this yellow book here, use of the marks, the listed or recognized, and they go through details on that. This is the product presentation, it kind of goes through that UL certification process. So, you know, if you're thinking about going through this process, this is a nice little breakdown of that process and what you can expect to have to go through and learn and stuff like that. Purpose of the NFPA. What is NFPA 79? What's Article UL 508A, Article 1.3? How that panel is broken up, how that article's, the structure of that UL 508A panel is, Part 1, Part 2, Supplement SA, Supplement SB, Annex A and Annex B, industrial control panels for general applications. Here we have a breakdown of the feeder circuit, the branch circuit, and the branch circuit 2. Also Class 2 control circuits. The definitions for them. And you can come back to this and, you know, read through all this, but at least it'll help you kind of know where a lot of this material came from. Factory wiring and internal wiring versus external wiring. Here's another breakout of the glossary. Here's your field wiring versus marking field wiring. A real stickler for markings. Make sure you get them right. Terminal sizes for field wiring. Here's your ampacities. Make sure again that you don't just follow these tables blindly, that you actually go and use the NEC and derate for when you have multiple current carrying conductors. Ground and neutral wires in the USA, ground and terminals and grounding wires. Size of equipment ground terminals. Number of cables in a conduit. You don't want to exceed 40% fill. Regulations in cable conduit sizes. So what it's telling you here is if you have a 1/2 inch conduit, the metric designation is 16, and you have a conductor size of 10 AWG, then you can only have 3 10 AWGs in a 1/2 inch conduit. Nice little table there. Fill rating of conductors. If you have one conductor, remember we were talking about that, you have one conductor, you can actually fill it up to 53% fill. If you have 2 conductors, you can fill it up to 31%. If you have more than 2 conductors, you can fill it up 40% fill. I always like to just keep it under 40%. Invariably, somebody's going to want to try and pull an extra wire in. Knockouts and knockout holes and dimensions. RMC is rigid metal conduit. RNC is rigid non-metallic conduit. EMT is electric metallic tubing. FMT is flexible metallic tubing. FMC is flexible metal conduit. LFMC is liquid tight metal, a flexible metal conduit. LFNC is liquid tight flexible non-metallic conduit. Those are good definitions because a lot of people don't understand what those are when you put RMC on there or something like that. Wire and conductors, you can use that machine tool wire, rubber insulated wire, thermoplastic, appliance wire, welding cable, wiring methods. Good manual. The internal wiring, the wire bending space, terminal to wall. So if you have a 1/0 size of wire, AWG, 1/0, 1/0, you've got, let's say you've got 2 of them per terminal, then you have to have 5 inches of wire bending space between the terminal and the edge. That's pretty big. It gets real big, and a lot of people don't factor that in. Conductor size, you've got your conductor sizes, internal and industrial control panels, determining the wire size, current carrying capacity, wire size, current capacity exceptions. This is a really good manual, really good guide right here if you got time to go through it. Bus bars. Remember, those bus bars get hot, and you need to maintain your system. Ampacities of bus bars. Conductivity of individual and multiple bus bars. Definitions of descriptive circuits here. Class 1 control circuits, we've already gone over that. low voltage limited energy circuits, external wire cross-sectional. So your internal versus your external wiring, they have different rules, right? Internal wire cross-sectional. Components which can be used in branch circuit protection, installation, sizing, motor control circuits, common control. Typical motor control circuit here. Control circuit containing downstream of the branch circuit protection outside the panel. Control transformers. There's your little chart to do primary winding over current protection only. That's part of the NEC 430. Here you got primary and secondary. Control transformer VA, a practical application. They give you a little example here, help you through it. Got more definitions here. Devices up to 10 amps. Conditions, requirements. Several limited energy circuits can be installed on the secondary side of the control transformer. We talked about that. We talked about class 2 electric circuits, field terminals and class circuits, sizing of control devices. We talked about that. Groups for alternating currents. Groups for direct current. Arranging control circuit contacts. Control circuit load. Talked about that. This is really a good manual though. And if you just do a search on it whenever you get in trouble, you can go back to it and use it as a guide. Electric circuits up to 30 volt AC. Beat that one to death. But they give you a nice little picture here too. So you have a UL Class A 6 milliamp GFCI circuit, and then you can power up your unlisted device. But just remember, just because you can do it once or twice doesn't mean you should keep repeating it. Otherwise, they're going to ask you to get it evaluated. Lighting regulations, cabinet lighting for service or repair. Receptacles, they give you all the rules for the receptacles in a UL panel. Branch circuit, feeder circuit, distances through air and over surfaces. We talked about that and what the distances were. We talked about listed combination motor controller type E and type F. Industrial panel markings. The markings are extremely important. You need to get right. Enclosure accessories. The IP versus UL degree of protection. So you got type 1 versus IP20. We talked about. They give you a little example here. Comparisons of specific applications. General issues concerning device selection. Regulation of non-current carrying metal parts in an industrial control panel. They just basically go over all the articles like we did before. Your doors and your covering plates and the rules associated with them. Give you a practical application. Ventilation, observation windows, fans and blowers and the rules associated with them. Cabinet air conditioners, cabinet heaters, cabinet filters, thermal insulation and enclosures. Don't see that very often. Maybe up north. Markings, required markings. Where can you find the short circuit values for industrial control panels? We went over that. They give you an example of one of their labels and they show you where the short circuit current is. It's 5 kA at 600 volts, largest fuse 150 amps. So they actually tell you exactly what it's rated. Short circuit current overview. So they give exceptions and then they give you that table straight out of UL. So if you don't have if your component doesn't have the listing of the short circuit current, you can just use one of these values. And all the exceptions. You can read through this and understand your short circuit requirements, how the fuses work, the class CC fuses between the threshold and the 50 kA, 100 kA, 200 kA. So it gives you your let-through values for fuse, maximum permissible short circuit rating values, supply circuit disconnecting devices, emergency stop push button. Circuit breakers, according to UL 489, molded case circuit breakers. So they tell you if it's 100% of switches and no integral fuse, 80% for switches with an integrated fuse. Give you all the rules there. Disconnect switches, air circuit breakers, sizing, arrangements of the main disconnecting switch, so you can't go any higher than the high. See, they pointed right to the dead center, but really it's the highest part of the handle is 79 inches. The installation post shall not be any higher than 79 inches. Measure from the surface that the operating personnel stand on at the center position of the handle. I always thought it was the highest. So you have your door interlocking for main disconnecting means and all the rules associated with that. Calculating the main disconnecting means for the feeder breaker. So you go through the calculations. Here's a nice example. Main disconnecting means here. The sum of all the motors times 1.15 plus the sum of all the loads. Circuit breaker UL 489 only for isolating function, not for overload protection. Gives you an example there. Calculating the size of the feeder and the cross-sectional area and American wire gauge. So you got UL 508A feeder is the sum of the loads. 59 per table 28.1 is 6 AWG, 65 amps. Configuration of sizing combination motor controllers. They give you good examples here. And they give you a nice little breakout here, a table. So it goes through each standard and it tells you exactly how it is. Group installations. When you've got one branch circuit protected device feeding multiple motor controls and you got a little heater or something or a panel, power panel out there. So it gives you an example of that. What standards apply. Full load current versus the full load ampere. So you get the nameplate rating versus the table rating. So you can say the nameplate rating says 17.3 horsepower. The full load UL 508A table 51 says it's 21 amps for a 15 horsepower motor. So you can use the UL 508A table for the feeder short circuit, GF device rating, feeder conductor size, branch circuit, short circuit, GF device rating, branch circuit, conductor size, disconnecting means, rating, controller rating. And you use the actual nameplate data for the overload rating. Let me give you a table here, full load amps. Give you another table here for motor blocking current or your locked rotor current. Detailed information about sizing combination motor controllers. Give you approved devices and the sizing associated. Give you a nice little example here. Give you a maximum rating of motor branch circuit device percent of full load amperes. So they take a table straight out of 508A, table 31.1. Maximum rating current range for branch circuit protection is percent of full load current. And they give you an example here, and they include exceptions. Fuses. When you're having contactors and switching devices for load controllers, they give you examples here, step you through it. They talk about AC1 and AC3. Remember the different loads that you have to factor in when you're specifying components or starters. They talk about the Siemens Type 3 RF solid state controllers. They go over overload protection for motors, trip classes, trip settings, According to UL 60947-4-1, the coordination is defined in IEC as type 1 coordination, and then you have type 2 coordination, right? They give you operating conditions. We talk about type E and type F coordination, and the type 3 RV Siemens motor protector solution for type F solutions. Supplementary provisions, we talked about that. Sizing of motor controllers. Suitable for tap connector protection. They go over tap protector connection. NEC 2005 new rules, they give you those. I think we're at 2011 now. And they actually break out the NEC tap rule. If the wire from the tap point of the branch circuit protection GTCP is longer than 7.5 meters, the tap connector B shall be exactly the same size cross-sectional wires as the feeder connector A. So they actually try to break out the different tap rules. It's kind of nice. And they give you the example here where you have your branch circuit protection, your no link limit A, you've got your L, your B, so they actually give you all the rules there and help you step through to understand the tap links. That's kind of a nice chart right there. They give you nameplate rating, give you a breakdown of different starters and the rules associated and the overcurrent settings. 250% of largest full load amps and the summation of all motors for item number 3. They talk about delta, a Y delta magnetic starter combination arrangement. They give you an example here in a table, which is nice. They also talk about 1M and 2M and how it functions. Here's the interlock between the Y and delta combination contactor combinations, and they kind of talk about that. Talk about drives and reversible direction and rotation. You have your soft start version. See how you have 2 SERs back to back, like a thyristor, with a little bypass contactor around it, and the issues associated with that. A little bit more details. Give you some of the rules. Here's a complete soft start 3-phase with a delta winding. And then there's the soft start with the windings in series with each internal arrangement. Frequency converters or variable speed drives. Branch circuit protection for non-motor loads. Go through that. Single appliance non-operating motor loads. Determining the full load ampacity of transformers, heater loads, and capacitor loads. Go through the calcs on that. Overview of power circuits and their functions. So it's a branch or a feeder circuit, the CSA file, the CCNUL file. This is really a nice guide. If you just did nothing but UL control panels or UL CSA control panels with Siemens parts, this would be the guide you'd want to follow. It's a pretty nice guide. Gives you all the breakdowns of everything. Short circuit protection, tells you what application to use it for and what not to use it for. Tables for selecting across the line magnetic controllers. Your selection criteria for Y delta combination, contactor combination arrangements. And then they've got different tables here for your combinations for 30 volt, for 40 volt, 575 volt. They give you some breakdowns, you know, each component, like your air circuit breakers, your molded circuit breakers, and they give you characteristics about them, what standards they comply with. They give you your contactor motor starters, soft starters, fuseless load feeders. We went over most of them. Your transformers, what UL standards they comply to. It's just got some really good products. Your motor starters, your motor management and control devices, coupling relays, power relays, monitoring relays, your different pilot devices, switch disconnectors, receptacles, time counters, your power monitoring devices, how to get to the UL website, how to look it up. They take you step for step through this. So you got UL category, they say type in DIVQ, UL number, you type in E156943, put in your keyword, which would be 3RV, and hit enter. Bam, you'll get their file. Then you can click it and find out all the details about that. You'll get your UL certified directory, and it says the motor controllers manuals and how they can be used and where they can be used. Color coding of the grounding conductors. Color coding of power conductors. Color coding of control circuits. Color coding for control and signal devices. Here's a breakdown. Color red, push button indicator light, or illuminating the push button. It'll give you different ideas. Give you Annex A, the device selection tables for combination motors converters. And tables, 240 volt, type F. So if you're looking for a type F 240 volt motor starter, they give you that table right there. So here's a 240 volt corner grounded delta for a self-protected manual control, motor control, construction type E. They give you the actual motor starter protector, self-protected. They give you the terminal E terminal block. They give you the short circuit rating. And they give you the internal cross-sectional for copper 75 degrees C. Here's a 240 volt corner ground delta magnetic control motor controller construction Z. 480 volt / 277 volt solidly grounded Y, type F, type E, type C. Here's a manual / magnetic motor control construction type C. These are very well written documents that can be used, and it gives you all the information you need to build those construction panels, those industrial control panels. 600 to 347 volts solidly grounded Y. There's all your tables, type E, C. Corner grounded delta. This diagram right here helps you with your start-stop controls, right? So when they talk about a 3-wire open loop control for motor control circuits, you see L1 connects to terminal 1, the stop button connects to 1 and 2, the start button connects to 2 and 3, and you've got the latching M contact that goes around it, and the overloads are on the outside of it. So you can have a 3-wire open loop motor control for motor control circuits with overload relay contacts and holding contacts. So here you'd have multiple stop buttons and multiple start buttons if you had different places where you wanted to interconnect it. 3-wire open loop control on the bottom for motor control circuits with overload relays and holding contact M with toggle switch 2 position for off, save, and operation run. You got your forward and reverse on the bottom right. So different versions of forward and reverse. Here's a stop, slow, fast, limit switches, a jog. I talk about jog in that VFD course, but basically if you just wanted to bump the motor and allow it to turn, rotate, you hit the jog button and it quickly releases it. It doesn't latch in. You can check rotation. You can also kind of inch up a motor or something like that if you've got some type of a conveyor belt or something. Open loop control for 3-velocity circuit. Size 0 to 2.5 with transformer and 3-position toggle switch. These are nice little control circuits you can use to add to your libraries. Classification, control circuits. So this gives you your AC12 classification for close and open, and then your DC12 and 13 and 14 for your DC circuits, close and open. So if you purchase this this course from the eBay website, you will actually have the guide information for electrical equipment, the white book, It's additional information you'll need to understand. You can download it directly off the UL 5088 website, but I went ahead and included it for you. And next thing we're going to talk about is CE and ATEX certified panel. First thing I want you to do is go ahead and watch the NEC area classification CDs. There's 2 DVDs that I included with this course, and this will bring you up to speed on ATEX and hazardous areas. So a CE panel is similar to just a general purpose UL 5088 panel. It's just built to IEC standards. An ATEX is a general purpose panel but put into a classified area. So you might add a purge system to it. You might put it in a special enclosure that can withstand the arcing, the fault, or not the fault, but the environment. Intrinsically safe, encapsulated. There's all kinds of different ones. Actually, they're listed right there. The 600792, 600797. These are all different examples. That EN 1050 at the bottom, risk analysis, I think that has been actually changed with the 61508, but I went ahead and included it as well. Self-declaration, depending on the level of risk of the product, the CE marking is affixed to a product by the manufacturer or authorized representative who decides whether the product meets all the CE marking requirements. If a product has minimal risk, it can be self-certified, where manufacturers a declaration of conformity and affixes the CE marking to their own product. Manufacturers must do several things before they can do this. So what the manufacturer should do is decide whether the product needs to have a CE marking, and if the product applies to more than one directive, it needs to comply with all of them. Choose the conformity assessment procedure from the modules called out by the directive for the product. There are several modules available for the conformity assessment procedures, as listed below. Module A is for internal production control. Module B is for EC type examination. Module C is for conformity to type. Module D is production quality assurance. Module E is for product quality assurance. Module F is for product verification. Module G is for unit verification. And then Module H is for full quality assurance. The only time you have to CE label a panel is if you're shipping it to a European country that requires CE markings, such as France, Germany, just anywhere in the European area. There's in that NEC article area classification, I circle all the areas that are European countries. You'll also find in this CD or DVD there's a manual called Guidelines, the CE Guidelines, or a product manual, and it shows you step for step which countries you have to comply with on this. These will often ask questions about the product to classify the level of risk and then refer to the conformity assessment procedures chart. This shows all the acceptable options available to manufacturers to certify and affix the CE marking. Even the CE it's so defined how they make that CE. It's incredible how much effort they went into it. Stage 1, identify the applicable directives. Stage 2, identify the applicable requirements of the directives. Stage 3, identify an appropriate route to conformity. Stage 4, assessment of the product's conformity. Stage 5, compile the technical documentation files. Stage 6, make a declaration and affix the CE marking. So basically what you do is, once you've identified all the applicable directives, take the directives and identify the applicable ones that are for you, that you comply to your panel. Identify an appropriate route to conformity. What I would do is I would take all those standards and, bring all the standards into Excel spreadsheets so that you can create a document that says, yes, I comply, no, I don't comply, or not, it's not applicable, and comments. And put comments in every section so that when you're done with this questionnaire, you can put this as part of your technical construction file, your technical documentation. Then what you do is you pull every component in that panel, including the panel itself, including all the wiring, everything. make sure you have a construction, a declaration of conformity that shows that these are ENCE marked devices for your control panel and that they're suitable for that control panel. Once you've compiled all your components, you've compiled all of your directives, then you go through that directives and that questionnaire and you answer all those questions. You add the appropriate guards, you add the appropriate labels, you add the appropriate ESD stops, you make sure you build the panel per CE directives. You draw the symbols not like an American or JIC type symbol. You use the European symbols, right, so that you design it in a European fashion so that it looks like a CE drawing, a European drawing. When you're finished with that and you've compiled this technical documentation, you don't have to give it away. You can just file it, right? The only time you want to show the technical construction file is if somebody challenges you and they come and visit your office, then you can show them your technical construction file. It might have proprietary information that you don't want to let anybody else have. Make sure the drawings are available and have all the proper markings as well. Then you make a declaration of conformity. If somebody challenges you on a CE panel, you can say, no, here's my declaration of conformity for that control panel or for that skidded package. And you have to affix a CE marking on that panel. The Chinese, I'm sure they did this for other reasons, but they put China export, right? So it's a China exported CE symbol. And so the difference between the CE logo and the alleged China export mark, you got to watch for that, right? They look so similar, and I'm sure that's exactly why they made it. You don't want to be confused with that, and you certainly don't want to get into trouble because you can be blacklisted where you cannot ship another control panel or a skidded package into a European Union area. IEC 60079 specifies general requirements for construction, testing, and making electrical apparatus and EX components intended for use in explosive gas atmospheres. So you need to go through all the 60079-1. Make sure you're using flame-proof enclosures. If you're using a flame-proof enclosure, that's what you need to follow. So you need to go through this standard and create that questionnaire and make sure that you comply to each section of this questionnaire. And this would be for like an ATEX Zone 2 type panel. Standard is supplemented or modified by the following parts. So the -1 is the flame-proof enclosures. It's got the D, right? Pressurized enclosures is the P. Powder filled is Q. Oil immersed is O. Increased safety is E. Intrinsic safety is I. Tight protection N. And then encapsulation is M. So kind of similar to what we do in America. We have pressurized enclosures. We have flame-proof enclosures, the big NEMA 7 Krauss-Heinz boxes. But just figure out what you're doing and how you're complying and make sure everything that you put on that skid or in that control panel is listed for the environment. So here you got different standards that you might have to comply with. 60034-5 for rotating electrical machines. 79-1, we talked about that, explosive atmospheres. 79-18 is the encapsulated M. So this would be more like a hazardous classified areas or a skidded package where you had some motors on it. So you want to prepare your technical construction file. You first need to prepare a technical construction file. Obtain the IEC standards that are applicable, and then put each paragraph or sentence of each standard in an Excel file. Address each item. Note the hazard, the compliance, yes or no, not applicable, and always add comments. When you probably have a standard product line you're doing anyway, so once you've done this once or twice, you'll understand it and you can quickly go through it. But one of the things that I liked about going through this EN process or CE process or following these EN standards was because it made our system a little safer. It was like, well, why don't we put guards on our motor? between the motor coupling of a pump and a motor, because it made it safer. Because now somebody, if they were to fall into it, the chances of getting hung up into that motor are slim to none, right? So it's just a better system when you went through this, because you're always building, you're complying with your NEC standards, but by adding an additional level of detail, you're actually making it safer. So here is a design and engineering hazard questionnaire. So basically you go through your different standards, right? And you create these hazard questions, right? Has the risk of cutting, scraping resulting from sharp edges or corners been excluded wherever possible? You would think that that's true, right? But if you went out there and looked at your skids, you might find some sharp edges or corners, right? So you just have somebody just walk out there and check for sharp edges or corners, and if they find one, go back to your manufacturing process and say, hey, look, why don't we change that design so that it's more rounded, so it doesn't have sharp corners. You'd be surprised that after you go through this, you'll feel good about your unit. You'll feel like you've increased its quality. Are there guards installed next to moving parts such as gears? Sometimes we didn't do that, and when we didn't do it, we actually put fixed guards on these pumps, right? It's a good idea. Are there guards installed next to moving parts such as fan blades? If there's a fan blade and you can stick your finger in there, that's a problem. Make sure that it can't be, somebody can't get hung up into it. Make sure that it's safe, right? So you repeat these Excel questionnaires for the following modules. For module A, B, C, D, E, F, G, and H. It's a lot of work. I'm telling you what, this process is a lot of work. So for a typical control panel, you can't really see the top. I think it says EN292-1. You need to find that standard. Safety for machineries, emergency stop, EN418, EN547-1, the whole body. EN547-2, access openings, EN547-3, surface temperatures, ergonomics, the EN614-1, these might have changed, I don't know, maybe there's a 60 in front of each one. Lower limbs, ergonomics for displays, ergonomics for controls, EN953 for guards. There's EN953 ET for guards. There's EN954-1 for control systems. You have EN1037 for unexpected startups. So these are questionnaires you'll have to go through. EN1050 is the older risk assessment. EN1088 is your interlocks. And then EN60204 is electrical safety. If you go through every one of those standards and make sure you have the latest standards on file, you'll realize, hey, you know what? This process, although it's very time consuming, actually improves your quality and makes your product a better product. So I'm not saying it's easy. I'm just saying that if you have to do it, it's doable. You might want to get some help from Met Laboratories or maybe from TUV or somebody that's real knowledgeable in these areas. Once you're done, create a declaration of conformity. Put your company logo at the top there and just write all the directives that you comply to. These list most of the directives for a typical skidded package for an offshore application. Put the day and the month that it was affixed and the year. Whoever the engineering director or whatever engineering supervisor or the design engineer, they put their signature there. The quality assurance manager puts their signature there. The engineering manager puts their signature there. And make sure that you guys all embrace this declaration of conformity and make sure that nobody's just trying to gun deck the report or anything. Another thing you want to do is go through that electromagnetic compatibility directive. It's a little harder to do, but it is. So you got to go through the EMC electromagnetic compatibility directive. Again, you create an Excel spreadsheet file for the EMC directive, and you step through and answer all the questions. If you have something you're not aware of, find out through a manufacturer how you can solve that particular directive and question. It might be just a different component that you need. on all the components, but every component you used to build the panel, including CE paperwork from each manufacturer in your technical construction file. Keep the file in a safe place. You only need to have it in case someone challenges you. It is always best to include an NRTL, a nationally recognized testing laboratory, to do the first certification, be it UL 508A or CE or ATEX for Zone 2, especially if you have repeat products, because once they've done one, you can just keep copying it over and over and over, the procedure. That's it. I thank you for taking the time to learn about industrial control panels. I hope you found the material to be helpful, and hopefully it improves your quality. If you have any questions, you can email me at vwedelich@gmail.com. Again, I did not create any of this material myself. All of it was taken from the internet or from different sites that I saw on the internet. I'm not trying to take any of their work from them or copyright any of that information. I'm just solely putting together an audio and a recording for you to learn from, and I hope you enjoyed it. Thanks a lot.